Hello, I'm Jim Mielke, Professor and Chair of the Department of Fire Protection Engineering, and it's my pleasure to kick off a class in the effect of fires on people, property, and the environment. As part of this course, we're going to provide an overview of fire safety and fire protection engineering. For the overall course, we want to take a look at development of fires in buildings, examine or talk about the array of fire protection systems that are available and are used to mitigate damage from fire, describe the scope of fire protection engineering, talk about how people are affected by fire and how people respond to fire, talk about how structures are affected, how property and contents are affected, and in some cases because of thermal damage, in other cases because of interaction with smoke and corrosive products at combustion. And then finally, we want to talk a little bit about how one develops a solution, a fire safety solution to a building, and what sort of thought process a practicing engineer would go through to deliver a particular level of fire safety. I'm going to be doing much of the presentation for this course, but I'm also going to be assisted in 3 of the 6 presentations that we're going to make. One in talking about the discipline of fire protection engineering, and that will be offered by Chris Jelenowitz, who is the engineering program manager of the Society of Fire Protection Engineers. The discussion on the effect of fire on people will be given by Dr. Erica Kulagowski, who is a fire protection engineer and sociologist with the National Institute of Standards and Technology. And then finally, the discussion on implementing fire safety designs and the solutions will be developed by Eric Rosenbaum, who is a vice president of Hughes Associates. As part of this course, we'll anticipate that you'll get involved in the class a bit. There will be short discussion papers that will be associated with each of the weekly modules. These discussion topics will be included in each of the presentations, typically near the end of the presentation. And the idea of each of these presentations is to allow you, the participant in this course, to apply the material in the module and really be able to appreciate what's involved as a part of that particular topic. Perhaps conduct a little research. So the intent is that you go a little bit beyond what is presented in the discussions, and do a little bit of research to further explore a particular topic. As part of any of these discussion papers, we ask that you provide at least one outside reference in each of your discussion papers, and there should be a citation of that respective reference. So just very briefly, as much as you're going to hear from Chris Jelenowitz in much more detail about what is fire protection engineering, but I felt it was appropriate to have at least a little discussion here in this beginning presentation as to what is this field of fire protection engineering. And the definition from the Society of Fire Protection Engineers is that fire protection engineers use science and technology to make our world safe from fire. Well, what's that mean? What's making the world safe from fire mean? And it means we're going to provide protection to people that would be exposed to the fire. We'd be providing protection to property and contents, to the environment, and perhaps to the economy. You see in the couple of photos here of the MGM Grand, first of all, and the fire in Las Vegas in November of 1980, where 84 people died. Very much a life safety issue was involved in that incident with the deaths, the many injuries. The hotel was out of business from November until the following July, until the renovations could be made and following the fire. Another incident just very recently in the Philadelphia area of a Dietz and Watson warehouse. So again, a huge amount of property and contents damage. But the other major piece of that was damage to the local economy, because now you've got a facility that's obviously going to be out of business for quite a while until the structure's rebuilt, and now all those workers that were part of that facility are now out of work, basically. So that provides an impact to the local economy when such a devastating fire occurs. Fires occur frequently. They are rare events in general. For any one of us, it's rare that we experience a fire in our own personal lives, but they occur. And as you think about the media reports that you find that fires are in the media pretty much all the time. They occur in all areas of our world. Certainly, much of our focus is going to be on building fires. So this is a fire in Los Angeles in the 1990s. There are fires in our homes or in homes. This is the Dietz and Watson fire, again, from a little different perspective, or earlier in the day. As that was going, they occur in cruise ships, an assortment of transportation vehicles, and our space capsules are not immune from that, with the Apollo fire that killed astronauts in that incident. And then there are wildland fires that occur as well. We'll mention just again in a beginning sort of overview. So this course is being provided from the Fire Protection Engineering Department at the University of Maryland. And the one item that I'll mention about our program at Maryland is that we're unique. We are the only professionally accredited fire protection engineering undergraduate program in the United States. So that makes us very, very special, very unique sort of institution. Further, at Maryland, we have one of 3 fire protection engineering graduate degrees in the United States. So that the combination of the undergrad and the graduate program at any American university is only here. Again, you'll hear more about the discipline of fire protection engineering, but a question that often comes up for a student that gets in our degree program here, where might they go for employers? And you can see logos of several of the employers. And the first way I should answer where do the fire protection engineering graduates go for employment, the comment I'd make is that they basically go to the same type of entities as any other engineer. So fire protection engineers are not particularly special in that regard. For us, some of the logos of recent employers are indicated here. So we have consulting engineering companies on the far right-hand side of the slide, and these are logos of consulting engineering companies that are principally fire protection engineering consulting companies. So you can see the Koffel Associates and Hughes and RJA, Aon has a consulting group, Code Consultants and Pool Fire Protection are all fire protection engineering consulting companies, so that perhaps are relatively small names for people, for those of you who are from outside the fire protection engineering field, but are very, very much significant entities, at least in fire protection engineering here in the U.S. Fortune 500 companies employ fire protection engineers, and you can recognize logos from several of the entities. Many of these people, the Marriott and Disney World, ExxonMobil, Intel, all the fire protection engineers there are involved with protecting or being concerned with protecting the facilities of that corporation. Siemens and Simplex Grinnell are manufacturers of products, of fire protection products. So the engineers that are there look at products, and then those at UL are looking at those products, but from a certification or a listing process. And then finally, the government agencies hire fire protection engineers just like they hire any other engineering discipline. So you see some logos here of fire protection engineers working with government agencies where they're involved in research, perhaps in setting regulation, or again, perhaps in overseeing the fire safety of the facilities of that agency. The one exception to that profile would be those at ATF, that is a fire investigation group that gets involved traveling nationally to a fire investigation where there's the possibility of a federal crime that's being committed, or perhaps where local fire investigators need some help with the investigation that they're confronted with. So with that very brief introduction, again, we'll hear much more of that in another segment from Chris Jelenowitz, but wanted to provide a little perspective for you as we start our walk through this introductory course. And talking about fire protection engineers and what is the discipline, we've said that fire protection engineers use science and technology to make our world safe from fire. And then finally, or second, want to emphasize one of the key characteristics and why this is being offered from Maryland is that the University of Maryland Fire Protection Engineering program is truly one of a kind, having the only ABET accredited undergraduate program in the country and also having a graduate degree program here as well. So with that, we'll bring this to a close and come back with another segment very briefly that we'll talk about fire behavior. Okay, so welcome back. This is the topic for week one is to discuss fire behavior, and as part of that fire behavior discussion, we want to talk about some basic sort of issues involving flames. So, what is a flame? How is a flame structured? Talk a bit about what products are produced by fires, and then the third part of this discussion in fire behavior, we'll talk about the growth of fires in rooms or compartments, as we call them. We start the presentation or this whole discussion on introduction to fire safety with fires, in that fires end up being the challenge or being the demand that fire protection engineers have to respond to. So that it's important to understand what that challenge is first before we can start talking about ways to mitigate the hazards associated with a fire. So as we look to flames, we want to talk a little bit about, so what is a fire, first of all, that this flame is an indication of? And as we look at a fire, the first point is that a fire is a chemical reaction. So it's a chemical reaction that involves the mixture of a fuel and an oxidizer, and the result of that is that there's a release of heat, and often the energy generation will get generated and released in the visible wavelength, so you'd have light that would get created as well. This chain reaction, or this chemical reaction, I should say, gets depicted with this fire tetrahedron, where there are four sides to this object, and the idea of this tetrahedron is that there are four items that are essential to have a fire, for an ignition of a fire. We'll look at that same fire tetrahedron, I should say, in terms of suppression strategies or extinguishment strategies in a converse sort of way in a later week, where we'll look to pulling one of those sides away that would say that the fire can't continue burning and has to go out. But let's talk about ignition first of all. So we need four things. The one is an oxidizer, and the typical oxidizer that we have or that is available for fires is oxygen in the air. The next item is the fuel, or as the chemist would call it, a reducing agent. And the fuels can be in any one of the physical phases. So solid fuels could involve woods and plastics. Liquid fuels could be gasoline and other flammable or combustible liquids. The gaseous fuels might be hydrogen, natural gas, propane, and so on. The fires need heat to get the process going, and this heat could be in the form of sparks and other flames that are available, lightning, arcing perhaps might be a source of energy or a source of some heat to get the process going. And finally, then a chain reaction is needed to keep things going so that it isn't just a little flash, but is a sustained fire that continues to burn. So we need all four of these things to have a fire. As we look then to the flame, that is one of the indications that a fire is present. There have been several studies of flame, and it seems very, very simple that we get used to seeing flames as part of an environment that perhaps a homeowner tries to create with a little candle, or every birthday in your birthday cake, you put the candles there perhaps. So we're very used to seeing candles in our environment, as well as at birthday time perhaps as well. But a flame is actually a fairly complex entity in that it involves processes of chemical kinetics, so some of the chemistry that goes on to make this fire, fluid dynamics, heat transfer, thermodynamics, all play a role, so that in providing a really elaborate, comprehensive study of a flame, the flame is actually a fairly complex beast. Candle flames are buoyant, and so this is part of the fluid mechanics and heat transfer that's going on. As we experience the candle flames in our environments, the hot gases rise because of buoyancy, so the candle flame takes on this conical sort of profile that you see as a result of, again, the buoyancy that's causing that hot air to rise. If we take the gravity away, such as in a microgravity application or a spacecraft application, now the flame takes on a spherical shape, so there's no gravity that's giving us the buoyancy effect to give that rising hot gas anymore. So gravity is going to make a difference, very, very significant difference in flame structure, let alone how flames spread and overall fire behavior. Well, let's look inside this flame a bit here. So this flame that you're used to seeing at the top of a candle, we want to look to that structure. So what's going on with this flame? That we want to look at the flame and that fire tetrahedron again. So what's burning? What's the fuel, right? What's the fuel? And with the fuel here is, of course, the candle wax that is melting as a result of the heat input from the flame. It travels up the wick. It evaporates. So we have fuel vapor now that is available. Air is coming in from the sides. It's being brought in by the fluid dynamics that's involved, so being brought in close to the vicinity of the flame, mixes with the fuel, and if there is heat present, consider fire tetrahedron again, there we get ignition with a chain reaction that ensues. So a question I ask you is, what is inside this flame? Right? If the flame is an indication of where the chemical reaction is going on, is that chemical reaction going on throughout the entire volume of the flame, either here or in this little lab version of a candle flame? So is it in that entire volume, or is it just on the edges? Let's take a look. Let's look inside. Let's look inside. We can use this wire gauze to cut the flame, and that the wire gauze stops the flame from traveling up by removing heat locally. So as we look over in here, we see the wire gauze on top cutting the flame, and the flame's not able to extend to its normal conical sort of shape as a result of heat removal. So we've taken something away from the upper part of the flame. We can look down inside the flame and you see it's hollow, so that the actual chemical reaction's going on the edges, and only on the edges. And the reason it's not going on throughout the entire volume of the flame is that the oxygen that's coming from the outside basically gets consumed on the edge, and there's not sufficient oxygen getting into the inside to allow the chemical reaction to go with the fuel. So today, to answer the question from the previous slide is, so what's inside? What's inside that you're seeing here in this hole is fuel vapor. Basically, nominally 100% fuel vapor, very, very little oxygen. And without having the sufficient oxygen to burn, we don't have any combustion of the fuel vapor inside until it diffuses to the outer edges to where that reaction's actually going on. This is the elevation view of cutting the flame. Right? So you see that the flame has been cut, and that's through heat removal here with this wire gauze. In indication in the top here, we can reignite the flames up here by introducing some heat. There is still fuel vapor in here traveling up. It's hot, right, as a result of being heated up from the flames, so that fuel vapor is still traveling up. It's lost its heat source for ignition. There's still plenty of oxygen, of course, up in here. And as we add the heat to it up above, we can reignite those fuel vapors up above. So in this little segment, we looked at what is a fire, and have understood that a fire is a chemical reaction. It needs 4 entities to be able to occur. It needs heat, fuel, air, and needs to have that sustained chemical chain reaction. We briefly mentioned suppression, and that suppression can be done by removing any one of those 4 entities, and that's a topic of discussion for a later week in much more detail. And then otherwise, flames that we see, and perhaps we take for granted, at least come birthday candle time, these behave according to physical and chemical mechanisms. Again, the chemical kinetics are certainly there that are dictating how this reaction goes of the chemical constituents. And the physical processes are fluid mechanics and heat transfer and thermodynamics. And going through, again, a comprehensive discussion of any of those items, even for the very, very simple candle flame, let alone flames involving more significant fuel items such as mattresses and sofas and the like. This is a fairly complex area of study. Well, with that, we'll bring this particular module to a close and come back in a bit to talk about what fire produces. Welcome back. This is a continuation of the week 1 discussion, and now we want to talk about what is produced by a fire. Fires, again, we've talked about these as a chemical reaction previously, and it's an oxidation reduction reaction, as the chemists would call it. It's accompanied by light and heat, typically, as we talked about also previously. The products, then, that you get out of a fire, out of this chemical reaction, or energy, and then secondly, chemical species, or the combustion products that may be in a variety of physical forms. Can be gases, can be liquids, can be ash left behind, of course, solid particles or soot that would get generated. So let's talk about these products of combustion. And the first of these will be energy that we'll talk about. And there are a couple ways to characterize how much energy is released. The one parameter that's used is called the heat of combustion. The test for it, I have a graphic running here from a University of Missouri professor, put together this very nice animation of the oxygen calorimeter, where we put the fuel in a pelletized form in this oxygen bomb, have it surrounded or have enclosed in a pure oxygen environment, introduce a spark, the combustion process occurs, and the heat generated by that combustion process gets transferred into a water bath. The temperature rise in the water bath is noted, and we know for a particular amount of temperature rise of water how much energy had to be introduced to the water to make that happen. So that we can get a measure of heat of combustion then, or the amount of heat that you get from the combustion of a particular fuel that gets measured in kilojoules, and that would get normalized by the amount of mass that was used. So we talk about a heat of combustion in terms of kilojoules per gram of a particular fuel item. Every fuel has its own heat of combustion based on the combustion chemistry that's involved. I have a few items that are here, fairly common fuels that you would encounter or could find in an office environment, in a home environment, You can see the array of heats of combustion that are in the 10s, 20s, 30s of kilojoules per gram sort of area, but we do see a fair range of the low being the corrugated carton at 13.9 kilojoules per gram and the high being polystyrene at 39.2. Heat of combustion is a useful measure to assess of if a particular fuel array burns in a room, what's the total heat output that room is going to experience, that one can then maybe make some temperature estimates based on some elementary thermodynamics. So heat of combustion gets used in these fuel load calculations, as they're called, that helps to assess how much fuel is present, or what's the energy content, as it sometimes gets called, of the fuel that's in a room or in a compartment. So that I have an office environment here that was used in an experiment several years back, 1971 to be specific. You see the array of fuels, the papers and so on that are present on top of the desks. So that if it was all paper, we'd be able to weigh all the wood, and literally the fuel load studies are done that way, that one has a scale. You put all the fuels on top of the scale, get the total mass of that fuel as a way to assess what's the total amount of fuel that's present in an office environment, or maybe in a library or a warehouse or wherever it might be. The challenge, though, becomes in real environments, in real buildings, in real rooms, there's usually not just one fuel present. Usually several fuels that are present. As I look in this room where I'm providing this lecture, there is some wood products, there are some polymers, there's a carpet, there's again some cushioning, and just thinking of some of the polymers. So we have a wide array of fuels that are present in this relatively small classroom. And where these mixed fuels are present, we'd want to have a way to try and combine the role of wood and whatever polymer might be there to assess what's the total energy content associated with the array of fuels in the space. So that the way that's done is through a mixed average or weighted average sort of approach. So where mixed fuels are present, we're going to combine the weights of all the fuels by using an equivalent weight of wood concept. Is what gets used. So wood ends up being the baseline material that everything gets compared to, and that's largely historic in reason, I think, in that wood was a very dominant fuel in buildings in the early 1900s, mid-1900s, when this concept was being introduced and thought about, and we've basically stayed with that norm ever since. So that as we look at fuel load, we're going to look at the mass of wood then that has the same heat output as that produced by the mass of another material. For example, if there are 10 kilograms of polyurethane that are present, I want to sort out or assess how much wood equivalent would that be to provide that same heat output. I multiply the mass of the polyurethane by the ratio of the heats of combustion of polyurethane to the wood. And you see that I've got those on the previous slide here. So you find that the 10 kilograms of polyurethane are equivalent to 14 kilograms of wood in terms of potential heat content. Fuel load ends up being a surrogate measure or becomes associated, I should say, becomes associated with how the building's being used. So as you picture an office building, you picture a particular fuel load that might be there, and maybe an open office plan. I showed you the slide a couple slides ago of all the paper on top of the desks. There's a library environment, very different amount of fuel here than here. So that one of the differences in use of a building and the fire hazards associated with that would be the fuel that's present. But we have to keep in mind that fuel load's not the only parameter that's useful in assessing or estimating fire severity or comparing fire severity of one place to another. And there was a hospital room experiment done here locally in the late 1960s, as it is. So a hospital room, you can see the dimensions of it, so 16 square meters in floor area. The fuel was limited to what you see right here, so this plywood wardrobe. It was 64 kilograms of fuel that has a fuel load in the way that the fuel load usually gets expressed, not just in terms of the total mass, but total mass per unit floor area. So we've got a fuel load here of 4 kilograms a square meter. And by an assortment of measures, if you were to do an assessment of a room, or if you saw a room and only saw that in it, you'd say, well, that's not going to be very much of a problem. How bad of a fire could that be? Well, because of the way the fuel is arranged here, and because it's in the corner of the room, where you can create the worst-case thermal conditions if the fuel's all accumulated in one local area, and that local area happens to be a corner, that the whole room becomes involved in fire in this experiment, where you would have said, that can't be much of a hazard. So one of the takeaways from that comment is that fuel load ignores, if we're only going to base, to my statement here, if we're only going to base fire severity on fuel load, that ignores the following things that were reflected in this example. Fuel distribution and arrangement, ventilation becomes a key player, and that's an item that we'll talk a little bit more about in the next segment, actually, and compartment construction. So that the temperature development in a space depends on how well insulated the room is, and the better insulated the room is, the more the temperature is held inside, the heat, I should say, is held inside, and the greater temperature rise we're going to get in the room as a result. So that heat of combustion is an interesting parameter. It's a useful parameter in assessing or comparing fire severity of one facility to the next, but it's not the only measure. And that's a key point to understand. Another very significant parameter is rate of heat release, or heat release rate, as I title this slide. And that is the amount of heat that's released per unit time. Gets reported in kilowatts, typically. Where a kilowatt, keep in mind, is a kilojoule per second. So we're looking at the heat release. And before, with heat of combustion, it was just kilojoules, right? There was no time unit. So there was no time significance there as to whether you get that heat in a second or a day. It's the same heat of combustion. Right? Here, now we are concerned with the rate of heat generation. That makes all the difference in early fire development. Right? Rate of heat release is again, measured in kilowatts. One of the ways to assess rate of heat release is, at least in a simple way, is to say, so what sort of flame height do you see from a particular fuel item? In that the flame height that one gets from a fire will be tied to the heat release rate from that fuel. The heat release rate becomes a key starting point for many analyses that we do in our field that involves early fire behavior. All right, so before the room becomes fully involved in flame. This gets used an awful lot in fire investigations, as well as a starting point in a reconstruction of an incident. So that one of the ways to estimate initial rate of heat release is you're looking at a particular fire, or you're maybe interviewing eyewitnesses of a fire or emergency responders who have seen a fire, so how tall were the flames? And if we had a fire that was away from the walls, for example, and let's say the flames were let's not go 3 meters, let's do 2 meters tall, all right, we could come on across and estimate a heat release rate as a result of the flame heights that were observed. So 2 meters, 3 meters may be an easier one to look at for a specific example. So we come over 3 meters, we're here, and then up, and we're about 1,000 kilowatts or so, approximately. Heat release rate is dependent on the fuel, but also dependent on how that fuel is configured, as well as how it's oriented, right? So we have an example here of some furnishings of sofas and love seats and a single chair. I show a love seat experiment here. Furnishings typically have this growth pattern, so the heat release rate starts out very, very small. in the beginning as the fire starts, of course, and then goes through this curved profile on up to a peak, and then at that point starts to decay as the fire starts to run out of fuel. Very characteristic of an awful lot of fuels to have this sort of profile. However, I will say that the heat release rate of a chair, such as I show here, has a peak heat release rate of about 2,000 kilowatts or so. That particular profile varies an awful lot from chair to chair to chair. So not all chairs are equal at all, and that one could have a chair with significant cushions like this, as compared to maybe a desk chair that you'd have that doesn't have that lot of cushioning. Does the chair have solid arms? What's it made of? Makes a difference for sure. So that these are simply examples, and the only way you'd be able to find out what's the heat release rate for a particular chair of interest to you would be to run a test. The heat release rate itself is affected by ignition scenarios. So what are we igniting this item with, especially that early profile of the heat release rate curve, that is this first little bit down here, right? Depends on what we ignite that item with, and is it a trash can? Is it a smoldering source? Am I using an acetylene torch? What's being used? The fuel characteristics make a difference, as I mentioned. And then there are some enclosure effects. So if I burn this item in a room, in a small room, where there's already a hot smoke layer present and another item burning nearby, the initial ignition, let alone heat release rate of that second item might ignite, will be affected and will be different than if I just burn that item in the middle of a warehouse somewhere. Moving on from energy products or energy-related products, I want to talk about organic fuels and inorganic fuel-related chemical products of combustion. So that as we look at the chemical species, so what's in this smoke that you see here in a recent fire on the Jersey Shore? It started in this ice cream shop, at least so it's believed. As we look to the combustion products for organic fuels, so we have to think the organic chemistry. So these are fuels that contain carbon and hydrogen. For all of them, we get carbon dioxide, and that's kind of the ideal product that you get. If you wrote out a simple chemical equation for the combustion of methane, you'd write that the combustion products are carbon dioxide and water vapor, and that assumes complete and perfect ideal combustion. So we get the carbon dioxide and water vapor that you see here. But we also realistically get carbon monoxide, because the combustion process is not going to be perfect or complete. We'll get carbon, we'll get unburned hydrocarbons, so that some of the polymers will unzip and produce monomers as an initial byproduct of that fire. There are other chemical products of combustion that are the result of, so exactly what is the fuel composed of. And if the fuel contains nitrogen, then there are nitrogen-containing compounds that are produced by the fire. So the nitrous oxides, the cyanide will get produced where there's nitrogen containing. And to that point, I just want to dispel a myth that the nitrogen in the air typically does not dissociate. There's not sufficient energy available in a normal fire to cause the nitrogen in the air to dissociate to get the nitrous oxides and the cyanides. The sulfur oxides, where the fuel again contains sulfur. The chlorines, chlorine-containing compounds here, are where the fuel contains chlorine, such as polyvinyl chloride. One of the combustion byproducts is going to be these chlorine-containing compounds. Right? For the inorganic fuels, which means the combustible metals, notably, so a fire involving aluminum, magnesium, uranium, we're not going to get carbon dioxide and carbon monoxide up here, because there's no carbon involved in the chemical process anywhere. So we're going to get metal oxides. There'll be aluminum oxide and uranium oxide and those type of substances. So, as a summary to this particular segment, the couple takeaways should be that the fires generate energy and gaseous combustion products, so the two different categories of combustion products. that the important characteristics of fuel packages is their heat of combustion and their heat release rate. Those will be key factors in dictating the thermal environment that's created in a fire early on, let alone as the fire potentially becomes, the room becomes potentially fully involved in fire, as well as will dictate how long a particular fire will burn, will be part of the heat of combustion. So with that, we will call a close to this segment and continue shortly with a discussion on the fire behavior in a room or in a compartment. Welcome back. This is the last segment of our week 1 discussion on fire behavior. We have talked about flames and the basic structure of flames. We talked about what is produced in fires in the way of energy release, in the way of chemical species. And now we want to talk about the fire development process in a compartment or in a room. The fire development in a room is going to go through these particular phases. So there's a growth stage, and that gets referred to as pre-flashover, which says that there are just a few items burning in the room and don't have that full room involvement yet. So we want to talk about a fire plume and what's a ceiling jet, and then the formation of a smoke layer, and these are different stages in the development of a fire in a room. Go through the discussion of flashover, at which point nominally everything is burning simultaneously in the space, and then after that transition, a little bit about post-flashover fires. Well, the fire development in a space is going to be governed principally by fluid mechanics, heat transfer, thermodynamics, some chemical kinetics, of course, but the dominant mechanisms are more from the physics side of the issue. As we look at the beginning of a fire, so the fire is localized. It's going to be in a small portion of a fuel package, so on a cushion of the sofa, for example, or a very small part. But the fire is now certainly there and sustained in some very early stages of the fire. That you may see flame a little bit, and then it'll go away and back and forth, and we'll see some of that in a video in a little bit. But for right now, we've got this very localized fire involving a fuel package. The characteristics of this fire now and where it's going to go, how fast it's going to spread, what it's producing, very much dominated by the fuel that's present in the space. So what is the fuel in terms of chemistry? How is it configured? Where is it in the room? All makes a difference. As the fire burns a little bit, we didn't see so much in the previous photo. You see a little bit of this smoke column or a fire plume here, smoke plume, but it's not real obvious at this stage. But you get that certainly in very early on after the fire and flames become sustained. So we get the fire plume, and this is a buoyant column of flame and hot combustion products that are rising above the fuel, as you see here. And that's all from the process. It's buoyant and it's rising because it's hot. This plume is a very important item now in the early stages of the fire, especially because that plume ends up being a transport mechanism. So it's taking all the combustion products from down near the fire origin and taking them into the upper portion of the room. So as this plume reaches the ceiling and hits a hard surface, it can't go up any farther. So now the smoke starts to spread out laterally. And in the initial phases, it spreads out in a fairly thin layer of smoke, and that gets called a ceiling jet. The ceiling jet is also a transport mechanism, and as it's now taking this smoke from right above the fire and traveling laterally along the underside of the ceiling. And that's very important to us in fire protection engineering, because it's that horizontal transport here to the vicinity of where a smoke detector might be or a sprinkler might be. So it's taking the combustion products and now submerging these protection equipment, these types of protection equipment, inside the smoke layer. And it's this sealing jet that our detectors will respond to, our sprinklers will respond to, at least that would be our hope, in a timely response or indication of the presence of a fire. So as the sealing jet travels and eventually reaches walls, again another solid barrier, now the room will start to fill. So we create this smoke layer that now fills the upper part of the room, and it's again in the upper part of the room. Why? Well, because we're dealing with hot gases, buoyant gases, they want to rise. So we end up with this filling process, and very similar in principle to the filling process of a bathtub or a sink. It's just upside down. This smoke layer will be hot. So in addition to filling up the upper portion of the room, it's also going to be warm, maybe just outright hot. So that there's the possibility of now radiating energy back down on other fuel objects in the space and starting to preheat them so that they rise up close to their ignition temperature. That gets us into the process of now multiple items that ignite in the room, in addition to whatever radiation heat transfer is coming from the flames directly. As we approach that transition point that I referred to as flashover, these are some of the indicators of that as to what occurs very near the onset of that full room involvement. The temperature in the upper part of the room, that smoke layer temperature I talked about, will exceed 540 or so degrees C, and that's not a hard limit, of course. So it's somewhere in the neighborhood of 500 to 600 degrees is when that is the heat or the temperature rather associated with that smoke layer that's going to cause a radiation down onto other objects in the room and heat them up to their close to their ignition temperature. We're going to get a heat flux at floor level, again, from the radiant energy coming from that smoke layer of about 20 kilowatts a square meter. And that's the radiant energy typically associated with spontaneous ignition of ordinary combustibles, woods, polymers, textiles. The oxygen level right after flashover is going to go way down as a result of the sudden increase in the amount of burning in the room from a single object or a couple objects to now where essentially everything in the room is going to be involved in flame. And that as a result of that increased burning and increased desire or need for oxygen, the oxygen level in the room is going to drop very, very quickly to just a few percent. We're going to get a steep pressure rise as a result of, again, all this burning and the expansion of gases, the sudden increase in temperature. And now there's going to be this significant increase in pressure inside the room. And why that's important is because now we're going to get a lot of smoke and flame that's going to be projected out of the room. There's now an increase in pressure in the room that's going to cause a driving force to get the combustion products leaving the room of origin, where there's not so much of that going on early on because there's not a pressure development or a heavy, significant pressure development. And now it's there in a very, very significant way. Because of the reduction in oxygen concentration, now we're typically in an underventilated situation. There's not enough oxygen to burn everything completely. And as a result, where we had enough oxygen before to generate a lot of carbon dioxide, the extra oxygen's not there. And we end up with a lot of incomplete combustion now going on. So there's a very steep rise in CO production. When you look at this overall picture here, one of the very significant things about flashover, in addition just to the dramatic and fairly noteworthy increase in fire development and in temperatures and so on, but very important in terms of fire protection strategy here, in that once you get flashover in the room, there's no life safety in the room of origin anymore because of the high temperatures, because of the heat flux levels. Even if somebody's lying on the floor and under the smoke layer, the heat flux is going to be unbearable, about 10 times what it takes to create a skin burn. The oxygen level is well below anything that can sustain life, so that life safety in the room of origin basically goes away, and our attention, fire protection-wise, is now for life safety for people outside the room of origin, where now they're going to start seeing smoke, being exposed to smoke, combustion products, and possible fire spread as a result of the driving force of that fire outside the room of origin. Also noteworthy just in terms of structural response. Until the temperatures get up near 500 degrees C, there aren't many structural materials that are going to be seriously impacted, or at least steel and concrete are really going to be only nominally affected. Timber will be igniting by this point, or charring at least. So if it's a wood frame structure, there's some involvement there. But largely our structural fire protection issues are not being challenged really or significantly until we get flashover into space. There is an estimating procedure by which we can get a feeling for, so is flashover likely in a particular room or not? And there are several ways to estimate that, including some fairly complex computer models, but there's a fairly simple way that we can use or can talk about for our little intro course here. And that was developed by 3 researchers at the National Institute of Standards and Technology back in the 80s. That's Bernie McCaffrey, Jim Quinteri, who is a recently retired faculty member from Maryland, and then Margaret Harkleroad. They developed this correlation that was based on some theoretical analysis, but mostly was then calibrated, if you will, with the experimental data that was used to determine the constants and confirm the theory actually held in real life. The experimental basis of this MQH correlation, as it's called in the initials of the 3 developers of this, were these. So it's limited, as are many of our simple methods in engineering, so it has its limitations, involving fairly small compartments, relatively low height compartments, not incendiary sort of fires or explosive fires. And you can see, so near cubic spaces, not severely ventilation limited to the point that the fire is now choked and starts to smolder because there isn't enough oxygen being supplied. And the fire is near the middle of the room, so it wasn't involving the wall linings and these type of things. Here's the correlation that they developed. They estimate the temperature rise based on the rate of heat release, the ventilation to the room, so the area of the door, for example, and the height of the door, a heat transfer parameter, or the H sub k, which is essentially the ratio of the thermal conductivity to the thickness of the enclosure materials, and then the total surface area of the space, A sub t. We can do a little algebra on that to say, so what's and solve for QF, Q dot F, that would give us an estimate then of what's the minimum heat release rate needed to drive a room to flashover, assuming that flashover is with a delta T of 600 C. So a little different than number than I proposed back a couple slides ago, but the time difference, the heat release rate difference between a temperature rise of 600 C and 540 C is really pretty minimal in many respects, and certainly for our simple method makes no significant difference at all. So we can ask the question, how big of a fire is needed to cause flashover into space, where we've solved this equation with a delta T of 600. The room size, let's pick an example and demonstrate the use of the method. So we'll pick a room size at 3 by 5 by 3. So a nice cube or a rectangular room. Doesn't have to be a cube. It should be a rectangular solid. Low height space is okay. The ventilation is by an open door. I give you the dimensions for that of the 0.9 by 2.1. So a fairly typical sized door is the hope. And then 13 millimeter thick gypsum wallboard. Right. I gave you the thermal conductivity of gypsum wallboard as an example on the previous slide, and this shows the substitution of all the numbers that are given in the example provided above in those 3 bullets. The 78 is the total internal surface area of all the walls, so the 4 walls, the ceiling, and the floor. And as you work through that bit of geometry, you should be able to get 78 square meters. I've included the area of the doorway as part of that 78. I guess to be perfectly pure, we should subtract that. But given the accuracy that any of this is dependent on, that little detail is really unnecessary to cover. We get a heat release rate of 1370 kilowatts that would be necessary to drive that particular room to flashover. That's the heat release rate associated with a comfortable stuffed chair, as we saw in the previous module, that a stuffed chair gets to 1370. A sofa would certainly get to this heat release rate, or we typically get to that heat release rate, as a couple of examples of how big of a fire that is. After flashover, there is nominally a constant burning rate that will be observed, and that this is largely going to become a constant because there's just so much airflow that's coming into the room. This open doorway is the only ventilation available for this fire in this what was a simulated family room fire, and you could see that through the clear part of the lower part of the door, that's where the air is going in to support the combustion process of this fire. The fire becomes air regulated, so there's just so much burning that can go on, and that gets us to a constant burning rate then, essentially until the fuel is consumed. The heat flux in the post-flashover stage, you see, is much greater than we saw in the pre-flashover stages. So at ceiling level, 100 kilowatts a square meter is a very significant heat flux now being transferred to the ceiling assembly. That's a very significant. If it's a combustible ceiling, that's that's appreciably greater than any minimum needed to provide spontaneous combustion of a ceiling. That's why combustible ceilings are such an issue. At floor level, there is again a very significant heat flux at floor level. Again, well beyond anything that's survivable, more than enough to ignite typical carpeting and flooring materials. The temperature at this stage inside the room, the smoke temperature is in the range of 800 to 1100 C, depending on the characteristics of the space based on heat, height, and area of the ventilation openings principally. Again, talking about, so how much ventilation does this fire have? You see here's a doorway. And also heat losses to the enclosure. The better insulated that enclosure is, the more temperature development we get inside the room. Let's take a look at a video that will hopefully demonstrate the issues and reinforce the issues that we just talked about. So this is a simulated family room or living room fire that an experiment that was done at the National Institute of Standards and Technology, about a 40-minute drive from where I stand here to do this taping. The furniture is all typical furniture that was acquired at a secondhand shop. See the curtains, and so actual real materials as they are, so not any special materials fire retardant wise. We're 30 seconds into this fire now. As you can see, it's still a fairly small fire, limited basically to the cushion. Start to see a bit of a visible smoke plume now rising to the upper part of the space, and that's been there a little bit now. But you do certainly see the visible plume and a little bit of smoke. You can see certainly some smoke coming across the ceiling that would be part of that ceiling jet that I talked about. We're a minute into this fire and still not a terribly threatening fire in a lot of respects. Probably a little bit beyond the ability of someone to just throw a glass of water at and do much with, but is not posing a huge hazard. There would be detectors going off certainly at this point, I would say, and perhaps a residential sprinkler even at this point. Again, fire still limited, now a minute and a half in, still limited to that portion of the cushion of the sofa. And part of what I want you to take a look at is how dynamic, how transient this fire development is, as things are going to start to evolve here fairly quickly now. We get to see a smoke layer here now at probably about head height or so in this space, a very dark smoke layer. And again, that's going to be hot, so it's going to start radiating down on this other sofa sitting nearby. 2 minutes in, as we get low and get under that smoke, we could probably survive that, but it's starting to get to be a bit serious. Keeping in mind that all this smoke that's in here, some of this would probably be going out from under the top of the doorway and starting to spread to other parts of the room. We're 2.5 minutes in. The smoke layer is just above the top. We see that part of the lamp is ignited. The shade has dropped away. We'll see this chair, or rather this sofa, ignite here soon. You start to see the gases coming off of it, so it's starting to be heated up, and we're starting to get some thermal decomposition and fuel vapors coming off there. And we're at the 3-minute mark at this point in this fire. Now we've got ignition of this other object. Very rapid flame spread on there. Again, it's a very hot smoke layer. Keep in mind, very, very hot smoke layer. And we're very near flashover. Flames are coming out the doorway at this point. The carpet's ignited, and essentially we've got everything burning in the space at this stage. So that was at just a little bit over 3 minutes. So we went from a minute, remember, we're about a minute, and well, it wasn't too threatening really to someone who was alert and awake and able to self-evacuate. That you could have easily gotten away from that fire. But in 2 minutes' time, the situation changes dramatically to the point that now anyone left in that room is not going to survive this incident, but more than likely, unless immediately rescued and receiving medical care. But the other noteworthy point is now we've got flames projecting out of that room, and that's spreading to the other parts of the home now at this stage, or the other parts of the building perhaps, if this was some light hazard, a lounge in a light hazard occupancy. The discussion topic for the week is this. So I want you to refer to the video that we just saw and identify the time after flame ignition when each of the following becomes evident. And I want you to try and identify that first time, right? I noted some times where we see this now, we see that, but that was not necessarily the first indication of that. So I want you to get the first indication when you first see a visible fire plume, you first see a smoke layer form. So that's beyond that ceiling jet side. When do you get a little bit beyond that to where there's a definable layer? And then when do you note flashover? And that's defined typically when other items in the room ignite. Right? Though the other telltale of that is once flames come out the doorway, that's an indication that there isn't sufficient oxygen in the room anymore, and the room's now gotten the fire's now gotten air regulated. To the point that we probably have reached flashover also as a result of flames coming out the door. So the other piece that I want you to do for this discussion paper is exercise that equation, that MQH equation that I showed you. And basically, we did an example for a room that was 3 by 5 by 3. I want you to take that same room and explore what's the effect of room size as one possible examination. So I want you to look at what is the heat release rate, right? Heat release rate needed for flashover. If the room is a little bigger, that it's now 4 by 6 by 3 instead of 3 by 5 by 3. You should, I would think, have some intuition as to a bigger room, and does that require a bigger fire or a smaller fire? So as you get an answer for that heat release rate, you should be able to look at that answer to say, does that make sense to me? Right? Just based on a little intuition, would you expect a very small room to lead to flashover more quickly, or a huge room? And I'm going to just leave it at that and expect that you might have some expectation for that. Is it easier to flash over a closet or a huge arena, for example? Right. So think about that. And you should have some expectation then as to the validity of your answer, at least if your answer is in the right trend. And with that, we will close this particular week's discussion in the 4 segments. In this last segment, we talked about the stages of fire development. We talked about these stages being dictated principally by physical processes, by thermodynamics and heat transfer and fluid mechanics. And otherwise, point out what you saw in the video, that the early stages of fire development are very, very transient in nature. And I can't emphasize that enough to lay people, to folks that are not fire protection engineers. They are routinely extremely surprised at the speed at which these fires develop. And I have to say that's an item that as I do experiments in room fires, it's something that I get surprised by as well. As you watch some fire and you start thinking, is anything going to happen here, and so on, and then things take off, and it's astounding to see that, even as you see it perhaps many times running experiments. So with that, we'll bring this to a close, and look forward to talking with you next week.
Hello, my name is Chris Jelenowitz, and I am the Engineering Program Manager with the Society of Fire Protection Engineers. And today I'll be talking about the profession of fire protection engineering. Specifically, I'm going to talk about why fire is a noteworthy problem. And actually, it's a much bigger problem than you probably even thought. And second, I'm going to talk about how fire protection engineers design ways to protect people, property, and our environment from fire. During this presentation, fire departments across the United States of America will respond to about 12 structural fires. That's 12 legitimate fires where a building is on fire. We're not talking about false alarms where somebody pulled a fire alarm and tried to run out of the building. These are your homes, the place where you send your kids to school, or maybe where you work. And unfortunately, during our lifetime, we will always have fires, no matter how hard we try to prevent these fires. And it's the fire protection engineers' mission, or their number one goal, is to make sure that when there is a fire, you get out alive and you're not injured. And their secondary goal is to ensure that damage to property and the environment is minimized. So, what is a fire protection engineer? Well, fire protection engineers use science and technology to make our world safe from fire. The important parts of this definition is that we use science and technology. These are the things you learn in physics, chemistry, mathematics, thermodynamics, fluid mechanics. We take these theories of science and adapt them to practice and find new technologies so that when a fire occurs, people will be protected. So, you ask, why do we need fire protection engineers? Well, first of all, each year in the United States, about 3,000 people will die as a result of fire. An interesting fact about this statistic is that about 80% of these fire deaths occur in our home. And the home is the one place where people feel the safest from fire. Additionally, thousands of people every year are injured as a result of fire. And a lot of times, these injuries are very bad, where people will spend lots of time in a hospital or a lot of times in a burn ward. Additionally, about 100 of our nation's firefighters will die in the line of duty. They die responding to the fire, they respond operating at the fire, coming home from a fire, or training for these fires. And that's why fire protection engineers are important, to protect people from fire. And once every several years, we see a catastrophic fire. When we're talking about a catastrophic fire, we're talking about fires where many people die, or a lot of firefighters die as a result of the fire. The one catastrophic fire I'm going to talk about today occurred on February 20th, 2003, in a little town of West Warwick, Rhode Island, at the Station nightclub. At the night of this fire, over 400 people came to see an 80s revival band called Great White. Unfortunately, 100 people died in this fire. 100 people did not make it home that night as a result of the fire you're about to see. When I show this video, you're going to see in the background some indoor pyrotechnics. These indoor pyrotechnics, called gerbs, which are high-octane sparklers basically, ignited some flammable wall finish. Once the flammable wall finish was ignited, you'll see a very fast-moving fire. The fire moved so fast that 100 people could not get out alive. And if you look, when the camera turns back to the band, you will see the flames starting on that wall finish. Now, it's fires like these that really could tear apart communities. Everybody in that community knew somebody died that day, whether it was their mothers, their fathers, their sons, their daughters, their friends, their cousins, the people they work with died in this fire. And then additionally, because there were so many people that died that night, people started to place blame. Was it the building's owner? Was he responsible for this fire? Was it the band that decided to ignite those indoor pyrotechnics? Or was it the fire marshal that was out, who was asked to come out and inspect this building and make sure the building was safe from fire? An interesting note about this fire: fire protection engineers from the National Institute of Standards and Technology were asked to investigate this fire. They used the most complicated computer fire models. They went into a laboratory and recreated parts of this building and did fire tests to see how this fire burned. And what they found out was that if proper fire protection existed in this building at the time of the fire, nobody would die. Specifically, they said if an automatic sprinkler system was installed in this building, a simple system is an automatic sprinkler system, there would have been 0 deaths. Additionally, there are other costs of fire. For example, every year about $11 billion in property damage results from fire. Another thing that a lot of people don't think about is business interruption. Can you imagine coming to work someday and the building you work in burnt down to the ground from a fire? That was the case on February 23rd, 1991, at One Meridian Plaza, a high-rise fire in the middle of downtown Philadelphia. 1991, we have a high-rise fire that is so bad, the building was damaged so bad that they had to demolish a high-rise building in the middle of downtown Philadelphia. Unfortunately, 3 firefighters also died in this building. They were operating on one of the upper floors. They ran out of air. They tried to tell the command center that they were lost, that they ran out of air, but unfortunately they told them the wrong location. And unfortunately, 3 firefighters died that night. So how do fire protection engineers make us safe from fire? Well, first of all, they design safer buildings. When we design buildings, we have what we call a project team. We have architects, we have engineers, we have electrical engineers, mechanical engineers. A fire protection engineer is just another person on that design team that works to make sure that all the things in the building are safe so that people get out alive. Additionally, fire protection engineers review design documents. They work for a governmental agency, fire marshal's office, code enforcement office, where they review the design documents to make sure that they comply with the codes and standards that exist in their jurisdiction. Additionally, fire protection engineers evaluate structures to pinpoint risks. Many large corporations have fire protection engineers on their staff, and their job is to go out to their facilities, like this oil rig right here, and make sure that if there is a fire hazard, they find ways to correct it so that fires like this don't happen. Large hotel chains have fire protection engineers on our staff. Can you imagine how bad that would be for business? If somebody died in their hotel, they hire these fire protection engineers, and the owners know that they could go to sleep at night knowing that nobody's going to die in their hotel that night. Additionally, fire protection engineers do fire research. They get to burn things. It sounds like a lot of fun, but we're burning things for a purpose. We're burning things so we could have better, safer building materials. We burn things so that we could find better systems that will detect fires quicker or extinguish fires even faster. Fire protection engineers also investigate fires. As you see in this photo here, here are some fire protection engineers from the Bureau of Alcohol, Tobacco, and Firearms. They are rooting through the rubble after an explosion that occurred in the state of Texas. In this capacity, fire protection engineers try to find out, why did this fire start? What happened? Why was the damage so bad? What measures failed? And how do we make things better so the next time we build a building or renovate a building, that these type of emergencies or these types of incidents will never happen again? So how do we make buildings safe from fire? The next couple of slides are going to talk about how a fire protection engineer thinks through the process of making a building safe from fire. First of all, they analyze how a building is used. What is inside that building? What are people doing? So for example, this high-rise building here in Tokyo, we would definitely design that differently than we would this museum that's in Ottawa, Canada. Or in the soccer stadium above, we have a lot of people in this building. Well, when we have that many people and such a high population density, there are different things a fire protection engineer will look at. And finally, up here is a historic building in Ghent, Belgium. When we look at these types of buildings, we might design that a little differently than a new building because we want to make sure that we could preserve the historic fabric of the building, but at the same time, making sure the building is safe. After we know how the building is used, we analyze how fires start and grow. How a fire will travel through a building if there is a fire. Where will the smoke go? In this picture here, we have some fire protection engineers working with the New York City Fire Department and trying to find ways to better protect buildings that are subject to high winds. Up here, you see that there's a fan here, and this is really trying to show the same situation that we would see with a high wind condition in a building. So once we know how a fire is going to spread, smoke's going to spread through the building, we ask, how will that fire affect people? When will conditions become so bad in that building, no one will survive? Or we ask, how will people react to this fire? If they smell smoke, will they eventually evacuate the building? Will they go back to get their belongings? Will the people in this building even have the capacity to evacuate on their own? After that, they design systems that control the fire. These are systems like fire sprinkler systems, or there are situations where water cannot control a fire, where we use gases and design special hazard systems that will control and eventually extinguish a fire. We also design systems that alert people to danger. These are your fire alarm systems that provide an early warning that a fire has occurred. These systems also provide information that tell you what the problem is, what you need to do to get out safely. Fire protection engineers also design the means of escape or the exits from a building. In this picture here, you see a stairway. And one thing fire protection engineers will look at is how wide is that stairway? Is that stairway wide enough to get everybody out of the building safely? And we're not only talking about people leaving the building, what you'll see here, but do we also have enough width of this stair so that firefighters could also go up the stairs and do their job of extinguishing the fire? And finally, fire protection engineers protect the structure. They make sure that fireproofing is available and measures are available so that when the critical building components are exposed to fire, that these building components will hold up the building and we will not have a building collapse. Fire protection engineers, where do they work? About 53% of them work in consulting firms where they design buildings to make them safe from fire. About 25% work for local governments where they're reviewing drawings, making sure government buildings in the cities, the buildings in their jurisdictions are safe. They also work for education, insurance, and contractors. So to sum up things, fire protection engineering. Well, first of all, fire is a noteworthy problem. Each year in the United States, 3,000 people die as a result of fire. It's the fire protection engineer that uses science and technology to make our world safe from fire. And fire protection engineers design ways to protect people, property, and the environment from fire. Hello, my name is Chris Jelenowitz. I am the Engineering Program Manager with the Society of Fire Protection Engineers, also known as SFPE. I'm also a licensed fire protection engineer. And in this segment, we're going to discuss the history of fire protection engineering. And specifically, we're going to talk about how the profession of fire protection engineering has evolved. It evolved from ancient times when some city planners kind of thought about what are some common sense things we could use or do to prevent a city, an entire city from burning down, to where we are today, where we are using very sophisticated computer fire models and very sophisticated technologies to alert and people about fire and control fires. So before we even had fire protection engineers. Actually, fire protection engineering was actually practiced by city planners and people who run the government. Basically, the first issue with fire was that we were burning down entire cities. So, for example, the city of Rome, back at 64 AD, had a fire that completely destroyed the entire city, just about. There's old folklore that the Emperor Nero sat there and played the fiddle while the city burned. That's where we came up with the idea or the concept of fiddling while Rome burns. There was also a huge fire in 1666 in the city of London, and probably one of the most popular fires or most notable fires came in 1871, which we see in the picture behind me. That's a picture of the city of Chicago, or the Great Chicago Fire, and the idea that Mrs. O'Leary cow started a fire that destroyed a whole entire city. Well, after these cities burned, city planners thought, well, what can we do so that never happens again? Well, they thought of ideas like, well, instead of building our structures out of wood, let's build them out of non-combustible materials. Also, we were noticing that when there was a fire, the fire in one building would cross an entire street and expose another building to fire. So the city planners thought about widening the streets. They also said we need water to extinguish a fire. How do we get water into the hands of the people who are fighting these fires quicker? So this lasted up into the late 1800s, early 1900s. We kind of got a good feeling, hey, when we have a fire now, we're not burning down the whole city. However, we are seeing that entire buildings are burning down. In the late 1800s, going into the 1900s, in New England and other places in the East Coast, some giant factories were burning to the ground. The picture here is the Crystal Palace, which burned down in 1858. That was in Manhattan or New York City at the location where Bryant Park is right now. And when they built the Crystal Palace, the designer said, hey, we're going to design a fireproof building. We're going to build a building out of steel or concrete or products that do not burn. And as a result, these buildings will not burn to the ground. Unfortunately, their logic was a little flawed. The one thing they didn't think about was, even though the building is non-combustible, the things inside your building are combustible. These things will burn, and they will be responsible for spreading fire throughout a building so bad that it will burn down an entire building. So what did we do? First, the fire protection community said, hey, let's put up these things called firewalls. These are walls that we put in the building, and then when a fire starts, the fire will not spread from one side of the building to the other. So we're using the idea of compartmentation, compartmentalizing the building. So when there's a fire, it will remain in that part of the building. Therefore, the entire building will not burn down. Additionally, we saw the first automatic fire sprinkler systems. The idea of putting pipes through a building, attaching nozzles in them that spray water onto a fire when there is a fire. These systems would eventually control a fire and then extinguish the fire. So we got pretty good about protecting buildings from burning to the ground. And then what we saw throughout the 1900s is a series of catastrophic fires. We're talking about catastrophic fires. We're talking about fires where many people died, sometimes in the hundreds. The first fire to talk about occurred in 1911 at the Triangle Shirtwaist Factory. In this fire, 146 people died. Most of them were young teenage girls who were forced to work in a sweatshop. In 1911, sweatshops were very common. They had very poor working conditions. People were asked to work long hours almost every day, and they were death traps. When the fire occurred at the Triangle Shirtwaist Factory, there were 3 exits for people to exit the building if there was a fire. One of the exits was locked. Now, in 1911, it wasn't uncommon that we locked the exit doors in these sweatshops because the owners did not want people to go on breaks. They were concerned about people leaving the job early. So we locked them inside the building. Imagine that. The second exit was a stairway. The door of that stairway swung against the direction of exit travel. So when people tried to enter that stairway, the door kept getting in their way, and it slowed the time for people to exit the building. If you ever see an exit stairwell today, you will see that the door swings into the stairwell, going the same direction that we travel, so the door will not block people that are trying to egress. The third exit was a very poorly designed fire escape. Not too many people were able to exit. When this fire occurred, it sent a message to the whole fire safety community that we have to do a better job. It sent a whole message to our government policymakers saying that these sweatshops are death traps and we need to fix them. So the one thing we did is we designed our codes appropriately. We said that no longer can you lock exit doors. If we have an exit stair, the door going into that stair should swing in the direction of exit travel so that when people are in a fire, they could get out safely. Unfortunately, a fire in 1946 at Atlanta's Hotel Weinkauf left 119 people dead. And once again, it was our younger population. Atlanta being the capital of Georgia, on the night of the fire, that day they were holding a mock Congress or a mock legislature where they invited high school kids from every legislative district in Georgia to come and pretend like they were a part of the lawmaking process in Georgia. Well, most of those students were staying at the Hotel Weinkauf that night. What happened there was a fire started at the lower part of the building. And in this building was one large open staircase, the only way to get out of the building. The fire started at the bottom of the stair. The hot fire and gases extended through this stair like a chimney. As a result, the poor kids that were on upper floors had no way to exit the building. They either had to die inside that building and die in the fire or jump out the window to their deaths, like this poor person here. The interesting thing about this photo, it was taken by an amateur photographer. The next day, that photo was on every newspaper in the world almost. And this is the first time that an amateur photographer has received a Pulitzer Prize for photography. As a result of this fire, the fire protection community got together and said, hey, we have to do something about exit stairs and make sure that we don't have fires that extend from the bottom of the building all the way up to the top. We have to make sure that there's more than one way to get out of a building when there's a fire. Another fire occurred in 1958 at Our Lady of Angels School, which was a grade school in Chicago. An interesting point about this fire was that the principal had a rule. She said, if there's a fire in the building, we have to get the principal's permission before we activate the fire alarm. Well, when the fire happened that day, 92 people died, most of them young kids. And they all died. One main reason they died is they didn't get adequate notification to tell them that there was a problem in the building. Additionally, there was a delay in notifying the fire department. As a result of this fire, the fire protection community got together and said, hey, when there is a fire, we have to make sure we get the information to people out as soon as possible. We also have to get quick notification to the fire department, because the quicker the fire department comes, the better chances are people will survive. In 1977, there was also a fire at the Beverly Hills Supper Club. The Beverly Hills Supper Club was not in Beverly Hills, California, but in Kentucky, in a suburb right out Cincinnati. When they built the Beverly Hills Supper Club, this was one of the ritziest, glamorous nightclubs in the whole United States. The best people came to this nightclub. On the night in 1977, John Davidson was performing. Unfortunately, that night, 165 people died. The main reason they died was a fire burned out of control away from the main audience. The people did not know a fire was occurring in the building. By the time they knew it was time to exit, it was too late. Some people died in the exact chairs they were sitting in. When they interviewed the survivors, they said, hey, what happened in there? How did you get out alive? A lot of people said, hey, the building staff really helped us out. It was the building staff that ran through the hallways and ran into the club and said there's a fire. It was the building staff that showed people how to get out of the building. And that's where we come from, the idea of emergency planning and making sure we train building staff appropriately. Because we see when people enter buildings, especially public buildings or buildings they're unfamiliar with, they don't really take a lot of action when there is an emergency. They rely on the staff. Also, the people said, hey, we were in such a glitzy, great nightclub, we never thought that something like this could even occur. But unfortunately, 165 people died that day. Another interesting fire occurred in 1980 at the MGM Grand Hotel, right on the Las Vegas Strip. 84 people died that day. The fire started in the casino right here. The interesting thing about this fire was that the codes at the time in Las Vegas, if you had a fire suppression system, like a sprinkler system, you were not required to protect the areas that are not occupied. If an area was occupied for more than 24 hours, or for 24 hours, you did not have to have protection in that part of the building. In the casino, they said that's going to be occupied 24 hours. There was an adjacent deli. That part of the building also would be occupied 24 hours a day. Unfortunately, they changed that plan. A fire started in the deli, quickly spread to the casino. Most of this casino was on fire. The adjacent hotel right here, none of the fire spread to the hotel. However, the smoke and the toxic gases did. And this is where most of the people died. The smoke and the toxic gases traveled through shaftways, expansion joints. As we can see here, a lot of people were forced to the balconies, where that was their only hope, to seek an area of refuge on the balcony and hope that either the fire would be extinguished or the firefighters would come to rescue them. The World Trade Center, I think everybody knows what happened on that day, on September 11th. The one thing you might not know is that the fire protection community worked hard to investigate this incident and find out what happened. This is probably the largest investigation in the history of the world. I'm sure over 100 fire protection engineers looked at everything from why did the structure fail? How did the fire spread through the building? What about the fire suppression systems or the fire systems that were in the building at the time of the fire? They also talked to the survivors. They asked them, hey, what were you doing when you noticed something was wrong? What made you decide to get out, to leave the building? How did you leave? They took all this information and developed ways to make sure that today taller buildings are safer because of the investigation that occurred after this incident. And today I would say we're in the era of what we call performance-based fire protection. Over the last 100 years, fire protection was basically revolved around the codes and the standards. The codes say you do this for this type of occupancy. If you're designing a hotel, you need to do that. If you're designing a school, you need to do A, B, C, and D. However, with modern technologies, buildings are becoming much larger. They're having unusual shapes. They're becoming much taller. Like you see right here in the Venetian Hotel, we're taking buildings and we're making the inside look like the outside. And because of this, a lot of these building designs are not fitting within our own prescriptive codes. So what we're seeing in the future is that fire protection engineers, instead of looking at a code book and deciding how we provide fire protection, we're really taking all the great tools we have today, advanced computer modeling, advanced technologies in notification and suppression, and we're putting them into the building based on the performance, based on fire safety goals, where we always say our number one goal is to make sure that everybody will get out alive. And finally, any discussion about fire protection or fire protection engineering should resolve around Dr. John L. Bryan. Dr. Bryan started the fire protection engineering program here at the University of Maryland. He was the chair of the department, and there's a scholarship named after his wife, the Sarah Bryan Scholarship. If it wasn't for people like John Bryan, we wouldn't all be here today. So to sum things up, fire protection engineering has evolved. We started with protecting entire cities from burning down to the ground. Once we got a good idea of making sure that cities weren't burning, we looked at protecting individual buildings. Once we figured that problem out, we looked at catastrophes or catastrophic fires and said, how do we adopt those codes so these types of incidents never happen again? We are now at the point where we're using advanced engineering tools. And finally, our designs are coming more performance-based, based on fire safety goals that will ensure that people, property, and the environment are protected from fire. Hi, my name is Chris Jelenowitz. I'm the engineering program manager with the Society of Fire Protection Engineers. I'm also a licensed fire protection engineer. And today I'm going to talk about why fire protection engineering is a rewarding and exciting profession. It's a profession that you should tell your friends about. It's a profession, if you don't know where you're going in life, it's something you should think about. During this presentation, I'm going to discuss how demand for fire protection engineers is very high and that fire protection engineers have a lot of job opportunities. I'm going to talk about why people find fire protection engineering rewarding based on the fact that they're protecting people from fire. Knowing that they're making a difference is an important thing of why people become fire protection engineers. I'm also going to tell you how fire protection engineers make a great salary and work on interesting projects. So I found this quote from Steve Jobs, and I found it really interesting how it's really how I feel about the profession of fire protection engineering. And that quote is, do you want to spend the rest of your life selling sugar water, or do you want to have a chance to change the world? And if you want a chance to change the world, fire protection engineering is definitely a profession for you. Knowing that every day that you go to work, that you're preventing catastrophic fires, that you're preventing people from going to the hospital and have to spend excruciating time in burn centers. These are the things that are very fulfilling to the fire protection engineer. Now, one important thing about the profession or fire protection engineering is that the demand for fire protection engineers exceeds the supply. And what I'm saying here is that employers find it very difficult to find fire protection engineers because there's just not enough of them out there. So it's great knowing that if you graduate with a degree in fire protection engineer, that there's going to be a great job waiting for you. Also, it's good to know that if you work for an organization and say maybe that company had to close down for some reason, that most likely it won't take you too long to find a job. So you ask, how do we know the demand exceeds the supply? Well, first of all, the colleges that offer fire protection engineering programs tell us that their graduates rarely have a tough time finding employment after graduation. Here's a quote from Jim Milkey, who is the chair of the Department of Fire Protection Engineering here at the University of Maryland. Dr. Milkey tells us that the market for students graduating with a Bachelor's of Science degree in fire protection engineering is very strong. Many of our graduates this semester received multiple offers. Imagine that. In today's economy, we're seeing students getting multiple job offers. What a great feeling if you're a parent and you're spending tons of money to send your son or daughter to school knowing that they're going to have a job. What a great feeling knowing that when you work hard in college, you work hard to get that engineering degree, you're going to have a job. We also know that there's a demand for fire protection engineers when we talk to the people that employ them. When we ask employers, are you having difficulty finding fire protection engineers to fill all your positions? This is what Ray Grill tells us. Ray is a fire protection engineer with Arup. Arup is one of the largest design firms in the whole world. And what Ray tells us is that the demand for fire protection engineers continues to outpace the supply. This imbalance in demand makes it very challenging for recruiters to recruit qualified engineers. Also, as a fire protection engineer, you could command a decent salary. It's always nice to be in a profession where you're paid well. Every 2 years, the Society of Fire Protection Engineers surveys their membership, and they ask them about their compensation. How much do you make? How much do you make at bonuses? What kind of benefits do you receive? And what we find is that the median total compensation for fire protection engineers in the United States is around $113,000. That's a great solid employment, a great salary for anybody. Not only are experienced fire protection engineers making a good salary, people coming out of college are getting great salaries. Entry level, which we call for anywhere from 0 to 5 years, the median salary is about $70,000. It's not uncommon to see a graduate with a Bachelor's of Science degree in fire protection engineering to get an offer between $60,000 and $70,000. Another great thing about fire protection engineering, you get to work on a lot of interesting projects. So for example, one day you could be designing one of the biggest high-rise, tallest buildings in the world. The next day you could be in a lab where you're testing some new type of building material to see how it burns, or see how, if that material burns, how will that affect people in a fire. And lastly, we're using some of the newest technologies to model fires, similar to the way we see weather models predict how a hurricane is going to strike a city or a town or a region. Fire protection engineers have models that will look at fires and tell us, how will a fire travel through this building? How will the smoke travel through this building? Here's a quote from a guy by the name of Vidar Landa. He is a fire protection engineer out in the Los Angeles area. He comes from Norway. He went to school in Norway, came to the United States, and has a great job as a fire protection engineer. And he says, there are so many different things I do. I'm involved with everything, a huge variety of tasks. I never get stuck behind a desk. A huge variety of tasks. That's something that fire protection engineers always tell us. We always get the opportunity to work on something different almost every day. Whether it's a high-rise building to a new stadium in town, or maybe protecting a museum or an important piece of art. Fire protection engineering also gives you an opportunity if you would like to travel the world. Here is Tony Caro, who is a fire protection engineer with the city of Denver, saying in my first job, I spent my first 5 years traveling internationally, so I got to see a lot of cool places. When you look all around the world, whether it's the Middle East, Asia, Europe, Australia, New Zealand, we see fire protection engineers. So if you would like to see other parts of the world, there are opportunities for you to do that. And I think most importantly, fire protection engineers get a lot of job satisfaction knowing that they're making the world a better place, knowing that they're making a difference, knowing that they're making people safer every day. Stacy Welch, who is a fire protection engineer with the Marriott Corporation. In her job, she makes sure that all the hotels are safe. So if people go to sleep that night at a Marriott hotel, you will get out alive. She says, I feel there's a big reason why I go to work each morning. It gives me an incredible sense of purpose. It's a common theme we see. Teresa Chung, who is also a fire protection engineer in the San Francisco Bay Area, she says that the one thing that pulled me into the field was the human element. Knowing the work that we do impacts life safety and people in a building. Knowing the work we do impacts life safety and people. It's a common theme when we interview fire protection engineers and we say, hey, why do you like working here? It's all about the people. If people are looking for more resources, or you want to see more information about why fire protection engineering is an exciting and rewarding career, the Society has a careers in fire protection engineering website that can be found at careers.sfpe.org. In this website, you'll find a lot of important information. For example, the schools that offer programs in fire protection engineering, We have a full listing of scholarships. The one thing we find is, because a lot of people might not know about our profession or that there are programs in fire protection engineering, that some of the people that sponsor these scholarships tell us the biggest problem they have with the scholarship is it's very difficult for them to find people to apply for these scholarships. So it's great knowing that there's a lot of scholarships out there. There's also information about some of the resources where you want to learn more, and it also has a free membership application for the Society of Fire Protection Engineers. So as a student, you could go to this website and sign up and become a member for free. Additionally, the Society of Fire Protection Engineers sponsors a Careers in Fire Protection Engineering page at Facebook. That could be found at www.facebook.com/careers.sfpe.org. It's just another great forum where we have people that are interested in careers, talking to people who are already in the career, talking to people who are students like the ones out here at the University of Maryland. Have a nice forum to talk about the profession and talk about all the great opportunities that are out there. And we also have a career guide. You can find that electronically at magazine.sfpe.org. Or you could contact the offices at SFPE by going to www.sfpe.org. And this career guide has a lot of information. It interviews 3 recent graduates who have now entered the workforce, telling about their experiences, not only as a student, but as a practicing fire protection engineer. It has some of the salary facts that I discussed earlier today, and a couple other great, interesting stories about why fire protection engineering is a rewarding and exciting profession. So why? Why should we be fire protection engineers? Why is fire protection engineering a rewarding, exciting profession? Well, first of all, demand exceeds supply. Knowing that there are jobs available is certainly a great reason why somebody would want to become a fire protection engineer. You get to work on a lot of cool, exciting projects. Knowing that you have a variety of work, knowing that you have the opportunity to travel the world and go see other places and learn about different cultures and see the different ways that people across the world design buildings is very exciting. You can command a decent salary. Everybody likes getting paid well. A variety of projects and the opportunity to make the world a better place. Not every profession could give you all this. So when you're thinking about fire protection engineer, take a look at this list and take the steps to becoming a fire protection engineer. Hi, my name is Chris Jelenowitz, and I'm the Engineering Program Manager with the Society of Fire Protection Engineers, also known as SFPE. Specifically, I'm going to talk to you about how SFPE is the profession of fire protection engineering. And when we talk about the profession, or what is a profession, there's a couple things to think about. To establish yourself or call yourself a profession, one, you need a way to educate the people in your profession. And here I'm going to talk about how SFPE helps their colleges and our universities develop the curriculum for fire protection engineers. I'm going to talk to you how we educate people who are already out in the workforce and provide them with continuing education that is needed to do their jobs. Also, to be part of a profession, you need to be able to assess competence. How do we determine that somebody has the minimum competence to do the job effectively? In fire protection engineering, assessing competence is very important because everything we do as a fire protection engineer impacts the public's health, safety, and welfare. So making sure that we only allow competent fire protection engineers in the workforce is one of the most important things we do as a profession and one of the most important things we do at SFPE. Additionally, SFPE provides our body of knowledge. I'm going to talk about how we have different guidance documents so that engineers that are practicing could do a better job of practicing in fire protection engineering. And finally, for a profession, we need the support of the community. Not the entire community, but the profession's community. And SFPE, that's what we are. We are a community of fire protection engineers. Our membership represents about over 4,000 fire protection engineers across the globe. We have about 70 chapters throughout the world. And in these local chapters, we really have over 70 different organizations out there that are promoting our profession. 70 locations throughout the world where the people that practice in fire protection engineering can get together every month and talk about issues in their community, common things that they see in their jurisdictions. We also see these chapters going out to the communities and telling the communities about fire safety and how we can make buildings safer from fire. In that list of 70 chapters, we also have student chapters. The colleges and universities that offer programs of fire protection engineering often have these student chapters. It's another community where the students could get together and learn about the profession, learn about job opportunities, learn about new things that are changing. And it's another way that these students could get together and work together. So when they have projects at school, it really is a great forum for them to have a community of fellow students and work together to accomplish their goals and get their degrees. SFPE also supports the body of knowledge in our profession. Most importantly, our body of knowledge can be found in what we call the SFPE Handbook of Fire Protection Engineering. It's now in its 4th edition. And basically what this handbook is a compilation of all the important fire research that has gone on. All the important things you need to know to be a fire protection engineer are in this one place, and that is our body of knowledge. Additionally, when newer concepts come up or things change, SFPE creates design documents for people who are currently practicing in the field today. For example, you see here the SFPE Engineering Guide for Fire Safety in Tall Buildings. A lot of this work came after what happened on 9/11 and the World Trade Center. It really gave the fire protection community a way of looking at tall buildings in a different way. Also, we see around the world that there are a lot of countries that are out there that are building taller buildings every day. So this guidance document really gives the fire protection engineer some information on how to design tall buildings better so that they're safer. We also publish a quarterly magazine called Fire Protection Engineering Magazine. You could get it in a hard copy, or you could see it online at magazine.sfpe.org. And each of our issues really focuses on practical applications of fire protection engineering. We try to look at things that are new, exciting material. For example, we have an issue on sustainable design. We also have an issue here on brush fires. If you read the newspapers or watch your news, you'll see that very large brush fires are coming more and more common every day. We also have a nice issue about colleges and how we protect the kids that go to our college and make the college environment safer from fire. Additionally, SFPE has continuing education opportunities for its membership. Once you get out in the profession, you have your degree and you're practicing as a fire protection engineer, well, there's still new things that go on, changes in technology, changes in the way we design buildings. So SFPE has an annual conference every year where we bring in the top professionals in our society to talk about the latest advancements in fire protection engineering. We also have global conferences, and we also offer specific courses for people who are interested in learning more about fire protection engineering. In addition to continuing education, we also help promote the schools that offer higher education programs in fire protection engineering. For example, the Society of Fire Protection Engineers writes the criteria for programs that have fire protection engineering programs. This criteria is evaluated every 6 years through an organization called ABET. It's the people of SFPE or volunteers from our society that go out to these schools and evaluate these programs to make sure that these higher education programs are meeting the mark and providing a good education so that when people come out of school, they'll have the knowledge and the skills available to them to get out and work as fire protection engineers. Additionally, the society promotes the profession. We talk to newspapers, we talk to trade journals, we go on TV. We like to tell everybody about our exciting profession and why you should go out and be fire protection engineers. But we also like to go out to the community and tell them about how fire is a noteworthy problem and that each year in the United States, 3,000 people die as a result of fire, and how fire can be very dangerous and how quickly a fire could spread through a building, so that people know that if they hear a fire alarm or if they smell smoke in the building, the best thing you should do is get out of the building quickly. We also talk to trade journals in the different types of discipline and tell them about the work we do as fire protection engineers and how fire protection engineers, the work we could do, could complement the work that facility managers are doing, electrical engineers are doing, mechanical engineers, project managers, construction managers, how we can help you do your job better. And finally, one of the most important things we do as a society and as a profession, we assess competence. And we do that through the licensure program for fire protection engineers. One of the major parts of becoming licensed as a fire protection engineer, or being called a professional engineer, or PE, is the fact that you have to take 2 tests. The final test is the professional engineering exam in fire protection engineering. The Society of Fire Protection Engineers, our members, write the questions that are in that exam. We also write the specification of this exam based on what we see fire protection engineers doing in the workforce. So without a doubt, assessing competence and making sure that we have fire protection engineers out in the workforce is an important thing that we do as a profession. So kind of to sum things up, SFPE is our profession. Before you decide to go to college, we're out here telling you about fire protection engineering. We're telling you why fire protection engineering is an exciting career that everybody should get involved in. You find that through our career guide, our websites, our Facebook page. We go out to career fairs and talk to college students, high school students, tell them about our profession. When you get to college, we provide you with guidance documents on how to do some of your coursework. We also promote the establishment of SFPE student chapters. So as a student, you have friends that you could go to. You have a place where we could get all the fire protection engineering students working together on common goals. After you graduate, SFPE is there. We're there. We have a nice mentoring program for people who are newer fire protection engineers. We also do licensure. And licensure is a very important part of the process. So because we write the exam, it's our profession where people need to take this exam to become licensed. Additionally, we provide the body of knowledge you need to do your job. After licensure, we provide continuing education. Because our profession is changing so quickly, you need to have the continuing education to continue your careers. And finally, once you retire, there's still a place for you at SFPE where you can work in our committees and help make our profession even better. Hello, my name is Chris Jelenowitz. I am the Engineering Program Manager with the Society of Fire Protection Engineers. I'm also a licensed fire protection engineer. And in this discussion, we will talk about the licensure program for fire protection engineers. As a fire protection engineer, you have a unique opportunity. For those who practice in the United States, you get the opportunity to become licensed. And when we talk about licensure, we're really talking about establishing competence, determining if you are competent enough to practice as an engineer. Are you competent enough to ensure that when you do engineering, the public's health, safety, and welfare will not be at risk? And at the same time, as a licensed engineer, there are credible opportunities for you personally. You get to put the letters PE next to your name and on your business cards saying, hey, look at me, I'm a professional engineer. You can also command a higher salary and have a lot more job opportunities when you become licensed. As you'll see in this presentation, the important thing about licensing is the moment you enter school or the moment you enter college is the time you really need to start thinking about licensure. So licensure, as I said, is really about establishing competence. The idea came up about 100 years ago where engineers were designing bridges, and some of these bridges were substandard. So the local authorities said, hey, we have to find a way to make our bridges safer. It's not really good if the bridges we design and build are collapsing and people are dying. So they established a licensure program for engineering. Today, every important engineering discipline has a licensure program. Whether it's mechanical engineers, electrical engineers, civil engineers, chemical engineers, and fire protection engineers. They all have a form of determining competence. And they all go by the same guidelines that I'm going to talk to you today. When we talk about establishing competence, it's all about, does the practicing engineer have the knowledge, skills, and experience to do their job? And why we do this, or why do we have a licensure program? It's all about protecting the public. So a lot of people are going to say, what is licensure? Well, basically, it's permission from some sort of government entity giving you permission to practice. Most professions have some sort of licensure program. For example, to be a physician, you have to go out and be licensed. Attorneys become CPAs. Even the guy that used to cut my hair is required to be licensed. When we're talking about engineering in the United States, it's the specific states that grant that license. Each state in the United States and the districts, like the District of Columbia and Puerto Rico, have their own engineering laws. Each state's law is almost the same, but the states like to tinker a little bit to make sure that the licensing laws in their state meet with the public demands. So for example, in the state of Alaska, freezing and cold temperatures are a big factor. So they have a lot more things. Make sure that you understand how cold temperatures impact the systems that engineers design. When the states write these laws, in these laws, they define what is engineering. They'll say designing a bridge is engineering. Designing a fire protection is engineering. And anything we say or we define as engineering must be designed by a licensed engineer. In addition, the states get to decide who is licensed and who is not. The process I will talk about today to become licensed is about the same in each state. Additionally, the states, if they find out that you're incompetent or a poor engineer, or your engineering can conflict with the public safety, health, and welfare, the states also have the right to take that license away from you. Each state has what they call a licensing board. Sometimes they're called the State Board of Engineering. They could be called the Board of Engineering and Architecture, and sometimes they're engineering and surveyors. But each state has a board of people that are usually appointed by the governor, who are engineers who serve on these boards. And also, once you get licensed in one specific state, It's easy to transfer that license to another state by what we call comity licensure, which is basically transferring your license from one state to the next. So as I said before, only a professional engineer or a licensed engineer can practice engineering. So what does that really mean to you? Well, if you want to own your own design firm, you are required to be a PE. If you're doing consulting work or anything that the state defines as engineering, you are required to be a licensed engineer. A lot of times when an engineer does their design, they are given a seal where they seal that drawing. They put that seal on there with their registration number so that when that design goes out to bid or when that design goes out to construction, we know that that design was performed by a licensed engineer. And in many states, to call yourself an engineer or a professional engineer, you are required to be licensed. So what does that mean to me as a practicing fire protection engineer? Or what does that mean to you as somebody who wants to be a fire protection engineer? Well, first of all, it opens many doors. In a stack of resumes, if you're a licensed engineer, yours will stand out. Personally, I did apply for a job one time as a fire protection engineer, and I found out later that a very good friend of mine applied for the same job. We went to school together. He was a very good student. He was a very good engineer. However, he wasn't licensed yet, and I was. I got the job. After about a month or so later, I was talking to my supervisor. He said, hey, you know, because you had that PE, that's how you got the job. Also, as a professional engineer, you get to be part of a large club of people who are licensed engineers. When you walk into the room and you have PE on your business card, other design professionals will look at you differently if you didn't have your PE on your business card. And additionally, as a professional engineer, you could command a higher salary. Every 2 years, the Society of Fire Protection Engineers does a compensation salary with their membership. The last salary was done in the year 2012. And as you can see, somebody who has a PE could command a much better salary. On this chart here, we are looking at full compensation, the median compensation for fire protection engineers. And the median compensation for somebody who holds a PE is about $120,000 a year. For somebody who does not hold a license or who is not a PE, the median salary is about $99,000 a year. So without a doubt, it pays to get on the pathway to licensure and become a licensed professional engineer. So you may ask, how do I get this magical license? What do I need to do? Well, there are basically 3 steps. The first step is education. The first thing you need to do is get a Bachelor's of Science degree in engineering. There is also an experience requirement. Normally, the states require you have 4 years of experience practicing as an engineer. And there's also 2 exams that I'm going to talk about. The first exam being the Fundamentals of Engineering exam, which people usually take in their last year of college. And then the final exam, which is the final part of the process, it's also called the Principles of Practice of Engineering exam, or the PE exam, is a discipline-specific exam. So for fire protection engineers, you will take an exam on the principles of fire protection engineering. Once you complete these 3 steps, you become licensed and you are a PE. So going back to step 1, receive a degree from an engineering program that has an accreditation. ABET is the organization that accredits engineering programs. The Society of Fire Protection Engineers works with ABET to set the criteria that makes a fire protection engineering program different than an engineering program in any other discipline. Once you receive your degree, you could go out and work as an engineer, however, you cannot call yourself licensed. In the year 2020, many of the states are going to change the regulations and not only require that you have an accredited BS degree in engineering, but you will have to have the amount of education that is needed to get a Master's of Science degree in engineering. Specifically, they're not going to require you to have that master's degree. However, they are going to make sure you have at least a bachelor's degree plus about 30 credits, which that usually equals a master's degree, minus some kind of thesis requirement. So in the year 2020, our engineering laws will change significantly. So you will need additional education to become licensed. The second step is experience. Once you get out of school, you have your degree, you could work under the supervision of a professional engineer. However, that requirement depends that you work on with somebody who is also in your same discipline. So if you graduated with a degree in fire protection engineering, you couldn't necessarily go work for an organization that mainly does electrical engineering, where you're designing lights in the building and things like that that are non-fire protection related. You need to go work for a firm that specifically does fire protection engineering work. And during that 4-year period where most states require for experience, you will be supervised by somebody who is a licensed engineer. Now, some states have different requirements. So for the example, the state of California only has a 2-year experience requirement. However, once you get that 2 years experience and you become licensed, you cannot practice in other states unless you get 4 total years. And the third step is all about examination. You're required to pass 2 exams. The first exam you usually take in your last year of college. That exam is called the Fundamentals of Engineering exam, also known as the FE exam. This exam, for the first time in 2014, is offered only in an online electronic format. So if you want to take this test, you have to call up a test center in the area where you would like to take a test, and you go to this test center where you will take this exam on a computer. It's also called a supplied reference exam, where the references that you need to pass the exam are on the computer. So if you need a formula, or you need a chart or a graph, all that information will be provided on the computer that's at the test center. You are not allowed to bring any references into this exam. Now, this exam usually tests the things that you learn in your first 2 years of engineering school. Things like mathematics, statics, dynamics, physics, chemistry, engineering ethics, engineering economics. So it's important that people take that test in their senior year or their last year in college. Pass rates are significantly higher if you take this test as a senior. The farther you get away from college, the chances of you passing this exam decrease significantly. That is, significantly. So if you are an engineering student, the time to take this exam is your senior year. I understand that you're busy. There's a lot of things going on in your final year, but you need to take the time to take this test. It's about a 6-hour test, and each question is a multiple choice question where you respond A, B, C, or D. So I can't say this enough. In your senior year, make sure you take this FE exam. So you pass the FE exam, you get your degree, you go out and work under the experience of a licensed engineer. The next step is to take the PE exam, or the Principles and Practice of Engineering exam. This exam is a discipline-specific exam. So fire protection engineers take one exam. Electrical engineers will take a different exam. Mechanical engineers take a different exam. The question on this exam in fire protection is written by the members who are part of the Society of Fire Protection Engineers. About every 7 years, the Society of Fire Protection Engineers goes out and surveys licensed engineers. And when we do the survey, we ask them, what do you do on the job? What are the knowledge and skills you need to know to be a fire protection engineer? We do this so this test remains relevant. When you are taking this exam, it should look like the same type of work you are currently doing as a fire protection engineer. This exam is usually taken 4 years after graduation. Some states, like the state of Nevada, you could take it right after school, but you still need to meet that experience requirement. The fire protection exam right now is an 80-question exam. Unlike the FE exam, you do not take the exam on a computer. It's a pencil and paper exam, and it's called an open reference exam. And what we mean by open reference is you could bring as many books, guides, handbooks that you could possibly bring into the exam. So it's important that when you do take this exam, you have a strategy for the references that you do bring. Right now, in the fire protection engineering exam, we ask you questions from anything related to how humans behave in fire, to questions about fire dynamics, to questions about the different kinds of systems fire protection engineers might be asked to design, whether it's a fire sprinkler system, whether it's a special hazard suppression system, whether it's a fire alarm and notification system, a smoke management system, or a passive fire protection system. Everything you need to know should be asked in that test. One organization that SFPE works with to produce this exam, and then the state boards also work with, is an organization called NCEES. Their website is www.ncees.org. If you'd like to find more about the licensure process for engineers in the United States, I suggest you go to this website. It provides all kinds of information, like the 3 steps I talked about today. It also provides you with the references that are needed to take the FE exam. And they also have study guides and practice tests and all kind of other interesting information about taking the exams that you need to become licensed. So, why should we become licensed? Well, first of all, we do this to protect the public's health, safety, and welfare. It's all about protecting the public from bad and incompetent engineers. That is why we have a licensure program in the United States. A licensure program establishes competence. It tells you and the other people you work with that you are competent to go out and work as a fire protection engineer. It is also a tremendous career path for advancement. It opens doors to many jobs that you might not get if you were not licensed. It also provides the opportunity to make a better salary. And I don't know a single person that would not like to have a higher salary.
This particular week is part of a couple-week discussion that we'll talk about fire safety systems. These fire safety systems that we talk about in this week will be a bit of an introduction to the fire safety systems, principally that get installed in buildings, though they could get applied also in some ships and various transportation vehicles, offshore oil wells, and so on. But we're going to talk principally about buildings as our case study. The fire safety systems in particular that we will talk about in detail today will be detection alarm systems, suppression systems, and smoke control. There are other systems, as you'll see as part of our introduction, that get talked about in later weeks. So, as we look to these fire safety systems that are provided, There are these set of 7 fire safety systems altogether that are talked about and recognized in the fire protection engineering field pretty much internationally. I have to say that there's agreement that these are the 7 systems. So in no particular order, so these are not prioritized or whatever by where they are on the circle, but you see these 7 fire safety systems all have arrows pointing into fire safety objectives. So they're all there to accomplish or help accomplish a set of fire safety objectives for the facility. The objectives in the fire safety systems are flammability materials, so it gets into material control type issues, and what do we line the walls with, and what kind of furnishings are provided in the building. We look to protect the structure, provide egress and life safety systems, basically exiting systems. The fire department plays a role in some fashion, needs to be recognized, and as such. There are smoke control systems, there are suppression systems, and detection alarm systems, finally, that get incorporated into buildings, all for the reason of providing or accomplishing a particular set of fire safety objectives. So what objectives come into play? Well, life safety is of course one of these, and that we want to protect people, property protection, and also protection of contents. Would be relevant. So the property, sometimes people just think that to be the building, the structure itself, but we want to consider the building and its contents. Protecting the mission is important. So a facility may want to have a relatively minor fire so that they can reopen in the next day. Or the next month, or in some defined time period, or there may be some missions that they can't abort unless there are absolutely catastrophic circumstances going on. And you might imagine a hospital being that mission protection is very, very important. Heritage preservation might be a significant objective in historic properties or in cultural resource properties, in museums and those sort of places. And finally, protecting the environment will be a part of, or could be some of the objectives stipulated for a facility as well. So an example, let's look at life safety. And in the NFPA 101, so part of the National Fire Protection Association's codes and standards, NFPA 101, the life safety code from the 2013 edition, the statement is made of an objective of what the premise of that code is. And that is, you can see, except for occupants intimate with ignition, no occupants shall be exposed to instantaneous or cumulative untenable conditions. So aside from the people that are intimately involved in starting the fire, either as an act of negligence, maybe a criminal activity, or just an accident that they were part of, aside from those individuals, everyone else, the life safety system is designed to make sure they get out. Property protection, another example. So this is a photo of one of the World Trade Center buildings, Building 5, that was impacted by the events of 9/11. You can see that this building sustained complete burnout on that particular day, but it's still standing. Right? There was a statement made in a research report from the Building Materials series from at that point the National Bureau of Standards, now that's NIST, the National Institute of Standards and Technology, that made the following statement that said the idea of designing some buildings for the full fire severity corresponding to the occupancy is a logical advance in fire protection engineering. So as made in the middle of the 20th century, the idea that you should get this outcome, they felt was a very reasonable approach and could be an objective. Fire protection engineers typically are interested in reducing the cost of fire. And it's not just in the losses, but what's the total amount of investment that's made in the name of fire safety. And it could include whatever fire protection costs, so the built-in protection cost. We have costs associated with fire departments, with providing fire insurance, that whole array of costs and maintenance of systems. There are then losses that occur, direct losses, indirect losses perhaps. that occur as a result of a fire. And the general idea is that we want to minimize the total costs. The total costs. You can see that in the cost of fire protection or losses, the one slide, looking at the blue and the red curves that are here, in general, with increasing protection and increasing investment in fire safety, one would hope that the cost of the losses come down. So there is that trend. Though you notice the losses never go to zero, right? Never go to zero, even with a huge expenditure. We're not going to go to zero, but we can get into at least a minimum point that one might talk about as an objective. To the point that having zero loss is not feasible, the other way of saying that is that complete safety is impossible to achieve. We cannot guarantee that for any incident that you might envision that everyone gets out of the building, despite the objective of NFPA 101. If there are explosions, if there are terrorist events, we may not be able to get everyone, we as fire protection engineers may not be able to get everyone out of the building all the time, every possible incident. So everything's got a design limit. It would be another way to say that. So the approach is typically to limit the risk associated with fire to an acceptable level. Right? And that there are acceptable levels of risk that we talk about philosophically for how we live our normal lives. Whether we cross the street or not, there's a risk associated with that. Whether you engage in some sporting activity of skydiving or skiing, there are risks associated with that. And there are some of us, like myself, who see no reason to jump out of a perfectly fine airplane and do skydiving. Right? So there are risks that we make personal decisions about. Corporations similarly make those same sort of personal risk decisions. Right? So what's risk, though? I've talked a little bit about risk here, and before rambling on for a minute or two there, I probably should have come to this and then going back to that. So what's this risk thing all about? Well, risk is typically described as the loss, the probability of loss or injury to people, property, environment. I don't have all those words here, but would be the probability of harm, basically, to particular objectives that we're trying to achieve. It's generally expressed, risk that is generally expressed as the product of the frequency of the event and the magnitude of the consequence of that particular scenario. So we talk about acceptable risk usually using curves of this style or graphs of this style where we monitor or would plot up rather the frequency of events and the consequences of those particular scenarios that have a given frequency. Right? And that anything down here is acceptable. Right? Anything down here under the green line, the blue is simply to identify that for a particular scenario that has a given frequency, that scenario will have a particular expected loss outcome. So accepted risk is anything under the green. And basically the idea here is that we accept things, even very low consequence events. I mean, there's some upper limit there that if you're continually cutting your finger, that there's a point at which if you're doing some activity over and over again to the point that you're cutting your finger, that's a fairly minor thing, you're eventually going to stop that activity if you're getting a cut on your finger every minute, right? If it occurs once every half a year, well, that's life, and we put up with that, paper cuts and that sort, right? As the consequences get more significant, our tolerance for those things goes down, right? So that there is some high consequence sort of event that we would not want to put up with as often. And that's the whole point of the acceptable risk curve, or unacceptable risk, anything up above the green curve. And again, philosophically, at least, if not quantitatively in some cases, the fire protection design and what fire protection is included in buildings would be done to relate to this, whatever is the acceptable risk. So, fire safety is provided in the buildings, and what level, how much fire protection you see as you travel around different buildings. You may not see sprinklers in every building. You'd say, why is that? and it gets back to some of the fundamentals of risk philosophy. So fire safety is provided to achieve a particular acceptable level of risk. Fire safety systems are incorporated into building designs to achieve selected fire safety objectives. So with that, we'll call this first segment of week 2 to an end, and move into segment 2 here very shortly, where we'll talk about the fire safety systems. All right, welcome back. In the continuation of our week 2 discussion, we'll talk some about detection alarm systems. And here we'll talk about the variety of detection systems, some variations in the alarm component or the notification component, and a little bit about again, what are detection alarm systems supposed to do. So a detection alarm system, first of all, has several major parts associated with it. It has initiating circuits, and there are sensors out on the end of those initiating circuits. We may call those detectors as an example, though that's only one example what may be at the end of the initiating circuit. You see, here's the initiating circuit and alarm initiating devices. There's a control panel that's here. So the initiating devices will send a signal back to the control panel to say, hey, something's going on. The control panel then has to sort out what to do about that. There are indicating circuits or notification circuits, and that's what may ring bells or do a variety of things, as we'll talk more about. And then there are power supplies that get involved in any fire detection alarm system. These are the contemporary systems are all electronic, so that power supply usually involves some sort of source of electrical power, if not backup power, secondary power as well. So what's a fire alarm system supposed to do? Well, we get the initiating devices that are here that would initiate some signal going to the control panel. So with the sprinklers, as they operate, there's a water flow switch that will get engaged and send a signal, or detectors or send a signal, or someone pulls a manual pull station that sends a signal to the control panel. The control panel then is the brains of the system, so to speak, that has to figure out then, what am I supposed to do about this? And it's all pre-programmed in by the designers, of course, but it may sound, the notification appliances that may be bells or other things such as we'll talk about, may close doors, may start smoke control fans, call the fire department. So there are these sort of functions that may go on, and again, the function of a particular fire alarm system in a particular building will be dictated by what are we trying to achieve, what do we need to achieve as a result of this detection input. Talk about the variety of initiating devices that are available. So these initiating devices, as the definition says here, are devices that respond to heat, smoke, or other fire signatures. So some way that the fire is telling us it's there, and that's called a fire signature. Or they may include devices which sense movement, flow, or other quantities associated with fire and fire protection systems. So that may be a supervisory switch, for example, in a sprinkler system. This little tamper switch right here that would send a signal in case somebody closed off the sprinkler system. Want to know about that, as now the sprinkler is disabled, and that impacts then the design basis and the level of fire safety in that building if the sprinklers are disabled in the facility. So we see a water flow switch here that would be attached to a sprinkler system to send that signal. A detector, manual pull station, once again, as examples of these kind of things. Fire signatures. What are these fire signatures? And the fire signatures are basically fall into two categories, and largely related to the fire products we talked about last week. So fires create energy, right? And that energy gets released in two modes. It gets released convectively, convection heat transfer, or convective movement that's going to move the energy around. That is movement by way of a fluid, is what the scientists call it. And a fluid means either a gas or a liquid in the scientific terms. So our convection heat transfer is going to go on because of a gas, principally, that is that smoke plume, that ceiling jet I talked about in week 1. Fires release energy also from the immediate vicinity of the fire by radiation. And some of it's in the visible range. We see flames. That's because of the radiant energy coming off in the visible wavelengths. The fires also produce radiation in a variety of wavelengths, wide variety of wavelengths, of which there are 2 others besides the visible range noted here, ultraviolet and infrared, that those wavelength bands are also used with commercial devices such as I show here of a flame detector, or more generically called a radiation detector. The fires produce a wide range of wavelengths. There's been some research on microwave detection, for example, among other things. But these are the 3 ranges of wavelengths that currently have commercial devices involved. There's also a suspension of matter. There's the generation of an aerosol or that smoke layer where now there are particles that are put into the airstream, solid or liquid particles, the case may be. These particles may be invisible in size because they're very small. They might be visible. That's largely what colors the smoke that we see, the fact that there is now visible soot particles that gets us the gray, the black, smoke, and so on. And there are gases that are produced, such as we talked about last week as well, that there are various detection devices that are available to look for particles, basically, of the invisible or visible range, and also to look for particular gases. So let's look to some examples of heat detectors here. The heat detectors may be a spot detector. That is, there's a detector that fits on a particular spot on the ceiling or maybe in the upper part of a wall, and it's monitoring conditions at that particular location or that particular spot, as it's called. These detectors may operate on a fixed temperature rate of rise basis. That is, once the temperature gets to a particular point, maybe the set point is 70 degrees C, that at that point the detector goes into alarm. Rate of rise, similarly, there might be a rate of rise at which the temperature increase is being monitored. So not just a set point temperature, but a rate of increase of perhaps 10 degrees C a minute, something in that area, at which point that would suggest that something may be going wrong in the space. And they go through a variety of different inventions. There are some references around to say, so what's the inside of a detector look like? These heat detectors that are really clever inventions. And for those of you, the entrepreneurs and those of you with an inventive mind, I'd encourage you to take a look and just imagine yourself in your own garage, your basement, putting this little type of device together. They're really clever devices. There are linear detectors as well, where now the detection is done anywhere along a line, right, where this detector is going to be placed. So there are linear heat detectors that basically look like wires, right? They operate on a couple different principles. The one is that the insulating material between 2 conductors melts at a predetermined temperature, and you end up with a short. As a result, sends an alarm, and there can be even some diagnostics about where that short has occurred to identify the location of that fire within a large building. Smoke detectors have a few different types of designs or mechanisms by which they operate. So the one, arguably the most common that you'll find commercially in non-residential buildings, is a photoelectric detector. This uses a light scattering method, so that there would be a chamber inside the detector here, such as I've depicted graphically, a light source, and the light beam going away from the light source. If the chamber's clear, that light beam just goes from one end to the other and never gets to a photocell or a light receiver. Right? Once there's smoke that gets included or contained within the chamber, now that the light gets scattered from that light source, just in the same way that light gets scattered as you drive through a fog. It's the same physics. So that now there's some light that scatters up to the photocell that then sounds an alarm. Projected beam detectors are another possibility where they look like this, and basically it's that light source and photocell again, and usually at 2 opposite ends of a large indoor space, I show an arena as an example. That's one place where they get used. I don't believe they are used in our particular arena, such as I'm depicting here. But this was how in principle it would look with the light source on one side, photocell on the other. And this is going to work that if there's a fire that gets created, we get a smoke plume, a smoke layer. Now that light being transmitted from one side to the other will be obscured to some level, and you'd look for that drop in the light being transmitted to the photocell for the purpose of sounding an alarm. Ionization detectors are the final category of smoke detectors, and this is was the original type of spot detector created or invented in the 1940s. Was the first development of a spot smoke detector using a radioactive source. So americium-241 is the source of choice in these detectors commercially. As a result of producing some ions from this radioactive source, they will migrate between an anode and a cathode to create an electric current. With the introduction of smoke in the chamber, that affects that flow of ions between the cathode and the anode, and you look for that change in current in order to sound an alarm. Air sampling detectors were developed in the 1980s, largely for electronic spaces to begin with, and basically these will have these tubes, these pipes of sorts, often a polymer pipe, maybe a PVC, that will get used, and out at the end there are these little perforated holes or little cones that will be drawing air into the system through an air sampling or an aspirating sort of device. Be drawing the air back all through the piping and down to a sampling unit that is a highly calibrated sampling unit, so you can take a very precise measurement now of smoke concentration and end up with a very early form of detection. Again, it was originally generated primarily to protect electronic equipment rooms and clean rooms, though they've found the market into many other places, in that if it's a good way to detect fires very early in electronic equipment rooms and clean rooms, why not in a lot of other properties? Makes a lot of sense. Radiation detectors, flame detectors, as they commonly get called, will be looking for radiation being transmitted through the air, through the electromagnetic waves from a fire source, and then on up to a detector. These are typically used in cases where you're worried about flammable liquid fires, and often in maybe aircraft hangars and those sort of places, industrial applications typically. And here we look at how these things work, and that a particular fire will produce a radiation spectrum, as I identified that fires release radiation in many, many different wavelengths. You see the visible range noted here. One type of detector, the infrared detectors, are going to be looking at two peaks right here at the right above 4 microns and right above 2 microns. So it's looking for these two peaks, typically, one commercially available unit, that are associated with the generation of carbon dioxide. It's that carbon dioxide emission that is being looked for. That's a very prominent combustion product, as we talked about in week 1 of the commercially available fires. Let's see, as we can look to more contemporary styles of detection or more recent developments. This is using a security camera, where you see a smoke plume on the screen here. So you'd say, well, if we use a camera, we ought to be able to do a screen analysis with a little bit of intelligence and identify the presence of a fire also there, so that we've just detected the fire at this point. You don't see any smoke up here at all in the upper portion of this experiment that was run in our old field house, coal field house, here on campus. And you get detection at a very, very early stage that in high spaces like arenas and large indoor spaces, the detection time can be delayed appreciably if you have to wait for an appreciable smoke layer to form in the upper portion of this. And you see we're getting detection very, very early on from just a smoldering source in the arena. So the video detection is a newer technology that was developed in the 90s and is getting applications in large indoor spaces typically. The selection of a particular initiating device. So I've given you an array of detection devices of the major categories. Haven't talked about all the nuances and the subsets of detectors within those groups. But basically, how does a fire protection engineer choose, I want one of those? Right? And basically that choice comes on these four issues. And of course, cost is going to be involved in any of these kind of decisions. So I put that in, and cost here is associated with the initial installation cost as well as any maintenance cost, of course. Otherwise, the top three are the other issues here. So how fast of a detection do we need to have in order to accomplish our fire safety goals? All right? So that becomes, and of course, we'd like to catch fires very, very early, I mean, to be sure. But there's a cost associated with that. Costs in terms of some of the very, very early detection systems are typically a bit more expensive than that little heat detector we put on the ceiling. We have to look at what signature is going to be produced from the fire in that for a particular scenario that I'm concerned about and achieving fire safety objectives associated with that fire scenario. What's the dominant fire signature that's going to be produced? So I have to think about that. And then finally, what's the ambient environment like, and what sort of changes do I get in the environment? What nuisance alarm sources might be present? In that there are some of these type of detection methods that if I'm in a particular environment that has lots of particles all the time, then a smoke detector may not be the best choice. Right? So that we have to do some thinking about what's the signature produced, and is that the magnitude of that particular signature going to be easily recognized, or is it going to be masked by a continual presence of nuisance alarm sources? Looking at the notification appliances, there are three general categories of notification appliances, and it all started out principally here with audible methods where loud bells were rung, or you make a lot of noise by horns or chimes or those sorts of things. And we'll talk more in a life safety related discussion about alerting and what type of signals are appropriate, especially as we notify people, the building occupants of a fire. Basically, this ought to do more than just scare them because it's a loud noise. Ideally, if we're looking for a particular response, then we need to give people some information about what's going on, and that gets us into then the speaker-based systems where there may be a taped message that gets played to occupants on a particular floor given a particular detection device is operated, and then sound horns and so on, but provide information to people. Very, very important. For the hearing impaired, strobes are going to be very, very important as a way, and this is an example here where there's a strobe that will operate to tell the hearing impaired people that there's an alarm. If the hearing impaired folks are not awake, having a strobe is effective to a point, but but has a limited effectiveness. At which point that perhaps there are bed shakers that get used, as are commonly used as part of an alarm clock for the hearing impaired, for the deaf. And we could have a bed shaker as a possibility, as a way of alerting them of a particular fire condition. So, in this particular segment, we saw there are fire detectors available to detect a variety of signatures from fires: smoke, heat. Convected heat is largely what the spot detectors respond to. We saw the radiation detectors for the radiant energy. That fire alarm systems are used to alert building occupants, may also perform additional functions, and again, what the fire alarm system is intended to do depends very much on what are the stipulated fire safety objectives for that facility, and what is it that you want to accomplish by detecting a fire early on. At least alerting the building occupants, that's pretty much a common denominator. Whether you do more depends on the facility. So we'll bring this particular segment to a close and come back in the next segment and talk about suppression systems. Welcome back. This is our third segment of week 2, and where we want to talk some about fire suppression systems. So these fire suppression systems will get installed in buildings, or there are various mechanisms for fire suppression. We'll talk about the various options for systems that are available. And I do want to point out I'm using the word fire suppression here. Very, very important distinction as compared to fire extinguishment systems, in that fire suppression systems looking to contain the fire or limit the growth of the fire, where a fire extinguishing system is specifically designed to put the fire out. And of course, that's the ultimate objective. But many of our fire suppression systems are geared or designed principally to limit the growth of the fire, to reduce the hazard until the final extinguishment can be achieved. When we look to the mechanisms of fire suppression, we go back to Hessler's Fire Tetrahedron. We talked about that in the first week. Remember, there were 4 surfaces, and the idea of an ignition was you needed all 4 parts of this surface to be present. Here, in suppression, now we talk about removing one of the surfaces of the tetrahedron to provide fire suppression. Water becomes the agent of choice more often than not, and there are a couple reasons for that. Number one, it's very effective for reasons we'll see here in terms of the thermal benefits of water. The other principal benefit of water is it's readily available in an awful lot of facilities and an awful lot of areas on the planet. So that being so readily available suggests that it's going to be fairly cheap. And this readily available agent, Mother Nature has been fairly kind to us in that this readily available agent is also very effective. So that water suppresses fire by one of 2 mechanisms, principally by a cooling mechanism and also possibly by oxygen dilution, as we'll talk about. So in terms of vaporization of water, when we get absorption of heat by water going from its ambient temperature up to steam, by first of all increasing the temperature from whatever ambient temperature it starts with. So let's say it starts out at 20 C and up to 100 C at the evaporation or boiling point. We're going to absorb 330 joules for every gram for every gram of water that's involved here. As that water then evaporates, as it gets to 100 C and now evaporates, there's another 2,260 joules for every gram of water that's involved. So we end up with about almost 2,600 joules for every gram of water that goes from 20 C on up to steam. When you look at the variety of other materials, other liquids, certainly, there aren't many that compare and do that well. Number one, and again, secondly, layered on top of that is the fact that water is readily available, and you've got this wonderful substance in terms of heat absorption capability. The other possibility is through oxygen dilution, and that when that steam is created, that 1 unit volume of liquid water now goes to 1,600 parts in steam. And so that's the 1 to 1,600 ratio you see here. So if I have a liter of water, just a little liter container of water, and transform that all to steam, I get 1.6 cubic meters of steam. As all that steam is generated, that's going to push the oxygen out of the area, certainly out of the local area wherever the fire is and all that steam generation is going on, and may effectively inert the room. There are special hazard suppression agents also that we talk about in the field, and these are basically the variety of agents other than water that get involved. So there's carbon dioxide as an example. These are the inerting gases. Carbon dioxide I mentioned. There could be nitrogen as well. There are some nitrogen suppression systems. There are steam systems. That was an early application, shipboard applications, to just dump a lot of steam into a particular container where a fire was. It acts by reducing oxygen level in the space and gets used in these sort of facilities currently. Now, one of the drawbacks, every one of these agents has their drawbacks, water included. The one drawback with CO2 and these inerting agents is that it reduces the oxygen in the room, and that's how it works. But the disadvantage is if there are people in the space, when that happens, they're not going to be able to survive unless they get out before that discharge, before that injection of that inerting agent occurs. Clean agents. These are the more contemporary agents. Some of you may have heard about the halon agents, the halon 1301 and that sort. There are an array of agents that have been developed since halon has been discontinued. The variety of clean agents here act principally by heat removal. There's usually not enough of the agent generated to do the oxygen displacement, though there's some of that goes on, but it's mostly, the action's mostly heat removal. And again, these agents get used where there's electronic equipment involved and other very water-sensitive objects. Dry chemicals that are in portable extinguishers, for example, will interrupt the chemical chain reaction and also act as a heat removal agent. These typically get used where there are flammable liquids and gases involved. You find them in office buildings and the like, so they're also effective to a point on solid materials. Foams, firefighting foams, that I have a video a little bit later, basically these layers of bubbles that get created by systems will provide a blanket over the fuel surface, so it separates the fuel from the air. So we're basically involved with a fuel removal system, though it depends what your perspective is. You could say it's separating the oxygen, so it's displacing the oxygen, limiting oxygen availability to the fuel, or it's removing the fuel and essentially by providing a blanket, not allowing the fuel vapors to rise and again mix with the oxygen. These typically get used in flammable combustible liquid areas, though again they've been used to combat fires involving solid fuels as well. So the couple types of systems and how we include systems here, so to speak. I want to talk first of all about manual suppression. It's a very commonly used type of mechanism to put out fires or to suppress fires, let alone extinguish them. I don't know that there are statistics on the relative proportion of fires that are put out manually versus automatically, though I would propose to you that there are many, many more fires that are suppressed, let alone extinguished, manually than automatically. And I mention that in part because I suspect there are many uses of portable extinguishers, for example, that get used where the fire department never even gets called. So we don't even know about those fire incidents. And there are some that suggest that for every fire incident that's reported, there are 10 of them that go on but are never reported to the official agencies. So portable extinguishers are part of this manual suppression system. We want to acknowledge that the use of hose lines by the fire department or by a fire brigade, by an industrial group, that provides a manual suppression activity as well. And then there are these automatic systems that very often have a manual discharge or manual button on the wall that if you detect the fire as you're the cook at the range hood, that you may see the ignition of a fire well before any detection devices in the hood, and you can go ahead and press the button and to get the system discharged. Automatic systems will have some sort of initiating device, so there'll be a fire detector of one sort or another, such as we talked about in the previous segment, so that your choice of fire detectors here, initiating device, get involved in how fast do I have to have operation of the suppression system. Also gets involved in what's the possibility of a nuisance alarm, or false alarm, as they sometimes get called, in that with the presence of a nuisance alarm now, these become a bit more of a nuisance in the sense of just ringing bells and bothering people, but there's now an agent that's going to get discharged, so there's this massive cleanup that's going to occur, as well as whatever costs to refill the reservoirs with the agent. So this fire suppression system, this is a gaseous sort of system, as you can see with the air bottles. This is the sprinkler system that we see, where now the initiating device is the sprinklers, or the sprinklers themselves typically, although there are some sprinkler systems that will be activated by, or actuated, I should say, by some type of initiating device. So there is this variety of types of suppression systems. The fire protection engineer has to choose which one to use and what's the basis for why they pick one type of system over another. And it involves essentially these 5 factors where, again, cost is very much part of the picture. We're not going to get away from that. So let's just talk about that. That's in the middle of the table here. So The costs that are involved, again, it's a life cycle cost. So not just design costs, but also installation costs, maintenance costs. Should also identify some costs that are involved here on the positive side of the ledger that may be insurance benefits, tax benefits, these type of things to help offset some of the cost picture. Performance, cost-wise, again, there are some cost issues that we'll get involved in terms of how responsive, how effective is the system, and what sort of losses do I expect out of if that system activates or operates. Is there any collateral damage that gets produced by the agent that will further damage equipment that I might be concerned about? Coming up to the top, though, for the rest of the items. So what's the suitability for the particular hazard? Does that particular type of suppression system or suppression agent work on fires involving that particular material? So I have to think about that. Water isn't effective on everything, on all kinds of agents. There are some notable examples of water-reactive materials, of course, that are not going to be good. Combustible metals, water's not very effective on those. There may be equipment damage, and that's the collateral damage sort of issue again that may be there. What the agent-fuel interaction to the point again that I talked about water-reactive materials. Personnel hazards, talked about that with respect to carbon dioxide, for example. You know, what's the toxicity of the agent? Is there a reduced oxygen level that's going to be created? Maybe obscuration levels in the space. Though I'll mention in terms of obscuration, there are few of the agents that work that don't provide some level of obscuration. Some worse than others, but that's fairly typical. They get at least some obscuration as a result of perhaps a changing characteristic in the smoke that's created. If it's a fixed system, such as I showed you the couple diagrams here with gas cylinders here, there's got to be some supply of the water that's here, and sometimes that's an elevated tank, maybe a lake or a reservoir that's present. In some cases, it's a flowing river where the water is coming from. So I'll have to think about where the agent supply is coming from. And if it's a fixed supply that I have just this on-site storage, now I have to look at how much do I need? How much room is that going to take? As the system operates for a particular fire, how long does it take to recharge it so that we can reopen with protection in place? What's the availability of the agent? There are still some Halon 1301 systems around, though, that as the agent's not being produced anymore, as a system discharges, then getting a replacement of the Halon 1301 is a bit problematic outside of some of the special reserves that are available. There are a couple application methods that are available, either total flooding or local application. The typical sprinkler system involves a local application that just the sprinkler above the fire or closest to the fires is the one that will operate in most fires. And it's rare that let me say it another way, sorry. So the closest sprinkler operates, and in order for a second sprinkler to operate, it requires that first sprinkler is not overly effective and there's still enough heat being generated and transported out through the ceiling jet to cause a second sprinkler to operate, and third sprinkler. The only exception to where all the sprinklers go off into space is, of course, what our movies like to portray, which is just a myth and usually completely incorrect for a particular facility, is where there's a deluge system involved that's specifically designed for all the sprinklers to operate. And that's usually a very special case, usually an industrial setting, maybe a transformer vault or those kind of places. There are total flooding systems. These are usually the clean agent systems, the gaseous systems, the foam systems, such as I've got a video on in a little bit, where you'll see the whole place fill up with foam. Water is usually the default agent of choice. All right? So why would you ever go anywhere else? And you get into some of these special sort of considerations where water is ineffective or hazardous, and then maybe in a fuel oil tank, storage tank fire, as water gets injected into that, if that drops to the bottom, it doesn't necessarily sit on top of the fuel. So as it sits on the bottom of the fuel tank, it may end up heating up as a result of continued fire development and end up with a boil-over situation. It just spews fuel, burning fuel all over the place. Water-reactive fuels, talked about that. Collateral damage issues. with water on a printing press or a computer room. Though again, I want to caution you a little bit in that there's an awful lot of overreaction to the interaction of water on some materials. That a fine mist or a fine spray is often completely acceptable to put out a fire because of the cooling aspect. So don't get oversold on, oh, we can't use water on this particular fuel item or type of fire scenario. Some cases their agents are more cost effective than water. That is, if the hazard's in a very, very localized spot and I only need a system protecting that corner of the room, well, then that may be less expensive than providing sprinkler protection throughout the place. So there are those possibilities, and it's not often you find a spot that the hazard's localized and will only ever be in one part of the room, but those cases do exist. There are cases of weight. The water weighs a lot, so that is there something we want to do besides sprinklers? So you don't find sprinkler systems on board aircraft, for example, because there's a huge weight penalty associated with that, or with our space vehicles. Shipboard applications, water may be difficult in that if we flood a compartment, if that may cause the ship to go out of balance, become a problem eventually. If you fill up the whole ship with water, that usually makes for a bad day for the ship, and you sink the ship at that point. So a couple of demonstrations. So this is a clean agent. So you can see the discharge in a clean agents here. So some of this obscuration, again, as that clean agent now evaporates or vaporizes and gets into the gaseous form where it's most effective. I have a short video clip here I think we should be able to see. So this is looking at the performance of one of the clean agents, Novec as it's called. So it's one of the clean agents. The vapor is heavier than air. See a little candle experiment here. As the beaker's being poured, the vapor's flowing out of the beaker. This is vapor that's heavier in air again. So the vapor accumulates in the bottom of the beaker and eventually puts fire out. So that's one example that I have for you. So this is looking at an aircraft hangar now, where foam systems are often used. So they've initiated the system, it sounds like, you can hear the horns. And we're starting to flow foam at this point from these rooftop units. You can see the foam now dispersing on the floor, and it is creating a blanket of foam. If you picture there was a flammable liquid spill that would be burning, we'd be blanketing over that spill at this point.
So what's the ruling there, Steve?
There are a number of these videos online that you can Google firefighting foam and get several examples of this with rather amazing videos of the foam and how tall it builds up and so on. So I'll leave that to you as the interested student to look for more of those videos should you find that to be interesting. Again, the idea with foam and the blanketing systems is again, we're going to blanket the foam here, or the fuel. You can see the spreading blanket such as you saw in the video, and eventually that it'll occupy all the space, such as in this storage tank, to where the fire is eventually put out. So, as we saw in our little walk through suppression agents, these suppression agents act to remove one or more sides of the fire tetrahedron. The fire suppression agents are selected considering four major factors of effectiveness that combined a couple of the items in the table: toxicity, what type of collateral damage might be done with the agent or by the agent, and then what costs are involved. So we'll bring this session to a close and move into the last segment. In the next module, we'll talk about smoke control systems. All right, welcome back, and this is the last of the segments on this particular walkthrough fire safety system. So we want to talk about smoke control systems in this particular portion. So one of the questions that we would ask right up front is why do smoke control? Why bother with that? And there are a couple reasons. From a life safety perspective, as you can see from the statistic up top here, 2/3 of the fire deaths in the United States in 2010, the last year that such was tabulated, were due to smoke inhalation, and that was for any building. The percentage jumps up to 87% in residences or residential occupancies. So smoke-related fatalities are a key part of the statistic. There may be big fires of this sort. This is the MGM Grand fire from November of 1980. The fire starts on the ground floor, on the casino level of the building, and effectively never leaves that level. There were a couple very small areas of growth to the next floor, but that was it. So the fire stays essentially on the first floor, and you can see the smoke billowing out of the upper half of the building. When you plot where the fire deaths were and what floor level they were on, there were some people on the casino level who came down elevators that opened up on the casino level. So that's these 18 of the 84 deaths altogether. Otherwise, all the rest of the fatalities are in the upper half of the building. And you'd say, why is this? And that this becomes, unfortunately, a textbook case in smoke movement in high-rise buildings, that the smoke's hot. It's rising. So this is similar to the discussion we had last week that talked about smoke rises to the upper part of a space. Well, it's rising to the upper part of the building. And the other piece of this is just in terms of airflows in high-rise buildings. This fire occurs early in the morning on a fairly cool day in Las Vegas. At the time of the fire is about 5-6 degrees C. So the normal airflow in such a high-rise building then is for the air to come in the lower floors and rise on up, and the smoke just piggybacked along with that airflow pattern. There was no active smoke control systems in the building at the time of the fire. Once this building was reopened the following July, there were smoke control systems put in, such as we'll talk about. Why else do you do smoke control? Well, there's the potential for property damage and extensive property damage in some facilities as a result of smoke contamination of the contents. Just the smoke staining, the odors that go on with exposure to smoke, as well as smoke may contain some very corrosive components that as that gets onto electronic circuit boards, that'll quickly lead to corrosion of that electronic component. So why do we put smoke control systems in buildings? You may get a sense from that from some of the problems as they are, but smoke control systems get put into buildings for a variety of reasons. And it really varies by the building, the type of building, as to why a smoke control system would get put in. I should say, and before I forget completely, and perhaps should have made this comment in the first module, keep in mind when I talk about fire protection engineers need to put in XYZ system to achieve a particular objective, keep in mind that the fire safety field is very much regulatory driven. So there may be regulations that will be in place to say, in this kind of building, you must put in a smoke detector, sprinkler, smoke control, whatever kind of fire safety system. So it's very much regulatory driven in a lot of parts of the world. There are cases where the fire protection engineer has much more choice as to what kind of system to put in, and it's more in those cases where it's an open book, where the fire protection engineer has complete choice, where some of that selectivity issue comes into play. But so where one's putting in a smoke control system, there may be a bunch of different reasons for that. And some of that may be to maintain a tenable environment in key areas of the building, such as egress paths that are required for evacuation, in which case we'd want to keep those clear for the time it takes to empty the building of people. There are areas of refuge where for some individuals we won't ask them to evacuate completely or won't require them to evacuate completely from the building, but they'll be able to remain in a place as long as that's a protected place, and that would involve some smoke control likely. Maybe command centers in buildings where all the controls go, where you'd want to maintain some tenability there for anybody having to monitor the incident from that location. Similarly, in shifting to shipboard fires, in the command center of a ship where the pilot is, and so on, you'd want to make sure that that area maintains clear or relatively clear smoke so that the ship can continue to move as necessary, or maybe engage in some military incident if that's the purpose of the vehicle. Some cases, our goal may be to limit smoke movement outside the immediate fire area. We may provide smoke control in buildings to assist the fire department, so that the smoke layer is higher than it otherwise would be, so that they can see where they're going and identify where the fire is, maybe provide search and rescue, and also perhaps remove some of the heat load so that the firefighter is not exposed to the very significant heated environment that they'd see otherwise. Maybe want to limit quantity of smoke exposing property and contents. That's kind of a blanket statement that may be covered in one of the above. And there are some cases that will get a benefit from smoke control by getting rid of the smoke after the incident. Talking about a couple of particular types of systems, stair pressurization is one type of system that gets used. This is getting used now to basically pressurize a stairwell. So this yellow shaded area would be a high pressure zone. And what's the significance of that? Well, any air or smoke or fluid travels from a high pressure zone to a low pressure zone. So if the stair is the high pressure zone, then the likelihood of fire spreading from an adjacent zone is reduced, right? Because it would be going from a low pressure zone to a high pressure zone, and the physics doesn't work that way. Right? Why would we do stair pressurization? Well, these are typically done to maintain a tenable egress path, because the people are going to be in the stairway in a high-rise building trying to get out. The design basis for the systems, there's a minimum and a maximum level of pressure difference that you'd want to generate in the stair as a result of some fan that would typically be at the top or maybe along the walls at different elevations of the stair. The minimum pressure difference is we want to create enough pressure difference here that it is greater than whatever pressure difference the fire generates. Remember back in the first week, talked about the fire room is going to be at a high pressure. So we want our stair then to be at a higher pressure than we'd expect to be in the fire zone here. And secondly, we don't want too much pressure in the stair, because as an occupant needs to get off the floor and into the stair, they have to open the doorway and oppose that pressure difference. So we don't want that pressure difference to be so high between the stairwell and the building floor so that people can't get into the stair. These systems, these fans are typically there solely for smoke control. We're usually going to use any fire alarm initiating device in the building to say, there's a fire somewhere, let's start the fan and get this pressurized. The stairs are usually not pressurized 24/7, only at the time of a fire. So zone smoke control is another type of system that's interesting and gets used, again, maybe to protect that area of refuge. In buildings with many levels up underground, basically a high-rise building that's below grade. High-rise buildings sometimes will have requirements for zone smoke control systems. And a zone smoke control system is now where there's an identified fire zone that we'd have because of initiating devices in that zone. They're saying that's where the fire is. It's on that third floor of the building in this graphic. And I'm going to make the fourth and the second floor high-pressure zones. And as a result, limit the smoke spread off the fire floor and keep it from going to one of the adjacent floors. This can be done, again, through dedicated fans that are there solely for that reason. In an awful lot of buildings, the HVAC system, the heating, ventilating, and air conditioning system in the building may be altered in its mode of operation to be able to generate this pressure difference. These get activated. These, again, it requires the HVAC system to change its mode of operation, so there's something that needs to be used to detect the fire. Or where there are dedicated fans to start, we need some device to start this. And in this case, we're only going to use those fire alarm initiating devices which can absolutely, reliably identify the fire zone. So we typically deal with automatic devices such as smoke detectors, heat detectors, sprinklers to do that, as opposed to manual pull stations, because we don't know where an individual is going to pull that pull station where they've sensed a fire. The previous two systems required some level of compartmentation. Right? So in large open spaces, we can't rely on creating a pressure difference across some transparent boundary in a covered mall, right? So that now we get into a whole different breed of systems and smoke exhaust systems, basically. So in a covered mall situation, where a store is now heavily involved in fire, producing a tremendous amount of smoke, endangering lots of people, spreading smoke throughout much of the mall and leading potentially very significant smoke contamination problems. Indoor arenas, coming back to our arena at Maryland, where there's a life safety issue, and if the upper bowl of the arena would get filled with smoke, eventually that smoke layer is going to descend, and we would not like it to descend on the people in that upper deck. Right? Just because they've got the least expensive seats doesn't mean they're expendable, right? Especially in that's where my seat has been, in that upper deck. So I have an interest in let's provide some smoke management here. So we'd want to have that smoke exhaust generally stop, or smoke exhaust systems there and of sufficient capacity to keep the smoke above the head of the people in that upper deck, on that top row in the upper deck. So that's kind of the point of this top bullet here in the design basis of looking at an atrium fire, or fire in a tall space. So I saw a high-rise building with an atrium and where there are walkways or balconies that the individual is on. Think of maybe some contemporary hotels that you've been in, or office buildings where you've seen these fancy atria where the smoke is rising, accumulating in the upper portion, and we'd want to provide enough exhaust to limit that descent. More on that in a moment. There are other cases where we want to provide enough exhaust to limit the conditions of the smoke layer. So if somebody does get involved or does get immersed in some smoke, that it's not going to be life-threatening or maybe damaging to particular equipment, and that we can tolerate a little bit of smoke, can't tolerate a lot of smoke. Right? Maybe we want to prevent smoke spread from the large space, so we want to prevent the smoke from coming down to where there's an open door and now starting to cause exposure of objects or people or whatever on the top floor that are in this adjacent space. The approaches, the two most common approaches for providing atrium smoke control is by having a fan up top here, exhaust fan, and again it would be dedicated for this reason. And the other possibility is a natural vent, a skylight that would open up, as an example. And again, typically any fire alarm initiating device will get used in this, especially any fire alarm initiating device that would be in the vicinity of this atrium area or large open area. So to dig into a little bit on smoke exhaust capacity, I've mentioned that we want to size this fan up here to limit the descent of the smoke layer. And basically, the approach is quite simple that gets used, amazingly simple what gets used. And that the smoke plume is supplying a certain amount of smoke. Remember, that was a transport mechanism for smoke and heat from the vicinity of the fire on up to the upper part of the smoke layer. So there's a certain mass flow being generated here and being provided by the smoke plume. If we take out that same amount of smoke, that same rate of smoke through the exhaust system as is being supplied to the underside of the layer, that smoke layer will stop coming down. Just in the same way that if you have a sink filled with a certain amount of water and a drain open a little bit with the faucet flowing, that you can equilibrate the depth of water in the sink if the amount of water going out of the sink is the same amount coming in through the faucet. So the question is, all right, so how much smoke is being produced? And that is shown here in this particular graph for different heat release rate fires. So there are a couple of factors that are involved in how much smoke is produced. There are several equations that are available in the literature, in the scientific literature, to estimate the smoke production rate for a particular height, right? For a particular height of space and for a particular size fire. NFPA 92, so the document in the NFPA system that addresses this, has a particular set of correlations as depicted by these curves on the graph. The clear height, I have to identify what's the role of the height in this smoke layer, and I guess it'd be better to come back to this bigger diagram, so that what's going on, that height is a player, right? And that what's going on where height is a player is that the fire produces so much smoke as a way of the combustion products. But basically, as a result of this rising plume, there is air that's entrained or brought in and mixes with the plume. And that entrained air ends up really dominating the volume or mass flow of smoke in the plume. So it's that mostly an entrained air or an air pollution problem, if you will, that we're dealing with in terms of how much smoke is being provided to the underside of the smoke layer. Mostly entrained air, and that overwhelms the volumetric flow of combustion products at fairly low heights, actually. So as we look to see how much smoke exhaust or smoke production is being provided, so that how much smoke exhaust do we need? And I guess I should say the other point, we're looking at mostly air here. But keep in mind, when we design a fan up here, our fans that are going to pull out this smoke, that is, yes, it's mostly air, but our fans are not able to discriminate and only pull out combustion products and leave the air behind. They've got to pull out all of it, and that's why we've got to pull out that whole mix, even though it's mostly air. So we look here at a particular clear height, for a particular clear height, and so what size fire do we have? Because the fire will drive how much entrainment there is. The stronger the fire, the more entrainment we get. So you can see there for various size fires, what's the smoke production rate. I have an example here for a 20-meter clear height. So let's say we want to maintain, go 20 meters above the top of the fuel. That's what clear height means, 20 meters above the top of the fuel, up to, let's say, here. We want to maintain that height for a 5-megawatt design fire. In looking at the graph here, alternatively, you could go to the calculations in NFPA 92 if you have access to those, that you see that for 20-meter clear height going up to the blue 5-meter and coming on across, the number you get is 165 kilograms a second. That's how much is being supplied to the underside of the plume at that elevation. So if that's where we want to stop the smoke layer from coming down, then that's how much we have to take out the top of the layer. In a volumetric flow rate, which is usually how we size our fans, there'd be 137 cubic meters a second. For those of you using the English units, and the 137 cubic meters a second is not easily understood as to, you wouldn't have for the American engineers, you may not have a good sense for how big of a number that is. This 137 is about 300,000 CFM. So tremendous, right? Tremendous volumetric flow that we're into at only a 20-meter height. And again, if there are any design engineers watching this course, you appreciate that there are some atria that are well above 20 meters. The arena I showed you, I think the ceiling height is about 40 meters there. So we looked at smoke control systems. These are designed to achieve identified objectives. I showed you the 5 objectives. That again, your objectives would have to be explicitly stated in terms of how deep of a layer can we put up with, or how tall of a clear height do we need to keep people out of smoke. Smoke control methods are available to limit smoke spread. Those are the stair pressurization, zone smoke control systems. Those that use a pressure difference with barriers, or we typically get involved in systems to exhaust the smoke. So for this week, there are, again, 2 issues I'd like you to address. First of all, I'll give you an opportunity to exercise the smoke production rate and smoke exhaust calculations that we just went through. So as part of question 1 here, I say for atrium smoke management, is the smoke exhaust rate more sensitive to the fire's heat release rate or the clear height? So I just want you to get a sense for what's the important parameter that gets involved here, and how important is it to very precisely define the heat release rate in the design fire, and also how important is it to properly identify the clear height, which I will say is usually fairly easy to understand, because you know how tall the tallest walkway is, and if you want to keep people out of smoke, you add a bit to that at the height of the top walkway. So I have a couple examples for you to run here, and that is analyze this by comparing the exhaust capacity needed for two situations. And these can be compared to the example I just ran. So we have our same 20-meter clear height, cut the fire size in half, and take a look at what the smoke exhaust capacity is that you get. And you're welcome just to use the graph. For using the graph, that'll be sufficient accuracy for anything we need here. Again, if you have access to the NFP 92 document, feel free to work out the calculations with a calculator and all that. They're not real hard, I will say. But the other case here is go back to the 5-megawatt design fire and reduce the clear height down to 10 meters. And take a look at the difference in the smoke exhaust rates that you have with our baseline case compared to these two alternatives. And then finally, I want you to pick one of two. Pick one of two here, and not to, you need not do both. You're welcome as an interested student to do both, but in the name of trying to keep the requirements of the course to a modest level, let's say do one of the two. So suggest a fire detector for an application involving a woodworking shop, where wood dust is going to be very prevalent, you might anticipate, where rapid detection is needed. So you'd want rapid detection, which is typically the case in a woodworking shop because there is the potential for rapid fire development if there's just lots of sawdust. It's fair.
Hi, my name is Erica Kulagowski, and I'm a fire protection engineer and sociologist at the National Institute of Standards and Technology. Today, I'd like to be talking with you about the effect of fires on people, and I have 4 modules for you. Through these 4 modules, I'll be describing the basic idea of human behavior in fires, including what human behavior is and what human behavior is not in a building fire. I'll then be identifying the types of behaviors that are performed in fires, giving examples of each through incidents, case studies, and experiments. And finally, I'll end these 4 modules with examples or applications of these ideas to improve safety in buildings. Through these 4 modules, I will be giving a short discussion paper that will be assigned. And I'll be talking about the topic of the presentation. I'll be talking about the topic of the paper at the end of the discussion today. So let's start with the first module. What is human behavior in fire? So there are 3 elements that are involved in a building fire event. The first is the fire environment. And what I mean by that is the smoke and the flames produced by the fire, kind of the conditions produced by the fire event, and these can also be toxic products as well. The second element is the building. And so that includes the structure in which people are housed and where the fire event occurs. And the third element of a building fire event are the people. And today I'd like to talk about the behavior of people. And what I mean by that is their behavior as they interact with the fire environment, the building, and other people in the building during the fire. Before I can get into more about human behavior in fire, I'd like to talk to you about the timeline of a building evacuation. Now I have up on the screen here, kind of as time moves forward, the first point of a building evacuation is the fire ignition itself. And this is when the fire starts, and this can be anywhere in the building. The second phase here I have is pre-alarm time. And this is the time between ignition and when there is notification of the fire to the building occupants. And this can be anywhere from a few seconds to several minutes to even 15 or 20 minutes if it takes a while to actually detect that a fire has occurred. And then you can see the dotted line here that is the alarm time. Now, what I mean by that is any way in which the building occupants are notified that a fire is occurring or some building event is occurring. And from ignition to the movement period here is what we're calling pre-evacuation. And that is the time from which the building occupants are made aware that something might not be right, that something is wrong, up until the point where they start purposive movement or purposive kind of physical activity to get to safety. And then that kind of third period in a building evacuation timeline is the movement period, and that is the time in which people move to safety, and that is purposive movement to safety. They've made the decision to get to a safe place, they've made some activities in which to prepare to get there, and they've started to move. And what I'd like to say with this slide is that activities or human behavior, human action occurs in each one of these periods of a building evacuation. Even in pre-alarm time, the building staff perhaps might be taking actions to figure out more about what's going on and whether or not a fire is occurring, and they might be taking actions to help notify the occupants. During the pre-evacuation period, when the occupants begin to think there might be something wrong, there are actions that they are taking in that period as well. They could be seeking more information about what's going on after they hear an alarm. They might also be taking actions to prepare to move to safety, like gathering their belongings, getting dressed if they're in a hotel building or if they're in their house. They might be trying to help others to get to safety. They might be alerting others. So there's a lot of actions kind of going on in this period here during the pre-evacuation period to kind of get ready to move to safety. And then in the movement period, there are other types of actions that humans are taking. They might be choosing a route and moving toward safety, maybe a route that they're familiar with or a route that they're not as familiar with. They might be resting if it's taking a long time to get to safety, or they might be changing their route if they've encountered untenable fire conditions. So throughout this entire evacuation timeline, people are behaving, they're taking actions, they're moving in certain directions, they're making certain decisions, and this is all based upon what cues they're getting throughout the pre-evacuation period and the movement period, what information they're getting. They're constantly making decisions, and all of this takes time. So the next thing I'd like to talk about is any time someone takes an action in a fire emergency, it is not just random. The action that they take is based upon a process of decision making. And here's my person, and they have certain physical abilities, they have certain experience, they have certain knowledge, they might have certain roles in the building. And once a fire occurs, in order to respond, and one response might be evacuate, one response might be to continue working or to continue their previous activity, whatever their response is, it is the result of a process of decision making. And so they must first perceive or receive cues or information. So if they don't receive any cues from the fire, there's no response to take. They don't even know that something's going on. So they must first receive some information that something has occurred. If they see smoke, they might actually smell smoke or see it. If an alarm goes off, they need to hear it, or if they're hearing impaired, they need to feel it through tactile means. But that's not enough to respond. They must actually pay attention to the cues or information that they receive. Sometimes in stressful situations in a fire, we might receive a lot of information, but we don't have the cognitive capabilities or capacity to even pay attention to it. So after these two phases of this process are complete, it's still not enough to have the individual respond to the fire. They must also comprehend the cues or information that they receive. So for instance, if they smell smoke or smell something burning, they might pay attention to it. Oh, that smells like something's burning, maybe it's toast. They start to kind of try to comprehend the cues that they receive, and it might be something that it might be that they think it's burning toast, they might think it's something more serious than that, but they actually have to go through the process of trying to understand what it is that they're receiving, what they're hearing, smelling, feeling, or hearing. The last couple stages of the process before an actual action can be taken in a fire emergency is they must believe or confirm that the information is valid, and they must personalize the risk. So let's take a fire alarm, for example. If you hear it, you've received it. You can pay attention to it if you've actually said, wait a minute, is that a fire alarm? You start to pay attention to it. When you actually comprehend the information, you say, well, I actually do think that that sounds like a fire alarm to me. But the next couple stages is do I believe that an actual event is occurring that I need to pay attention to? And do I feel that I'm personally at risk? And it isn't until we go through the entire process that we actually get a response from an individual. And this process takes time, because there might be gaps in it. We might misunderstand the information. We might not believe it. It might take a little while to actually confirm that there's a risk. So this is a process that takes time. And again, this process needs to happen before any action, before any and every action in a building fire evacuation. So just a few other pieces or tidbits about that process. If throughout that process at any time, if someone is uncertain about any stage in that process, that usually leads to information-seeking action. So if I didn't really understand the sound that I'm hearing, or if I didn't really know what smell I was smelling, if that's smoke or if that's just burning toast, normally an individual in a fire emergency will take time and seek additional information. And again, that process is a feedback loop. So anytime you receive more additional information, that process begins again. And sometimes that process can be very quick. If the cue is very clear, if it is so crystal clear what is going on, that process can be very quick and someone can make a decision. Or it can be lengthy and there's a lot of kind of feedback and information seeking and more cues are received. And so over and over again, the cyclical process can be very lengthy. This process can be messy also. If an individual is not provided with very much information, they start to fill in the gaps with their own biases. And one bias that is fairly common in fire emergencies is to feel that we are in fact not at risk. And so there might be a misconception in fire emergencies that a lot of people automatically feel at risk, and that is actually not the case. The opposite is normally the case. And that even though we might receive a fire alarm, hearing it or feeling it, our first response actually is to feel like there's nothing going on, that we're really not at risk and that we're okay if we sit at our desk or remain in our room. It isn't until we receive more intense cues or more credible information that people actually start to act. And when there is gaps in our information, we actually start to fill those gaps in with our previous experiences in disasters as well. So for example, if we've experienced a lot of fire alarms in the past that actually didn't, that a consequence from those alarms was not a fire, so what we consider maybe to be a false alarm, then we're more likely to believe that a false alarm is occurring at this point in time as well. And if we've been trained significantly in the dangers of fire and how to respond to fire, we can fill those gaps in efficient ways and say, I know that this is a fire alarm, I know I need to evacuate immediately, and we can start to do so. So there could be experience in our disaster that might hinder our progress in a fire, and there could be experience in our training in fires that can actually help us achieve a more efficient fire response. Or we can continue to seek information if we continue to receive little information or confusing information or conflicting information. And if we find inaccurate information, that is very unhelpful as well, because we can act upon that. If we believe it to be true, even though it's inaccurate, it might actually cause a response that's not safe and have people act in ways that might put them in danger. So as a result, what people do in fires is a lot of things that could actually lead them into danger or could inhibit their safe movement. One of those could be we might ignore cues. And that's not through any fault of our own. If we're doing something that takes a lot of our mental capacity, we might not able to pay attention. If we're very stressed, for example, we might be narrowing in on something and not being able to pay attention to the other cues that are going on. And that's why it's so important to provide cues that are very clear, that are intense in a way that really grab our attention so that we act in ways that are safe. We can also misinterpret cues and misunderstand instructions. And a lot of that has to do with the way that the instructions and the cues are provided to us. We might not understand what a fire alarm means. If we speak one language and we're in a building where the fire information is given in another language, we're not going to understand that. And so that makes it difficult for us to take safe actions because we've kind of stopped ourselves in the process. We're at that comprehending cues stage and we don't understand, and it's difficult for us to move forward and take safe action. And because of that, we could perform a variety of different actions that are not related to evacuation safety. For instance, we could be searching for information or milling about. That means talking with other people about what's going on. And that could be taking time away from us finding safe refuge, reaching safety sooner. We could also be searching for others or rescuing others. We could be performing non-protective action activities, such as continuing to work or continuing to perform our activities and not reaching a point of safety sooner. Or we could have started our movement to safety and then return to our offices or to our apartments because we really don't believe that an event is taking place. So a lot of these things, because we're not maybe provided with the right information or accurate information, or we've provided with conflicting information, we've seen in previous fire events that there are things that people do that do not lead them to safety and could potentially put them into danger. There's also additional kind of behavioral facts that I'd like to talk about before I move on to the next module. Remember that person that I had kind of standing in the middle of the screen that was going through all those stages of a decision-making process? That person can have differing physical or cognitive capabilities in any building in the world. Right? We cannot assume that our population, everyone moves the same, everyone has the same abilities, both physical or cognitive. That's just not going to be the case. And some of the numbers we've been seeing in the United States is that we can assume that about 6% of our population in our buildings have some sort of disability. And so we have to take that into account when we're thinking about how to make sure that our population reaches safety from a building fire. All right? And we're also not just one big group of people in a building that will evacuate all together, all at the same time. Instead, we can think about a building population as a kind of different social groupings. All right, so there might be families that stay together in an evacuation. There might be coworkers who know each other who stay together when they evacuate, or make sure that they find each other first before they evacuate. And so instead of looking at the population as, a group of strangers, that's not right either, or a group who all know each other and who all evacuate together, we should be looking at a building population as a bunch of different social groups and trying to understand how those groups might interact during a building fire. Instead of just thinking, too, as people who are risk-averse, which is what I talked about in the middle of this module, we also have some people who may perform high-risk behaviors. All right, they might do it intentionally or unintentionally. Intentionally is, we've seen examples of when there have been significant amount of smoke in front of them in a route, and they walk through it anyway. And so that is, if people feel at risk and that there is no other way to evacuate, we have seen that people will walk through a significant amount of smoke. Or unintentionally, if we don't give people the right information, they could find themselves moving through some very dangerous places in the building, and they do it because they don't know any other way. All right? The next kind of key behavioral fact is that people are likely to move to the familiar. And this is a really important part for fire protection engineers to understand, and for also the public to understand. We can't just know the one main route in a building, because that is what's familiar to us. Normally, we know the route in which we've entered the building, and for some buildings, that's about all we know. And our buildings are designed for people to use all of the routes available equally. And so what we found in some of our building fire events is that the main exit gets clogged or congested because that's the route that people use, because that's the one that they know. So it's really important for us to think about the other routes that are available to people, that we should also, when we walk into a building, understand what are the other routes available to us. And if we're getting to a point where we're designing an evacuation procedure for a building, we have to understand that people are most likely to use the routes that are most familiar and find other ways to make sure that in a fire event, people will find other routes that are not so familiar to them. Another thing that people do is move to people who are familiar to them. And so, like I talked about with the social groupings a couple bullets earlier, people are likely to find the other people in their social groups before they evacuate and evacuate together with them. And the last key behavioral fact is that people are likely to respond to authority figures and the information provided to them by that authority figure. And so what I'm saying here is that role matters. And so there was a nationwide survey done a while back asking Americans who was their credible source of information in the United States. And we should know that there is no one credible source for all people in our population in the United States. Some buildings may find someone else credible, like their building manager, or they might find the mayor of their city more credible than people in another building or another city. But the one kind of main credible source, the source that got the highest percentage in this nationwide survey was firefighters. So we do know that there's kind of an understanding in our country that firefighters do provide credible information to us, and if in a building fire, we are likely to listen to them. But it's important also for us to know when we are looking at a building, when we're trying to make a building safer, if we're designing emergency procedures for a building, who is the credible source, or who are the credible sources for our building population? Who will they listen to? Who do they find credible? And then provide that person with information, or a way for that person to give information in a fire event so that people listen and reach safety sooner. So as a summary to this module, what I talked about was that a building fire event is made up of 3 different things: the environment, the building, and the people. And human behavior occurs throughout the entire building evacuation timeline, all phases from ignition to the pre-alarm phase, to the pre-evacuation phase when people are trying to figure out what's going on, when they're trying to decide if an evacuation decision is necessary, when they're trying to prepare for evacuation and kind of move forward, maybe help others throughout that period. And then even in the movement phase, we're constantly receiving additional cues. We're making informed or uninformed decisions based upon those cues. And then we're performing actions like taking certain routes, maybe resting for a little while, maybe changing routes throughout the way until we reach safety. And then the third bullet is that behavior during fires is a result of a process. It is stages that people need to go through before they actually act. And that's kind of perceiving and paying attention and comprehending, and then getting to that place where asking ourselves, is this credible information, and do I feel at risk enough that I need to act? And throughout that process can be broken through different in different ways that I talked about, and that kind of leads us to do more information seeking, which takes a lot of time. So if we can give people accurate information about what's going on, that actually helps them to go through those stages sooner and reach a point where they respond in a safer, more efficient way. And so that's the end of Module 1. Thank you for listening, and I'll go on to Module 2 soon. Hi, I'm back to talk about the second module in the human behavior series on what human behavior in fire is not. So after talking about what human behavior is, I think it's important to kind of talk about some of the misconceptions of how people act in fires, and to try to kind of break those down a bit and talk about why those aren't really the case. And the first one is a really important one, the ideal situation. And so there are some there's a misconception out there that people are very, very efficient in a fire situation. And what I mean by the ideal situation is they get into a building. It's a very well-defined procedure. The procedure is implemented with current, accurate information. And because of that, the occupants respond very promptly to the instructions provided. And once the instructions are initiated, everyone gets up and moves directly to a place of safety. And all of the routes are used very efficiently. And I just want to show kind of a video of that, this kind of ideal situation myth here. And so as you can see, the fire alarm has gone off. Everybody just gets up at the same time. They walk very efficiently. There's no, someone's grabbed the flag, as you can see, and movement is immediate, and there are all the exits, and everyone seems to know about all the exits. And it's a very efficient evacuation. And what I'd like to talk to you about is this is a very ideal situation. This almost never happens. And it's kind of like a spoof on what we'd like to happen. And I think we can try to achieve this. And the more accurate information we provide to people, the more credible information, the more accurate it is, the more we provide the appropriate information to people, the closer we can get to this. And I would very much agree with that. But this is really not what we should be planning for or expecting in any sense in any way. It's very likely that there will be some delays. It's very likely that people will wonder what's going on if they hear an alarm. They will talk to one another about what's going on, especially in a movie theater, as this might show here, or a show. Some people might actually say, "Well, do you know what that is? Is that a part of the show? Is that a part of the act? Is this a part of the movie? Is this really going on? And is this something I really need to do something about?" And especially if you're sitting in a movie theater, you've paid to see the movie or you've paid to see the show, it's going to take a little bit of prompting from the building alarm message, or even having someone come in from the management of the theater and actually prompt people to move, because we've paid for the movie, we're sitting down, we're watching it, and in some of these situations, or especially in this context, it actually is going to take us a little bit more to actually believe that something credible is going on and that we need to do something about it. So although this is a nice situation, and we try very hard to get to this place where people evacuate immediately and promptly, this is not the norm. And also the ideal situation where people use all the exits evenly, again, this is not the norm. What I was talking about in the previous module is that we very much move toward the familiar. So the exit in which people came into this movie theater is more likely the exit that they're going to use to evacuate. And so some of the exits in the back that we almost never use to get into a theater, as shown in this example, it's probably not going to be used very widely unless there are people in that movie theater directing you to use that exit. So there are ways in which we can get people to use the exits more evenly, but some of these things have to be put into place, and it's not just going to be that easy, like you sound an alarm and everybody just kind of moves in a very ideal situation. Okay? The next is the panic myth. Okay? And human behavior in fire is not dominated by panic. And I want to read a little bit here from my notes about how the media helps to perpetuate the panic myth. Okay? Following the Beverly Hills Supper Club fire in 1977 in the USA, the Sun's headline was "Panic Kills 300." The Daily Mail had pages about 200 feared dead in the Kentucky club fire, many trapped in panic. And panic has begun to kind of be expected from journalists in the U.S. and maybe abroad. So much so that after the emergency landing of Flight 1549 in the Hudson River, and that occurred on January 15th, 2009, the CNN journalist asked a passenger, "All right," and I quote, "all right, So then what happens? You hit the water. Do people start to scream? I know there were a lot of people, you say, praying, but was there a sort of panic that developed? And the interviewee answered, I don't recall panic really at all. And so there's kind of this myth, and I believe it's perpetuated by the media, and also it's perpetuated by some of us who believe that they've panicked when it actually hasn't been the case. And it actually causes some consequences, some negative consequences. And so what do I mean by panic? And by panic, I mean that behavior that is antisocial and competitive. Okay? It's reaching safety at the expense of the safety of others. And from what we've seen by fire in building fire events, this is a rare occurrence. What is most likely the case is that individuals perform altruistic behavior. And what I mean by that is helping each other rather than competing with each other, especially at the expense of others' safety. What normally is the case is that people take time and try to help one another, even if they don't know the person, at the expense of their own safety. Now, there are conditions in which panic has been seen to occur, and I have a few of these written on the screen, actually, by Wenger, Dennis Wenger, and also Janice and Mann wrote about this, that there are conditions in which have to be in place for panic to occur. It doesn't have to occur, but this is when panic could occur. And these are that danger is perceived as a specific threat, and this results in a social crisis. Limited escape routes exist, and they're rapidly being closed off. People believe that escape is possible, and that competition starts to occur rather than cooperation. And so competition is actually necessary for escape. And there are a lack of ties to other individuals. And so these are some of the conditions, these are the conditions stated in which panic might occur, but we just don't see it very often in building fire events. And that's really important because there are consequences in which, there are consequences of this panic myth, okay? So I talk about a couple slides ago where the media asks, did panic occur? Now, sometimes the media has asked, or other people, interviewers or others have asked, so did you see any instances of panic? Or have asked, what happened in that building fire event? And sometimes people will say, well, I just panicked. It was terrible, I panicked. And then when you ask them a little bit more about what they did, they actually didn't panic at all. They say, well, I went to get my child, and my child was crying, and I put them over my shoulder, and I went to get my purse, and then I left the building. And that's actually not panic at all. They might have felt a higher level of arousal, a more physical kind of level of arousal, but that is not what we're considering panic here, which is the competition at the expense of others' safety. But once you start to kind of get into this panic myth and this kind of cyclical process of believing that panic occurred, you can see that people report that they panic. And then another issue is that emergency officials start to believe that panic is a normal response in fires. Okay, we know it's not, but if emergency officials such as building managers or fire marshals that have to design emergency procedures for buildings, if they start to believe that panic is a normal response, and actually this has been the case in the past, then what happens is that emergency information begins to be withheld. What I've heard from in the past is, well, I don't want to give people information about what's going on. They'll just panic. And that is exactly the opposite. If we don't give people information about what's going on, then I'm not going to say panic can happen, but people can start to get worried. They can start to get upset, and they start to actually look for more information themselves. So they start to do more information seeking. They start to ask people what's going on, and that takes time. That takes precious time away from their own safety, whereas if we gave them more information, right, if we told them what was going on and gave them credible, accurate information about what was going on, and it was consistent with everything else they were seeing and hearing, then they actually are more likely to take appropriate, efficient, safe responses in a fire. Okay? And so when we go through this loop and we worry about panic and we don't give people the right information, then the problem is that human response becomes delayed and inefficient. Okay, if we believe that people will panic, so we don't give them the right information, so then they don't have any information or not enough when something happens, then they're more likely to delay their response and potentially not take the actions that are safest for them. So we have some real serious consequences if we believe that panic occurs. And as a researcher in the field of building fires and even actually other disasters, we just don't see panic very often. It's a very rare occurrence. Okay? Another myth that I'd like to talk about is role abandonment. And this kind of comes more from the disaster realm, but I think it's still appropriate for building fires. And the definition here is that emergency officials abandon their post before or during a disaster. And here we're talking about building fires. And the thought is that they have a role conflict between their professional duties and their desire to take care of themselves and others, like their family. And after studying over 100 disasters, they didn't see role conflict as a serious problem. Dines and Quarantelli didn't. And so I asked kind of the audience, how can we relate this to fires? And we have some people in building fires that take some very serious roles. For example, a building manager might step into a more serious role when a fire occurs. We also have fire wardens. And their job in some maybe office buildings is to make sure that the people are accounted for, they put on their vest, they get their clipboard, and they walk through the halls maybe and make sure on their way out that everyone has reached safety. So they've got certain roles in building fires. And the question here is whether or not they'll actually perform their roles, or will they abandon their role when push comes to shove. And we also have firefighters, right, who continually respond to building fires and perform very important life safety roles in addition to putting out the fire, right? And they have search and rescue important responsibilities. And so we just don't see the type of role abandonment in disasters, and we shouldn't be expecting that in building fires as well. Fire wardens do take their role. If they're there that day, they do take the role that they're assigned and the responsibility. Some people even step up and they don't have a role, a previously assigned fire role. For example, building managers or staff of a restaurant, for example. Sometimes we see people who didn't even have a pre-fire or a pre-fire assigned role step up and take on those roles during an actual event. So we're actually seeing the opposite of role abandonment. We're seeing more people stepping up and helping others in a building fire. And the consequences of thinking that role abandonment occurs is that we may reduce the responsibility that we give to those who are best suited for the job. If people are willing to stand up and take certain roles in fires and make sure that the procedures are being followed appropriately, and we know that they're going to be there, and if they're there that day, we know they're going to step up and do that, then we want to make sure that we give them the role and not be fearful that their role will be abandoned when push comes to shove. Okay? And then finally, there is the myth of disaster shock or inactivity. And the definition of this is disoriented thinking, a general insensitivity to cues to the immediate environment. Okay? And that's kind of just having something happen and just being so much in shock to the immediate environment that they're not actually able to make any decisions or move. Okay? And there are three important conclusions that we've seen in past research, that this appears most frequently with rapid onset, low forewarned events, okay, where there's widespread damage, injuries, and death. Only a small proportion of the population is affected, and this lasts only for a small period of time, maybe a few hours, maybe not more than a few days. But then again, how is this relevant to building fires? And we just don't see this kind of shock and inactivity. I'm not saying it never happens, but it's not the norm. It's not the dominant behavior that we're seeing in human behavior in fires. Okay? It might be some people who are going through some initial shock that they have to kind of get through that initial period before they start making decisions. And these are the people who are going to be most intimate with what's going on. For the people who are kind of outside of the fire area, maybe a different floor, but they still need to evacuate, this is where we need to actually have them believe that something's going on. These are the people we're going to need to prompt. We're going to need to kind of provide them with a little bit more intensity, that they need to do something about it because they're not witnessing some of these more intense cues. For the people who are more intimate with the fire event itself, this might be kind of an initial problem that they have, but just really not the dominant reaction in building fires. And a consequence, if we believe that this is the case for the majority, then we won't anticipate that individuals help themselves or others, which is really not the case. And something as serious as what happened in 2001 in the World Trade Center disaster, we were seeing people help their fellow coworkers, some people who didn't even know each other, in some very, very serious, very dangerous situations. And so if we believe that people are in such shock that they're not able to save themselves or others, we may start to overcommit emergency responders, right? If we feel like people can't take their own action and help themselves or others, we might have the fire department spend so much time in search and rescue and not enough time in taking care of the fire. And this really is something that we just don't see that often. Instead, we see the opposite. We see people helping each other. We see strangers helping each other. We see people helping themselves. And so this is an important myth to kind of debunk so that we understand how people act in building fires and that we can commit our emergency responders to putting out the fire and other activities. So to end this second module of human behavior and fire, I wanted to just reiterate that there are certain beliefs or myths about human behavior that should be further explained and even debunked. And I hope I've done that during this module. The ideal situation is not likely to occur. We've talked a little bit about when it could occur and some things we could put into place so that people act more quickly, more efficiently. But this is really not the norm in most cases, and we need to expect that. And also, panic, role abandonment, and disaster shock are rare. Hi. For the third module of the Human Behavior in Fire series, I'd like to talk about types of human behavior in fires, specifically focusing on incidents and case studies where we have learned about how individuals react in building fire events. So the first fire that I'd like to talk about occurred in 1911, and that occurred in New York City at the Triangle Shirtwaist. That was actually called the Triangle Shirtwaist Fire. That was a business occupancy where 148 garment workers died, either from a fire or from jumping to their deaths. The Triangle Shirtwaist Company was owned, the top 3 floors, actually, of the 10-story Ash building in New York City. And the Triangle Shirtwaist Company employed 500 mostly immigrant women. The fire developed on the 8th floor, and it was possibly sparked by a lit match or a cigarette, or because of faulty electrical wiring. Most of the workers were alerted on the 8th and 10th floors, and they were able to evacuate. But the warning did not get to the 9th floor in time. On the 9th floor, there were 2 doors leading to the stairs. One was filling with smoke and flames, and by the time the seamstresses realized that there was something wrong, the other door was locked. Bodies piled up on the stairs. Others died using external staircases which collapsed, and they were poorly structured, and many ended up jumping to their death. The next fire I talked about a little bit in earlier modules when I talked about panic, and this is the Beverly Hills Supper Club fire in Kentucky that occurred in 1977. This fire took 164 lives. Because of overcrowding, almost 3,000 were located in the club that night, and additional guests were seated on temporary seats in the cabaret room. The fire actually began in the zebra room. The management of the building tried to control the fire with 2 fire extinguishers to no avail. The fire spread very rapidly. The building had no sprinkler system and no fire alarm. A busboy made his way to the cabaret room, and remember that was the room that was already overcrowded, to warn guests of the fire. Some followed his instructions, while others thought that he was part of the comedy act. And remember in the first module where I was talking about the process that we have to go through before we act in a fire? And here we've had a breakdown of the processing of information because of where they were. They were in a supper club where there was acts going on, and so it wasn't unbelievable that they would think that there was some comedy act going on. And again, our first instinct in any building event, fire event, is to believe that we're not at risk. So because others thought that the busboy, when he was saying that they should leave, was part of the comedy act, there was a delay in them actually taking action. 2 minutes after this busboy's warning, the fire made its way into the cabaret room, producing thick smoke, making it difficult to see and breathe. So deaths were blamed on building features, such as poorly marked exits. And again, if they're poorly marked, people aren't going to know about it. And they really would probably be more likely to leave the way they came in anyway. And deaths were also blamed on flammable carpeting and seat cushions that emitted toxic fumes when burned. The next fire I'd like to talk about is the MGM Grand Fire in Las Vegas that happened in 1980. This fire took 85 fatalities and 650 were injured. This was a 26-story hotel and casino, and fire broke out just after 7 a.m. in the deli area, which was on the ground floor. That was a restaurant in the hotel. Openings and vertical shafts through the elevators and stairs and seismic joints allowed the toxic smoke to spread to the top floor due to faulty smoke dampers within the ventilation ductwork. Because of that, toxic fumes circulated throughout the hotel's air circulation system. Most deaths occurred in the stairwells where the doors locked behind each person, and the victims died of smoke inhalation. Others took refuge in hotel rooms, trying to preserve their lives by placing towels around the doors, notifying others, and putting wet towels over their faces. No information was provided. There's no alarm. The hotel's alarm system was manually activated, and because no manual switches were in the casino and restaurants, the alarm was not raised. And actually, I've spoken with a gentleman who was in that fire, and he remembers turning on the television set, actually, to see if he could find out any information about what was going on about the fire at that point in time. It was very, very interesting kind of documentary where, because there was no information given by the building, he tried to find other ways to see if he could find out any information, and he turns on the television to see if maybe there was a news station covering the event. So it's just a very interesting tidbit. Okay, on to the next fire that I'd like to talk about here, and I have a video to play as well. This is a fire that occurred in the Bradford City Stadium. The fire broke out during a soccer match, or football match if you're in the UK, between the home team Bradford City and Lincoln City, and 56 people died that day, and there were 200 injuries. The fire was believed to have started by a fan dropping smoke materials, a lit cigarette, down into the gaps of the stands, and it fell into an empty space under the main stand, into a pile of trash that had accumulated over the years. People did evacuate onto the playing field, and you'll see that in the video. You can also see in the video how the fire spreads rapidly throughout the wooden stands. It engulfs the entire main stand in about 2 minutes. There were others seated toward the rear of the stand, and they became trapped in this fire. Fatalities were found along the back corridor of the stands, overcome by toxic smoke near the turnstile that was locked, actually, to prevent unauthorized access after the game had started. And there are also other issues here associated with this event, primarily that when you have sports events or something like that, you have to assume that the people in the stands are also potentially intoxicated by alcohol, very excited about what's going on in the event, and not as likely to be kind of noticing that a fire is taking place. And so you'll see that when I play the video starts and you can see the soccer match a little bit, and then off in the background you can see kind of the flames starting. I'll try to circle that with the pen using the screen. And then you can actually see some of the fans staying there and actually cheering, continuing kind of to cheer on the fact that this fire is occurring and not really realizing just how dangerous this can be. And very dangerous fire. And then I will talk about in the last module actually of my the series of human behavior and fire, how this event has actually help to change codes and standards for stadium fires. Okay, so the next fire that I'd like to talk about revealed the importance of telling people exactly what's going on in a fire event. So a fatal fire in London took place at the King's Cross station, which is a major interchange on the London Underground, excuse me. The fire began in an escalator shaft serving the Piccadilly line, which was burnt out along the top level, the entrances and the ticket hall. The escalator steps and sides were partially made of wood. The fire was probably caused by a commuter discarding a burning match, which then fell down the side of the escalator into debris underneath. The fire started beneath the escalator, spread above it, and then flashed over and filled the ticket hall with flames and smoke. Adding to the speed of the fire was the 12-mile-per-hour wind caused by an eastbound train arriving in the station as the westbound was leaving. So the deaths, which were 31 in total, they were unable to escape the ticket hall before succumbing to the effects of smoke and heat. And during this fire, conflicting information was provided to the individuals involved. The police, on one hand, were telling people to evacuate via the ticket hall, since that was the evacuation plan, and that was where the problem actually was, even though the fire was up there. And staff of the underground were telling people to keep away from that area, to stay below. And so since then, we've had a lot of work in the area telling people exactly what was going on in the fire and how important it is to provide people with consistent information rather than conflicting information. The next fire I'd like to talk about is the World Trade Center disaster that occurred in New York City in 2001. We've got almost 2,800 fatalities that occurred in this disaster. This was the most significant high-rise evacuation of modern times, and it was studied in detail as part of an investigation carried out by the National Institute of Standards and Technology, where I work. And I was actually a full-time employee assigned to this project during the investigation. And so we had in both buildings, once the towers were hit by the planes, in World Trade Center 1, we had stairwells destroyed by impact. And in World Trade Center 2, when the building was hit 16 minutes later, also, all 3 stairwells were taken out, except for one of them, which was passable by some people. There was about 16 people who made it past that stairwell, past the rubble, and that stairwell was passable, but that was until the buildings collapsed. We have an issue of conflicting guidance in WTC2, where at some point people were told to stay in their offices, and then a little while later were told to evacuate the building completely once a little bit before their tower was hit. And then in both cases, after both towers were hit, there was no ability to communicate with the occupants because of the damage that the planes had done. We saw in both towers delayed initiation. Even after the plane was hit, Tower 1 was hit first, there was delayed initiation, and some people stayed until the second tower. Their next door neighbors were hit with a plane. And that had a lot to do with whether or not they should leave, what guidance they were given, which was in some cases very little due to the fact that the alarm system was not available after the plane had hit the tower. We saw about 6% of occupants who were mobility impaired. right? Some being carried very, very long distances throughout the stairwells because elevators were not available after the towers were hit. Others were waiting on refuge floors that were lower in the building, okay, and then eventually both towers collapsed. There were transfer corridors, which provided some confusion for some individuals. And then we had firefighter counterflow in both buildings. And what I mean by this is the fact that because elevators were not available, and also because in some cases this may have not been the procedure anyway, that firefighters and building fires have to use the stairwells in some cases to get to where the fire is located. And these are the same stairs that occupants are using for evacuation. And so there's kind of some congestion going on, and in some cases occupants were moved to other stairwells to make room for firefighters moving up into the building. And just generally in both towers, people traveled very long distances in stairs. Elevators are not available in World Trade Center 1, and they were only available for 16 minutes in World Trade Center 2 before the tower was actually hit 16 minutes after 1 was hit, just causing very, very long travel distances in stairs for people coming from the top half of the building. Even if you're coming from the 20th or the 30th floor, it's still a very long distance to travel on stairs. The next fire that I'd like to talk about is the fire that occurred in Rhode Island in 2003 at the Station nightclub, where 100 fatalities occurred. Great White was performing that night, and pyrotechnics set off by the band's tour manager ignited the nightclub's flammable soundproofing foam. The flames were thought at first to be it wasn't kind of clear if there were just lights that were happening at the back of the band or if they had actually ignited anything. But very soon the fire reached the ceiling quickly and smoke began to spread in the dance area. The alarm did sound, but exit usage was uneven, with most people attempting to use the exit door in which they came into the building. And this makes perfect sense. For the most part, people are going to be familiar or most familiar with the door that they use to enter the building. And this led to a crush at the front exit. So what I'd like to show you next is the exit usage of the building. And so we have here, right, that most of the usage occurred in the very main exit of the building, right? We have 20 people, we've got the most using kind of this front exit here, and even people using the sunroom windows. And when it came to when the conditions were so untenable, people were actually taking these windows out and using those windows as exits. This door didn't stay available for very long. We only have about 20 people using this platform exit door. It became untenable very quickly. And then not as many people using these exits on the left here, especially from the kitchen, most likely because it's difficult to know that at the other end of the kitchen there's an exit available. It's likely that most of the occupants in the building are not going to know about the kitchen exit unless they're told about it by building staff or something like that. So it makes sense that most people were using the exits that they were familiar with, or at least gathering at that exit, and even though it was congested, started kind of taking out the windows from the sunroom because that's where they were waiting to use that main exit. And if we could take off the, thank you. Here I'm just showing the location of the fatalities. There were fatalities that occurred here when the conditions became untenable or crush conditions. One of the members of the band perished, and then we have people in the back here. I'm not 100% sure, their stories, of course, but it's likely that they were trying to find other ways out, and then just could not find a way at that point, and then died in the back offices and restrooms and things like that, potentially looking for an exit. Okay, and so the last is an experiment that I'd like to present to you. And this was an experiment performed by Latané and Darley. And this is what they called the social inhibition experiments. And their subjects were between 17 and 21 years old, and they were all males, and these were graduates and undergraduates at Columbia University. And they had asked these subjects to complete a survey. And so these subjects volunteered to complete a survey. They didn't really know that they were part of an experiment until after the fact. And they were supposed to be completing a survey on the problems involved with life at an urban university, okay? And so what happened is upon turning into the first page of the survey, they were sitting there, they got through the first page, and once they turned to the second page, the experiment continued, and titanium dioxide, which is white smoke, started to be ingested into the room. And the question was whether the volunteers would stop their survey and tell the receptionists that something was wrong and that they kind of to evacuate that space. Once the smoke started kind of being injected into the room, the question was whether or not they would stop their survey and kind of make someone aware of what was going on. Or would they stay in the room and kind of just continue with the survey. And there were three different modes. The first mode was, it was the person just by themselves, and I'm about to show you a mock video of what the experiment looked like. This is not the experiment itself, all right, because what happened in the experiment itself is that for some people would wait so long, the white smoke was so thick, they actually had to kind of wave it away from their survey because they were still sitting in the room through that. That isn't really shown in this experiment, this video that I'm about to show you, but it actually happened in the experiment. So sometimes the person was just by themselves. They were the only one in the room filling out the survey. That was one scenario. The second was that the subject was in a room with other people that they call passive confederates or passive participants. And these are people who were told to just sit there in that room no matter what. They were part of the experiment. And so they were supposed to continue filling out their survey, and then we get to see what the subject does. And that's the video I'm about to show you. And then the third is 3 naive subjects were put in a room, and none of these people knew what was going on, but they were together, and we're supposed to see kind of what their reaction was, if alone, with passive confederates, or with a group who also didn't know what was going on. So I'm about to show you, let me move forward here. I'm about to show you a video, a mock video. Again, this is not the actual experiment itself. These experiments occurred a long time ago. But this is just to kind of show you an example of a subject with those passive confederates. So these are people who are part of the experiment. They're not supposed to move. They're supposed to continue doing their survey no matter how thick the smoke got. And we'll see how long this subject takes to respond. Okay, here in the first example, this video shows a woman alone. And again, this is just the mock video, not the experiments themselves. But what it's meant to show is that when someone was alone in the room, they actually most likely went over to figure out what was going on and then left very quickly. She doesn't take a whole lot of time to figure out that there's smoke being pumped into the room and that there's something she needs to do about it. And so she leaves almost immediately. And that's a really good example of what we saw from these experiments for the people who were alone. Now here's an example, a mock video of someone with 2 passive, well, I'm not sure how many other passive confederates were in the room with her, but she's the only person, she's the only subject in this example. All others were told to just sit there no matter what and continue taking their survey. So the clock starts when she realizes that there's smoke being pumped into the room. She does look a bit concerned. Okay, looks around to see if other people notice. Other people, again, they're told to, as part of this experiment, to continue working and to not respond. So she doesn't have cues from anyone else upon which she can act. So 5 minutes later, in this mock example, which we actually saw this kind of stuff in the experiments, she's still sitting there. All right. At this point, the smoke is much thicker than what's being shown in this video here. and people are actually waving the smoke away from their surveys as they try to fill them out. 20 minutes, she's still in the room. And she actually is now, the experiment has ended, especially in this mock video, but for the Latine and Darley studies, they would end it after about 15 minutes. And what that is showing is the results here. And that in the cases where the person, the subject, was alone, they were very much more likely to report that there's smoke being pumped into the room, head out to the receptionist, and see, let that person know there's something wrong here. But in the cases where we saw the second half of that video, where the subject was with two passive Confederates, they were very much less likely to act on their own, especially when they were surrounded by other people who were not acting. They were continuing to do their survey, they were not responding, and so in the cases of a fire, in a real fire emergency, if there are people around us who are not reacting, we also are more likely to follow suit and not act. And so that's why it's important to have people in a fire event who are maybe fire wardens, who are told to act no matter what. As soon as you hear a fire alarm or anything that's wrong, you act, because then it's more likely that people are going to follow suit and act with you. It's less likely that someone's going to put themselves out on a limb, especially in a fire experiment, especially in a fire event, unless the cues are so intense. And here we've got white smoke being pumped into a room, and only 1 out of 10 subjects in the passive Confederate scenario actually responded. That is really significant, showing us the effect of having other people around us not acting. And even when there were 3 naive subjects, okay, what this tells us is they're a little bit more likely to act than the second scenario, but less than if they're alone. They probably spend some time talking. What do you think that is? Should we go out and find out from the receptionist? So it's kind of, when we're alone, we don't have we're not inhibited by looking silly or what other people are doing, and we're more likely to act than if other people are around us. And that's really important to understand in a fire emergency, because if we have a scenario where it's not very clear and no one's taking the first move to act, then it's kind of likely that people are going to just continue working. So we need to make sure in building fire events where it's not so obvious that something's going on, but we need to make sure people get out. They need to have credible information, and someone needs to prompt kind of the evacuation to start. And so I'd like to end this module with a summary. I presented 8 case studies on how human behavior influences life safety outcomes, right? What people do, the information that they perceive, what they think about the building, the familiarity with the building features, if the exits are clear, and if the exits are available or locked. All of these things can influence how people respond in a building fire, and ultimately their life safety outcomes. We saw some very serious events with long evacuation paths, or kind of very crowded, congested exits where people were using the familiar exit, or instances where information was given but misconstrued. All of these things can lead to life safety outcomes that are very negative, like deaths or injuries. Okay, I tried to show all different types of buildings and scenarios, various years, starting from 1911 with the Triangle Shirtwaist Fire to things that happened more recently, like the Rhode Island nightclub in 2003. Human behavior is still a very, very important component to understand in order to improve building safety in fires. If we don't understand how people are going to react to our building design and to our alarm systems and to the fire itself, we're not going to be able to understand the things that need to be put into place, and this is what I'm going to be talking about in the next module, so that we can improve the safety in our buildings, so we can ensure that people reach safety quickly and effectively, as fast as they can. So for our last module in the Human Behavior and Fire series, I'd like to talk about how to transition everything that we've just learned in the last 3 modules to practice. And essentially, I'm asking you, why does all of this matter? And I'm going to tell you the answers to that. So why do we care about what people do in fires? Why do we care about all these case studies and learning from previous events? And the point is, we want to be able to make buildings safer from fires in the future. And to understand how people reacted and why they reacted that way, we've been able to make changes along the years to improve the safety of buildings through a lot of different ways. And each one I'm going to go through. So the first is through improving building codes and standards. So in 1903 and then into 1911, actually that was the year that the Triangle Shirtwaist Fire happened, the NFPA created the Committee of Safety to Life, which is now our Life Safety Code. And so this provides requirements for the egress system design in all types of buildings. And this is a very, very important code. We continue to make updates and changes to it as more and more things happen in the United States and around the world. And this is the way that we can ensure through building codes how to design our buildings safely for building fire evacuations. Okay, and in 1942, there were some updates to this, providing requirements for emergency lighting, exit signage. So what signs should we be placing in buildings so that people know where the exits are located and where they should be located? Providing capacity signage, how much capacity should be in certain areas of the building in certain rooms. The importance of outward swinging doors rather than inward swinging doors to help with, to alleviate congestion through evacuation. And then having swinging doors on either side of revolving doors, and then the importance of panic hardware. Okay? And then as we moved on, there were some changes to building codes, eliminating places of eating and drinking as an exception to places of assembly. And then into the 70s, we were looking at retroactive alarm and sprinkler requirements. So some of the case studies and incidents that I talked about in the previous module talked about not having alarm systems, or the alarm system didn't function, which is different from not having an alarm. And then not having a sprinkler system in the buildings, which is a Rhode Island nightclub. So since then, there's been kind of retroactive. There's been kind of even more codes and standards put in place for updating the codes so that buildings are equipped with both alarm and sprinkler systems. So in 1985, and this might sound familiar from our Valley Parade fire that we talked about in the grandstand, the prohibiting of the construction of new wooden grandstands. So constructing grandstands with different materials other than wood, and also having smoking banned from all underground stations, including escalators, and that kind of as an action taken from the King's Cross fire, and then wooden escalators being replaced with steel escalators. So some things that came out from the World Trade Center investigation were the requirement of fire service elevators for buildings above 150 feet, and then the permit use of occupant elevators in place of the third stair for larger buildings above 420 feet. And this is really important because there's been a lot of work in providing standards on the use of occupant elevators in buildings, and so now this is being put into the code as an option for very tall buildings to help with the evacuation of people in addition to people with mobility impairments, all occupants really of buildings that are very tall. Because we talked about in Module 3 during the evacuation of the World Trade Center kind of these long distances that people had to travel to evacuate the entire building. And then, as I mentioned in the previous slide, sprinklering of all new nightclubs and retrofit of existing nightclubs with greater than 100 people as a result of the 2003 Rhode Island nightclub fire. So what's important here is that we're studying these types of events to try to understand what happened and to see if there are places in the codes and standards that we can make changes to try to make sure that these things don't happen in the future. Another reason why we try to understand human behavior in fire is to improve procedures and training for buildings, so specific buildings. And so we want to make sure that we design more efficient and effective procedures. All right, we'll want to understand how people react in building fires so that we can put the most appropriate procedures in place. So what events are even going to be possible in our building? What types of fires should we expect in our building? And then how could people react to those fires? And then how can we best use our signage? How can we best use fire wardens or staff to make sure that people take appropriate and safe actions in a building fire? Next, it's important to familiarize occupants with the procedures. So this includes training and evacuation drills. So it's not enough to put a procedure in place that we think is great, that's going to provide people safety. We have to make sure that the people in the building understand it. And so we know from previous studies of human behavior in fire that training works. That people, when they understand and move through the building and participate in an evacuation drill, that they start to understand where the exits are located. It might not be the main exit, but it might be the exit closest to them, and that's where training really helps. All right? And we also want to help guide occupants to follow the procedures, so the use of well-trained staff to guide people when it might be confusing or when we want them to use more than just the main exit, and providing appropriate fire alarm systems with the addition of voice communication. And this is very important. So it's not just important to provide a bell or a siren in a building fire. It's also important to provide information. So people need to know what's going on, what they need to do about it, who needs to act, so what floors, what people in the building, and when they need to act. That's also very important. Now or wait here on your floor, more instructions to follow. That's also a really important one. And then also who is providing the message. And so it's really important to make sure that the message is provided by a credible source. And it's also important for you to understand who those credible sources are for the people in your building. And we talked a little bit about that in the first module of this Human Behavior in Fire series. So we know from our first module in this series that people will seek information. They need to know what's going on. The more information we provide them, the better. So I would ask kind of the people who are listening to this module, which one of these two sounds, which one of these two alarms which one is better than the other? So let me play the first one first. Okay, that's the first sound. And then here's the second one.
Attention, attention. Evacuate the lab by the nearest safe exit. Leave the lab immediately.
Okay, so the difference between these two is that one provides just a sound and the other provides some information to the occupants. It doesn't provide as much information as we would like. It says to exit to the lab and to the nearest. It doesn't really say much about what's going on, so I would actually add a lot more to that second message. But the important part of what I'm trying to say here is it provides information, because a sound is never really going to be enough. There are going to be people in the building who aren't going to know what that sound means. And when you start providing some information, it provides credibility to that sound, which should act more as an alert to grab someone's attention rather than the whole warning itself. So what's nice about that second WAV file is that it provided the sound initially, it got people's attention, and then it provided some additional information to them about a little bit about what's going on and more about what they should do. So information is key in a building fire event. And so we know that. We know that from studying kind of what people have done in the past. They're information seekers. We know this already. And the more we can provide them information in a building fire, the better response they'll have and the safer we can keep them. Okay? And another reason why it's important to kind of understand human behavior in fire is because a lot of fire protection engineers are always providing assessments of a new building design or a change in occupancy, or they might change some part of the building, and then they're asked to kind of assess, is this still safe for building occupants? And what engineers will do is they'll compare what's called the required safe egress time with the available safe egress time. And the required safe egress time must be some factor of safety less than the available safe egress time. And the way that these are calculated is the required safe egress time. You have to know a bunch of these different aspects. And that's really kind of what I've been talking about, these human behavior and fire modules. It's an understanding of what the people will do and how long they take or are required to take to evacuate the building or reach a place of safety. So in any building design, the engineer must kind of calculate how long it will take occupants to reach safety. And to do that, they need to know the number of people in the building, their location, their occupant attributes, the activities that they'll be performing before a fire occurs, and the personnel that's available maybe to guide people to certain exits. And this is really not as well established process as this one might be, because we just don't have a lot of data on this. That's a whole nother module for some other time. But it is very important that we continue to do research in human behavior and fire so that we can populate some of these questions that are continually asked as we calculate our RSET, or required safe egress time. But this is one aspect of understanding how safe a building is. The other aspect is understanding what the fire's doing. And that's the available safe egress time. And that's how long will it take in a building until the conditions become untenable. And so what the engineer needs to know is the heat release rate of the fire location, whether the doors are open and closed. So in one case, we're kind of calculating how long occupants take to evacuate or to reach a point of safety. And in the other case, the engineer is calculating what the fire's doing, fire growth, and spread throughout the building, and at what time does the conditions become untenable in areas where occupants are located. And if that overlaps, if occupants are still in the building and the conditions have become untenable, then something needs to be changed with the design. It's not going to be safe enough. And so what we do is we use safety assessment tools or computer models to assess how long occupants take to evacuate a building. And we try to get as accurate as we can. There's a lot of data potentially missing, and we have to keep doing our studies of evacuation from buildings. But what the important part is, we put kind of the building design into these computer models, and we put our understanding of where the population might be located, and then we try to calculate how fast it will take occupants to evacuate the building or the building design or the area of the building. And the way that we do these, as you can see, I've just got some videos. I have an overhead view here of the Simulex model, and it's just kind of showing kind of an overhead view of occupants evacuating through a building design. The one down here is from the STEPS model, and that's showing kind of a 3D view of a high-rise structure. And we have to provide to these models like how fast people move, on what types of surfaces, but also there should be a lot of behavior in there too, the actions that people take during the building fire, how long they might delay information seeking. A lot of this behavior is not so accurately captured by these models. And so it's important for us to continue to understand building fire events from an occupant standpoint, so we can continue to improve these models that are used every day to assess a building's design safety levels. And so this is another reason why it's important to understand human behavior and fire. We need to keep understanding how people react in certain situations, in certain building types, with certain types of fires, so that we can incorporate these into these simulation tools that we use on a daily basis to calculate building safety levels for our building designs. And here I'm just showing one other kind of 3D view of a more sophisticated model here called Building Exodus at the University of Greenwich, and they've actually incorporated at what point after smoke obscuration levels or smoke levels that a person begins to crawl. And so it's important for us to understand how fast people move when they crawl versus when they walk. And this is additional data that is needed for these types of models. And so this model also tries to incorporate some behavioral aspects of a building fire, and it has started to kind of incorporate wayfinding and familiarity and things like that, and the influence of signage on our route choice decisions. And so our understanding of human behavior in fire, which is so important for not just building codes, not just design of evacuation procedures, but also these models, because developers are constantly trying to improve these and make these more accurate for engineers to use. And we need to kind of keep understanding how people react in building fires so that we can keep improving these models that engineers use on a daily basis. So as a summary to our last module in this series on human behavior in fire, I tried to provide an understanding of how human behavior, how an understanding of human behavior can help improve life safety of fire events through the improvement of building codes and standards. When an event happens, we try to learn from it and see if there are ways in which we should improve our building codes and standards. And I gave you some examples of how we had done that along the way. And also an important reason to understand human behavior in fire is because we're constantly developing more informed procedures and training for buildings and for building occupants. The last is the creation of these safety assessment tools, or these computer models that engineers use on a daily basis to assess how safe a building design is, or the safety levels provided by that building design. And it's important for these models or these safety assessment tools to have a true understanding of human behavior in fire. I think they're getting there. I think we've got a lot more work to do so that they can be improved to really incorporate how people react in building fires. And so I'd like to thank you for your attention through this human behavior in fire 4-part module. And as our discussion topic, as I mentioned in the very beginning of this human behavior in fire series, that I will be asking you to do kind of a 1 to 1.5 page paper on something that demonstrates the topics that I've covered over the last 4 modules. So here I'm asking for you to write a paper, again, 1 to 1.5 pages, that you describe one incident when you experienced a fire alarm. Could be a voice message, it could have been an equivalent fire cue. For example, you saw smoke in a building. And I'd like you to write a description about that event first, and then describe what you did. So please discuss what cues or information you received, what actions you took in response to that information, and more importantly, why you took those actions. And this is the why should be based on what you now understand about the process of decision-making and human behavior in fire. So think back to a time where you were in a fire drill, maybe. It could have been a false alarm. It could have been an actual building fire, an actual building event where you were asked to take safety or to take action. And I'd like you to describe that. I'd like you to describe a little bit about the incident, what information was provided to you, what actions you took, and then why you took them. And I'd like you to link that why back to what you've learned over the last 4 modules about human behavior in fire. I'd like you to analyze your own behavior and talk about why you took the actions you took. And if you might have gone in one direction, and even though you should have gone in another, let's think about in this paper why you might have made that decision over another. What information were you provided with? Were you provided with enough information? And if not, that might have led you to take maybe a less efficient route or a less efficient decision. Finally, if you've not experienced anything like this, if you've never been in a building fire event or a fire alarm or a fire drill that you can recall, I'd like you to produce a hypothetical scenario. So even if you haven't experienced something yourself, or you can't think of anything to write about, please then write about a hypothetical scenario that is likely to occur. And so, again, in that hypothetical situation, you can discuss what cues you would have received, what actions you might have taken, and why you might take those actions. And what I mean by a hypothetical scenario is one that's likely to occur. So it's very unlikely that you're going to be writing about a panic scenario. I'd like you to write about something that's actually could happen, or could happen to you. It would be ideal if you've written about something that you've done so that you can try to analyze some of your behavior. But if you can't think about anything, or if you can't recall anything and nothing comes to mind, then I just ask you to write about a hypothetical scenario. I don't want you to do both, do one or the other, and I'd rather you do something that you've experienced in the past. So thank you very much for your time and listening to these modules, and I very much appreciate your attention throughout these, and I hope you've learned a lot, and thank you very much again.
Well, hello. Want to provide another segment in our course of the effect of fires on people, property, and the environment. And today, the particular topic at hand is to look at the effect of fire on property and on the environment. So the outline for this particular week will involve looking at an impact of fire exposure on structures to see how a structure and in particular the load-bearing components will respond to fire, that is, respond to a heated environment posed by a fire. And then secondly, we'll want to take a look at the impact of fire and smoke and extinguishing agents on the contents of the building and also on the environment. So our first piece is to look at the effect of fire exposure on structures. There is some information in the literature that's available through the Fire Protection Engineering magazine published by SFPE. There is a website that provides the articles that is open to the public, and would encourage you to take a look at these articles for a little more information. They're relatively short articles that can be read fairly easily, not usually real intense in the way of the scientific principles that are involved and such. So that provides some very nice background and gives some insights into the engineering aspects in our field here, or in this particular topic of our field. So the first question we want to pose before we get into the details of looking at why structures potentially fail is to look at, so why is this important? And there are a few reasons why it's important. Certainly looking at just the overall issue of property protection is important, in that if a structure collapses because of fire, that usually then has associated with it a very large property loss as well, dollar value wise. But in addition, there are issues of wanting to have the structure stay up in order for the building occupants to be able to evacuate prior to the building collapse. And as emergency responders are dispatched to the building if there is a fire incident, having the building stay up and not collapse while the emergency responders are in the building is a very important issue, of course. There are different ways different ways we protect structures. That's part of what we'll talk about here. We'll mention with the array of buildings here. So there are a few of these buildings where the life safety aspect becomes an issue, and that usually is the case in high-rise buildings that take a fair amount of time to evacuate. So as we look at the new tower here, get myself oriented, sorry. Get the new tower in the Mideast that is a couple thousand feet tall. That's going to take a long time for people to evacuate from the top level onto the ground level. The First Interstate building, First Interstate Bank building in Los Angeles, and the fire that occurred in 1988, another high-rise fire. There weren't many people in the building at the time of the fire, but wanting to preserve the structural integrity of that building to allow building occupants to get out, and for that particular incident, for emergency responders to get in and control the fire, it was an important issue. There are other buildings like the cable TV headquarters for China, being here, being a rather innovative structure. The Olympic bubble for the swimming competition at the Beijing Olympics. We have our U.S. Capitol, where there's more than life safety. Now, if that building burns down, there is this historic building that has cultural significance would be lost. So there are those issues. I do have the basketball arena here as well on campus, where there's a life safety issue, where there are 17,000 people watching games, and it's going to take a while to evacuate that building. Having the roof collapse while the people are trying to get out would not be at all a desirable outcome, obviously. And again, there's the issue if there is a serious fire in this building, having the emergency responders to be able to get in and not to have to worry about the structural collapse would be a very important issue. So one of the items we want to talk about is the same level of fire resistance provided in all structures? And there's a rather easy answer to that, and the answer is no. One doesn't have the same level of fire resistance in all structures. There are some structures that have no formal fire resistance rating associated with them, and there are others, such as the high-rise buildings that we looked at, that may have several hours of fire resistance that would be designed into them. In terms of the U.S. codes and standards, the basis for the U.S. codes and standards and the basis for the fire resistance requirements in those standards really is expressed here. And you can see this comes out of a 1942 report from the National Bureau of Standards at that time. That's now called the National Institute of Standards and Technology. And there was a report, the BMS reports, or Building Materials Series, as they were called. So the BMS 92, one of the classic studies that were done in the early part of the 20th century, says here the subcommittee that was tasked to consider fire resistance requirements believes that the idea of designing some buildings for the full fire severity corresponding to the occupancy is a logical advance in fire protection engineering. So what that means is that the buildings should be, at least in principle, following this, they should be able to withstand a full burnout of all the materials in the space. All the materials in the space would be consumed, and the building should still be standing. A few years prior to this BMS report, Simon Ingberg put together a hypothesis of how long a fire will last. What was its severity measured in hours, according to Ingberg's hypothesis? And this was dependent upon the fuel load and how big of a building area was involved. Fuel load is one of the characteristics that helps define the occupancy of the building, that is the use of the building. And is that building a warehouse, or is it a restaurant, is it a library, an office? All have different amounts of fuel in them. And basically, the more fuel, the longer one would expect a fire to stick around or to burn. And that's also dependent on so how big of an area is there to burn before you achieve the burnout. So we have these different levels of fire resistance that are required according to the building codes and standards in North America, and I think applied to many countries similarly. So as we look to then achieve a particular level of fire resistance, you say, so how does this work? How do you do this? Well, we want to first look at, so what happens to structural elements when they heat up? And I'll say the one common item that we can say for all structural materials, whether it's steel or concrete or masonry or timber elements or whatever the structure is composed of, all those structural materials lose strength with temperature. There isn't one of them that is able to heat up to whatever unlimited temperature and maintain its structural integrity. So the question becomes then, so how quickly does the strength decay or decrease with time, with temperature, that may relate to time in terms of fire continuing to burn. So how much of a decrease is there, and at what temperature do significant changes start to occur? For steel, I show a graph here of the yield strength, or the strength of steel in terms of its load carrying ability, and also the modulus of elasticity, where the modulus of elasticity is as a parameter that's used in engineering to address how easy is it to deform or deflect, to bend a particular structural member. And those are two separate issues, two separate strength and how easy it is to bend a particular material or to get it to deform. And you can see for steel, there is this gradual decline. So it starts up at its ambient temperature strength. There's this gradual decline with temperature. And in terms of strength characteristics, if we look at the solid line, we have about half of the strength as compared to ambient temperature, up around, well, let me draw it on here. So we're about half the strength, and we're somewhere in the neighborhood of the mid 500s C, where steel has lost about half of its strength, as an example. So if we knew that the safety factor from the structural engineers is to how heavily loaded the structure was going to be, how heavily loaded the steel structure would be in this case, we could estimate a failure temperature, at least in a very simple sort of approach. And there are much more complicated approaches we'll allude to here briefly, but that gives you an idea of maybe a very simplistic idea of what sort of temperature limits there might be for a structural member. On the photo up at the top right, this is a photo from World Trade Center Building 5 associated with the events of 9/11, where the building sustained a very significant burnout on several floors of the building. The fire was allowed to burn. Firefighters didn't go in and attempt to control the fire on that particular day. This building wasn't hit by aircraft other than maybe a few bits of debris. So this is basically a fire event. You can see the steel is heavily deflected, significantly deflected, a little bit of flange buckling up in the top issue here, and that this is a very common scene for a steel frame building that has some fire resistance in it, that had 2 hours of fire resistance in it in ways that we'll talk about in a couple minutes, but shows you what can happen potentially as a result of a very significant fire exposure. What you see here is there's no collapse, and it's relatively rare that high-rise buildings collapse as a result of fire, and that's why the events of 9/11, or one of the reasons why the events of 9/11 are so significant, where there were 3 buildings that collapsed that day, the Twin Towers and World Trade Center 7, where fire had a piece of that, or had a part of the reason for the collapse. Wood and concrete also are affected by elevated temperature. Wood will lose strength with temperature as well. One of the significant characteristics about wood, in addition to the strength reduction, is that it chars. What you all appreciate already without having enrolled in this course, the charring that you see in the photo here, the charring and the depth of the char relates to how much heating there was, what was the duration of the heating, what was the magnitude of the heating that gets a particular char depth. As that wood element chars, and this char layer is unable to support a load, so we're now losing load carrying ability as a result of that exposure. The inner part of the wood here is maintained relatively cool, because wood has some insulating abilities that are enhanced, in fact, by the fact that there's now a char layer. So that Mother Nature was kind to wood in the sense that as it heats up and chars, it provides a bit of a protective layer, at least in terms of limiting how much heat transfer and therefore how much heating, how much temperature rise there is in that interior portion. Concrete, again, will lose strength with temperature, so it's not fireproof. There is no fireproof material structurally. The Pentagon here, and the collapse of the Pentagon building, as again a result of the events of 9/11 indicated on this slide. where you can see some collapse here, that some of it was as a result of aircraft impact, but there were collapses, as indicated here, as a result of the subsequent fire and the fire exposure. So how do we protect structural elements? Well, there's a lot of interest in finding ways to keep them cool, or to delay the heating process, similar to that char layer on the wood. For steel elements, you see the photo with the spray-applied fire protection material that's there, or insulating material, sometimes called fireproofing, which is perhaps not the best word, again, because there's nothing really fireproof, but it does delay the heating process for the steel, and presumably, or at least philosophically, long enough to allow the fire to burn, consume all the combustibles, and have the steel stay up, similar to World Trade Center 5, such as the photo I showed you. In addition to insulating materials, there's the possibility of providing a heat sink, perhaps. And this is a case where a heat sink would be such as a concrete encasement around a steel column, such as you see here, that will provide some insulating abilities. Of course, concrete's a pretty good insulator, but it also has this heat sink abilities. And what a heat sink does is it is able to take in a lot of heat without itself increasing in temperature a lot. And that's why the label heat sink gets used. There are other ways of protecting structures, and some of this may be to reduce the exposure. Okay? So that as you apply a strategy to put the fire out, well, then that takes away that heat exposure, I think, obviously. So there may be suppression systems that will get applied, and these get called active protection methods, as opposed to the passive methods that are the categories of insulating materials and heat sinks. That's all passive because it's always there, it's sitting there, and it doesn't have to be activated by a detection device, for example. So the sprinklers shown here would have to be activated, of course, but that water spray would be able to cool the environment, maybe control the fire, maybe put out the fire. Venting systems also get applied in some warehouse sort of environments, for example, to release some of the smoke or heated gases, if you prefer, from that fire area, and that again limits the exposure that the structural element sees, that roof supporting member would see. So it's another way of providing protection. And that the whole issue in providing fire resistance or providing protection for the structure ends up being a bit of a balance between passive methods and active methods. And how to provide that balance, I will say, is an issue of much debate, in that how much do I rely on these methods, the so-called passive methods, that don't have to be activated, and how much do I rely on these? And there's again the arguments that have gone on in the literature for many, many decades, and I'm sure will go on for many, many more, as to what the right balance is, and in terms of effectiveness, in terms of reliability. Both these systems, the active systems, and these systems have to be maintained. So you don't get any free pass because it's always there. There are issues where there are maintenance problems, maybe with the integrity of that insulating material. But there are lots of questions that come into the design practice in terms of, can I do less of the passive methods if I do some of these? In going back to the concept from the committee from the BMS 92 report that said we should be able to withstand a full burnout. Well, if you can prevent the full burnout from occurring, maybe that means we don't need as much of the insulating materials. And the building codes in the United States have accepted that principle, or accepted that as a design option, and that where the active methods are used, such as sprinklers in particular, perhaps we don't need as much of the insulating material, and there might be an hour less of fire-resistant material that's needed to be provided to achieve structural protection. There are more advanced methods by which we can examine the performance of a structure and what's the right level of protection, to go through an engineering assessment that might allow you to go through a detailed analysis and comparison of how much active and how much passive protection do we need. That's based on what heat exposure is going to be provided to the structural element and how that structure will then respond to that particular hypothesized fire. There are 3 steps to this analysis that need to get conducted. The first piece of it is to understand the fire exposure. So what kind of fire is going to be there? What are the characteristics of that fire? What sort of elevated temperatures are going to be provided? What's the magnitude? Not what sort, but what's the magnitude of the elevated temperatures that will be provided? How long will that environment be present and be exposing the structure? So there's the fire dynamics aspect of it, that we have to predict the growth of the fire, predict the behavior of the fire, and get a sense for what kind of temperatures, what kind of heat fluxes are going to be provided by the fire, generated by the fire, that the structure is going to be exposed to. The next step to that is then, okay, so now that we know what the fire is, we conduct a heat transfer analysis on the structural element. So I show here a computer simulation of a floor system that has a concrete deck, a steel beam, and that steel beam has that spray-applied fireproofing material on it, spray-applied fire protection material on it, would be, again, the proper phrase to use. And the colors all indicate temperatures that assembly has achieved as a result of some prescribed fire. So this is a heat transfer analysis, and I show you one result here from this model called Sapphire. There are several models that are available, including some that are, I'll say, run-of-the-mill commercial heat transfer codes, finite element methods that could be used to explore what temperature rise you'd expect in the various components in the structure, where the fire and the heat conditions, the temperature conditions, the heat flux associated with the fire end up being boundary conditions to that analysis. After we conduct the heat transfer analysis, then that gets input into a structural analysis, where now we apply a structural code to assess what are the deflections that might occur? Does the structure collapse? Do we get buckling? Any of those sort of structural behaviors that would get applied based on the temperatures that are predicted here in the heat transfer analysis, right? Where we would assess the loads, the decreases in strength, potential the expansion of the elements as they get heated up, et cetera, to be able to again assess, so how long does it take for the structural to reach some failure condition, either because of having excessive deflections or just plain collapse, and then to tailor the protection methods accordingly. And this type of analysis was done for a high-rise building under construction in London that took a photo of several years ago, where the gray indicates those structural components which have had the spray-applied material applied to them. In this case, a coating that was used. The red-colored steel beams here are not protected and are not intended to be protected. They're secondary beams. And the part of the structural analysis through that finite element calculation I showed you on the previous slide would have demonstrated that if these couple of red members fail, that the structure can still survive, even though they perhaps fail and are not carrying any load anymore, where there's load transfer to the other beams, to the columns, perhaps the floor slab carries some of the load as well. So that advanced analysis is possible, and that's the whole item I want to make mention of here. There are some very simple methods by which we assess how much of that spray-applied material to put on, based on results from standard tests. And then there are these advanced calculations that are possible and have just recently become available and used by some design engineers for selected projects. So in summary, for this segment, fire resistance levels vary, as we've said, based on the hazard, basically. that is provided by that particular building, by that particular use of the building called occupancy. And all that's dictated on a hypothesized potential fire severity that comes from some rules of thumb from the early part of the 20th century, or can come from elaborate computational models. And then secondly, the other point I want to bring up is the strength of all structural materials decreases with temperature, and that there are protection methods that get used to restrict the temperature rise in those structural members and help them withstand the insult provided by the fire. So with that, we'll bring this to a close, and we'll continue with another segment of this in a couple minutes. Okay, let us continue. And I mentioned that we were going to continue in a couple minutes. For some of you, this may be a couple days later that you're watching this video. Here's a segment where we want to look at the effect of fire on property and contents, where the structure may survive the fire, but the fact that there is now complete burnout of all the contents in the structure may be very troubling, depending upon what those contents were. Were they replaceable? Did they have significance beyond just replacement value that would be of concern to the building owner or the occupants? So we look at property protection here in some cases, where we look at, so there may be some valuable cultural resources like the Star-Spangled Banner, the original Star-Spangled Banner, that if it was involved in fire, would be lost forever in terms of a historic artifact. There are military aircraft that would be in a hangar, and the military aircraft are potentially inside the hangar or perhaps worth more than the hangar itself. So that there are several $1 million available, and significant fractions of billions of dollars in some cases of aircraft or whatever contents may be enclosed within a building. There are facilities that have food items, food warehouses, and pharmaceuticals, where the structure itself may not be the most significant thing in there, and in that a fire that contaminates food or perhaps has exposed some food items may make those food items completely worthless and have to be discarded. So that becomes a large loss event. And then, of course, there are these computers, and I show a basic computer here, but consider more of just beyond just a simple computer, though if you have your computer and if it was exposed to a serious fire, it may be of very significance to you, and depending upon what you've got stored on an external drive or hard drive, and maybe haven't sent up to the cloud yet. Maybe family portraits, significant papers that you're working on, whatever kind of things. But also to think of a much broader type of application of maybe now data centers, bank centers that have large servers and these sort. And if that goes out of business, even for a short period of time, let alone if it was damaged in a devastating way, would provide a huge loss to bank card centers, to data processing facilities, to Google perhaps, or whatever sort of facility that would have this electronic equipment. So let's look at damage sources here to property, and I show a couple of slides of electronic equipment. Looks like a PC was significantly exposed to fire, and this is I pulled these off of a couple websites noted here. That just looking at computer damage due to fire, so you can see the melting and so on that's going on here. More significant, server sort of facility here, and how these pieces of equipment can get damaged would potentially come from three sources. The one is fairly apparent, and at least in this case, there's thermal damage and enough heat to melt the housing and so on that is probably also bad for the circuits inside the housing. There may be exposure to smoke, and this could be an array of gases that are produced by burning items, and some of those gases might be very corrosive, like hydrogen chloride and those type of gases, or it may be particulates that again can be corrosive, and as those particulates deposit on a circuit board, that can cause very rapid corrosion of the circuitry on a circuit board. There are extinguishing agents that may negatively affect a piece of property or a content, and you may be thinking of providing water as an extinguishing agent for these items. But I'll say we want to go beyond some intuitive aspects of water and electronic equipment. The water spray is actually not a horrible thing to protect a computer, a PC in particular, or low voltage equipment, because the water spray will do a lot to affect the fire, and the conductivity of the water spray is actually less than the conductivity of smoke particulates. So that if you don't put in the water spray and allow the fire to burn, the particulates get on the circuit board, that's going to do more damage potentially than if the water spray gets in there. We ran tests with the water spray several years ago with PCs, and the PCs were absolutely fine with a water spray being applied and discharged in a room. And we just had the discharge of the water spray. It was a water mist system that we were exploring at the time, and the PCs operated without any trouble at all. The only time that we had an issue was when we took the cover off of the tower and it allowed the water to actually collect in the circuit board connectors that shorted out the board at that point, or at least temporarily. As we took those computers out that would stop operating, brought them out into the sun, allow them to dry out, turn them on again, they were fine. They were absolutely fine. So there are some knee-jerk reactions or reflexes that, oh, you never use water on electronic equipment, and that's not true. That's not true. High voltage equipment, different story, but low voltage, such as we're looking at here, really not as much of a problem as people might perceive. But there are issues with extinguishing agents, and certainly for artwork where this is an exposure from water and an extinguisher of some sort. The source didn't identify what type of extinguisher it was, but with a watercolor, that's not going to be good for sure. And for various pieces of art, artifacts, water exposure and soaking it may cause some damage. A lot of these kind of items can be restored to a great extent through freeze drying, and there are all sorts of amazing restoration capabilities that folks have developed over the years. Though a watercolor, that's probably permanent damage. Showing aircraft submerged in a foam layer. The foam is fairly corrosive to the electronic components, so that the aircraft here may be significantly damaged unless this foam is very quickly removed and the equipment dried out, which may be pretty much impractical to do in the sort of time frame that things need to happen. As we look to property and damage and the effects of fire and various aspects of fire on property, it's appropriate to think of, so what damage levels or damage thresholds are available for these things, or what information we have on damage thresholds, so we can do a fire hazard analysis. What type of hazard we expect to occur as a result of a particular type of fire and particular items that are burning, what's going to be in the smoke, how much temperature rise will there be, and we can look to temperature limits, for example. And I have just a few random examples here of temperatures that the literature talks about. Cable insulation, PVC cable insulation degrading at 205 C. Computer hardware, such as the couple of photos I showed you back before, that starts to get damaged up around 80 or 90 degrees C. Electric panels degrade when they're hit with a heat flux, and hit is perhaps the wrong word. They're exposed to a radiant heat flux of 6 kilowatts per square meter. That's a bit of a conservative lower level limit, but it is the limit that the U.S. Nuclear Regulatory Commission considers for fire hazard analysis with electric components. And basically, if the panel is exposed to that amount of radiant energy, the components inside start to get overheated and cause problems. Gas concentrations. For electronic equipment, visual damage will become apparent where you'll get some corrosion sort of effects at as low as 100 parts per million of hydrogen chloride exposure. That's a fairly low exposure. In percent, that's 0.01% by volume of hydrogen chloride. You see electric damage that if you were to do continuity tests and all that, it's a little bit higher to where there's just some surface corrosion to where it's really doing damage. But that's still only 1,000 parts per million. That's not all that high. That's 0.1%. And in fact, that if we were to compare that to tenability levels of people, we'd see that people can actually endure a higher level of hydrogen chloride before receiving significant effects and be affected in significant ways as compared to this electronic equipment. And then corrosivity of smoke particles that's recognized to be an issue, but in terms of any quantification of that, that's still not really within the state of the art to say a particular particle, given composition, particular size, whatever gases have been absorbed onto that particle, would have a given impact, and that level of quantification isn't there. It's recognized qualitatively for sure to be an issue. There is this kind of information in the literature on smoke particles generated by PVC smoke on various metal components, as you can see here. And so what's the depth of corrosion so many days after the exposure to PVC smoke? That could include some of the gases as well, quite honestly, as well as the particles that may deposit on the conductors. So as we think about the damage, the potential damage caused by extinguishing methods to the property and contents, the real issue becomes a comparison, right? So that as we get a water spray on books, for example, or water spray on electronic components, and that if there is damage caused by that particular extinguishing agent, whether it's water, whether it's a portable extinguisher, a foam, whatever might be used, looking at the collateral damage by those methods and comparing that to fire and smoke, and that do we delay performance of a water spray system here, a sprinkler system or a water mist system, allowing a fire to continue to burn and having things dealt with by fire service people. Will likely bring in large hose lines with much more water. That the conservators and the librarians and such have some guidelines for acceptable loss of contents of books, for example. As there's a fire, maybe only chars the outside edges so you don't lose any printed material. That's a much less consequence than if the books are completely charred and destroyed. And again, there was a fair amount of work we got involved in research we got involved in years ago here at Maryland in looking at water spray systems, for water mist systems in particular, for library collections and significant artifacts from museums, art museums, to look at what is the impact of a water mist system, for example, low flow system on these books. The conservators were part of those tests to show or to evaluate whether the water damage was significant caused by exposure to a water mist that was a very light coating of mist, but didn't soak the items. So the conservators felt that those were all very recoverable items. But even if completely soaked, again, the state of the art in restoration is rather amazing. largely through freeze drying sort of techniques if it's simply become wet. Where wet, just final comment here, that where wet is far better than charred. And that's where the librarians pretty much recognize that there is a lot of fear among conservators in the library community as a result of maybe false activations. And that's certainly a concern, but again can be handled through supervision of systems to prevent the unwanted activations. So protecting property and contents, it does require an understanding of how tolerant materials are to fire and smoke for sure. So what are the threshold limits? What size fire causes irreversible damage to the contents? And as one hypothesizes a reasonable fire or a likely fire that's going to cause damage, then you start to look for protection methods. Where the protection may be an extinguishing system, may be a very rapid detection, may involve backing up all the materials, thinking of electronic components and these data centers and so on, having backup systems available that are off-site and maybe in other continents even, literally in some cases, so that there's a whole secondary set of files that can be pulled up if that one data center is exposed to a damaging fire. And otherwise, extinguishing agents are selected considering potential for collateral damage. We talked about this a bit in the suppression systems module, remember, where we talked about water versus foam versus the clean agents and why one would pick one over the other. And one of the significant concerns that we raised back then was the fact that the collateral damage potential, and that we may put the fire out, but if that extinguishing agent damages the equipment by completely as a result of its activation, then you really haven't accomplished as much as you would like otherwise maybe with a different extinguishing agent. So with that, we'll bring this little segment to a close and continue with the third segment in the next module. Welcome back. This is the segment where we want to talk about impact of fire on the environment, and is a topic that's only relatively recently come about in the fire protection engineering field. Protecting structures was where the field started at, basically in the late 1800s here in the U.S., and one can even look back in history to the Great Fire of London in the 1600s, where protecting structures was an important consideration and the primary consideration at the time for fire protection strategies. We got to then protecting contents and protecting people, and those were identified as important design objectives where we could make a difference, largely in the 1900s. And it wasn't until the late 1900s where looking at the effect of fire on the environment became a key issue. So what environmental impacts are we talking about? Well, air pollution certainly is one, and this is where, as we produce smoke from a fire, as a fire produces smoke, we don't necessarily create that, I guess, but as a fire produces smoke, there's an air pollution potential. There's water pollution potential as a result of the application of extinguishing agents, water, foams, whatever, that then runs off of the property and into the local river or streams. And then finally, there are issues that fire protection engineers have gotten involved in with extinguishing agents that had negative consequences relative to global warming and ozone depletion. So selection of extinguishing agents becomes an important issue there. So let's look at each of these, and just in terms of some of the smoke generation that occurs. So the Deepwater oil well fire in 2010 in the Gulf of Mexico, you can see the very significant quantity of smoke that's produced there. The Dietz and Watson warehouse fire with the solar panel involvement, and the smoke, the very significant smoke plume there. And now think of what's in that smoke plume. That's at least partially composed of the combustion products from whatever those solar panels were made of, or in terms of the offshore oil well here, that's a petrochemical fuel, and whatever's in crude oil, basically, in the combustion products that are now in that smoke layer. There are also wildland fires where there's significant quantities of smoke produced from these very large fires that provide an irritating smoke, even though it's only wood smoke for the most part, or grasslands and agricultural products. It can still be a very irritating smoke and provide a lot of soot, maybe cause some significant problems for people with breathing difficulties. Water pollution, there are a couple very significant incidents in the relative to water pollution that we can talk about, and this is one, and there's a news clipping that I thought I'd run here that talks about this particular incident.
Do you remember what you were doing in 1987? Well, for Daytonians, it was the year of a giant fire that changed safety forever.
Flames destroyed the Sherwin-Williams paint warehouse. They also threatened the city's water supply. Jordan Burgess spoke with the man at the center of the inferno whose leadership kept our water safe and clean.
The fire is still out of control, and we have a number of news crews on the scene. One of them happens to be Dave Calabro and his photographer, and these are the pictures right now of the site.
All these years later, the flames are still seared into their memories.
Biggest fire I ever see in my 33 years in this business.
But the raging inferno at the Dayton Sherwin-Williams warehouse 25 years ago isn't remembered just for what happened, but what didn't happen, and how it may have rescued the city from an even bigger disaster.
And he may be the only fire chief on the planet that became famous for not fighting a fire.
The warehouse is now a field, the only machine here a mower. But in 1987, it was like a paint-filled time bomb waiting to splatter. You see, because of decisions made decades earlier, the Sherwin-Williams warehouse was sitting on Dayton's well field.
In retrospect, probably wasn't the best thing.
People had warned about the danger for years, and all it took to set the city's worst nightmare in motion was a small spill by a worker on a lift truck.
When he backed that piece of equipment out to get out of the way, that ignited the spilled product, and that was the start of the fire.
The plant had prepared for just such a situation. It had state-of-the-art sprinkler systems, but even they weren't enough.
That particular night and the way events turned out, I think those suppression systems didn't last probably a few seconds, and they were null and void.
The worker on the truck suffered burns to his legs, but thanks to a practice evacuation plan, everyone made it out safely.
You know, they had told us how fast it could go, and I just ran. When I seen it, I headed for the door.
Believe it or not, Dayton Fire Chief Glenn Alexander was actually painting at the time he got the call.
A neighbor had made a toy box for my daughter, and I was painting the thing.
When firefighters arrived on scene, they had hundreds of aerosol cans raining down on them. In the years afterward, they would be found on the nearby Kitty Hawk Golf Course and the roofs of buildings.
So they were just rocketing. You can see the bottoms blown out.
In this old video, you can hear them exploding.
It was like they were under artillery fire.
Aside from the paint can rockets, the fire was inching closer to other buildings. But Alexander knew he had a bigger issue at hand.
Let me tell you what our real problem is. You're standing on our biggest exposure.
Having been part of a well field protection task force and having talked with Water Department Director Bill Zilli and Environmental Manager Dusty Hall, Alexander knew the runoff from fighting a fire could pollute the drinking water.
Immediately in my mind, my whole thought process went for the well field.
So he made the toughest decision of his career and told crews to stop fighting the fire.
And I was bombarded with questions about, you're letting this thing burn down. And I said, yes, I am.
They're going to let this fire burn out. That's the whole idea, is let this fire burn out.
Unfortunately, firefighters weren't the only ones dumping water on the fire. The sprinkler system was still going. So the task fell to Bill Ford and another firefighter to go near the building and shut it down.
These aerosol cans were zinging by our heads, and he's saying, this is neat, you know. Let's just worry about getting in here and get this job done and get out, you know.
With the sprinklers off and no water being poured on the flames, The fire continued to burn for 6 days. The loss was in the range of $64 million. The 120 jobs there also up in smoke. But the well field was saved.
In this incident, as catastrophic as it could have been, there was never an operating public water supply well that became contaminated, ever. And no one would have ever imagined that that was possible.
25 years later, we went back to the site of the fire with those whose actions helped keep it from becoming even worse.
A lot of courageous decisions were made that night.
The impact of the blaze is still being felt today. It changed fire codes, making buildings safer. It also made people realize the importance of protecting well fields.
So what we learned from this was you can't engineer a facility with that kind of material to be safe in a place like this.
In the years following the fire, Dayton ramped up its well field protection practices and is now one of the nation's leaders in keeping drinking water safe.
People come here from all around the world to see how this drinking water has been protected. So it's a very positive story in the end.
But the men who made the difference that fateful night say those lessons of the past are only useful.
Okay, so let's come back to our topic here. So you saw in that particular case where the water pollution that was groundwater, and not surface water in particular, that was the major issue in that case, and that's certainly a significant concern. In another incident, this time in Europe, in Switzerland, there a plant that Sandoz chemical plant with pesticides and some agrochemicals, fire involved a warehouse, once again. A huge amount of these pesticides and agrochemicals were involved in the fire that were contained in the warehouse. You can see the firefighters working through this. And the runoff, again, was very significant with this red colored runoff that was contaminated materials. They continued to fight the fire in this case as compared to the Dayton, Ohio case we just looked at. There were thousands of fish killed in the Rhine River that was nearby. There was certainly air pollution as well, as you could see from the smoke plume that was on the previous slide. The building site was later covered with a concrete slab, though it remains contaminated to this day. 20-some years later, it is still unusable. In terms of the extinguishing agents issue and the depletion of the ozone layer, this came to the forefront in the 1980s, and finally with the Montreal Protocol being signed that would discontinue the production of substances which deplete ozone in the atmosphere, and this was basically the halon extinguishing agents, at least for the fire protection field. There were a range of CFCs, chlorinated fluorocarbons, that were banned by the Montreal Protocol, or at least where production was stopped. And one of those was the halon 1301 product. You can see it being discharged here in a data processing center. So halon 1301 was a wonderful fire extinguishing agent. Was applied in relatively low concentrations, had no real significant health effects on individuals who would be in that smoke, in that cloud of agent, and had a very, very strong effectiveness fire extinguishing wise. However, it was a very significant, had very significant ozone depletion capabilities. So that as a result, there was a policy put together by the U.S. Environmental Protection Agency, put together the SNAP program, as it was called, so significant new alternatives policy that basically was looking at clean agents, the next generation of clean agents that could be used in electronic processing facilities and or electronic equipment areas and data processing centers, bank card centers, places where, again, you were concerned with collateral damage of water and wanted to use one of these gaseous agents, where then the tests or the measures that were used to explore the environmental impact of these extinguishing agents looked at ozone depletion and ozone depletion potential, ODP, a global warming potential, GWP, and then how long these substances lasted in the atmosphere before breaking up, decomposing, going away, and that was the atmospheric lifetime measure. That are now all part of an approval strategy, and this is documented or referred to in an NFPA standard, NFPA 2001, that would talk in more detail about the acceptability of various extinguishing agents for these environmental impact type of concerns, as well, of course, of having agents that were still effective as extinguishing agents. So we've seen in this segment that there are certainly air pollution effects. Those are fairly obvious, where you see these large smoke columns coming about. And keep in mind that what's in the smoke may involve some substances that we would consider to be hazardous materials among their own. So there are heavy metals that somehow will burn. Or various organic pollutants, formaldehydes and that sort that may be produced in some fires. Having that in the smoke stream can be very, very devastating health-wise to the population as that perhaps now settles out downstream. Water pollution is very significant, and as has been demonstrated in a couple of one significant catastrophe and one non-catastrophe, at least in this respect, as a result of the actions of the emergency responders in disbanding their extinguishment efforts. But there is the possibility of the surface water being polluted, rivers, streams, and also the groundwater as a result of runoff. As there's runoff from a fire, and then even a small fire, that water that runs off and goes into the ground surrounding the building, that's going to go somewhere, and a lot of it gets down into our groundwater and into our water supplies. And then finally, the other concern for fire protection and the environment is finding acceptable extinguishing agents, so extinguishing agents that are effective, but also that are environmentally friendly and are not going to be ozone depleters and contribute to global warming, that have lifetimes that are relatively short would be the preference in general. So that's a relatively new item since the late 80s, and the discontinuation of production of the halide agents 1301 and 1202 in particular that were the most popular. So with that, we'll close this particular module and look forward to seeing another topic for next week.
I'm Eric Rosenbaum, a vice president with Hughes Associates Incorporated, which is a fire protection consulting firm. And today I'll be talking about implementing fire safety designs. I will be concentrating mainly on implementation of fire safety designs in structures and buildings, but the concepts will remain the same no matter what you're pretty much evaluating. What I'll be going over in the presentation, which will be broken down into 4 different short presentations, are what are the different concepts and options for fire safety design. I'll then be discussing what are the code or prescriptive-based approaches for the concepts of fire protection. Then I'll be looking at performance, or if you define goal objectives, what are performance-based design options to meet the intent of what you're trying to do. And then I'll be discussing what are different engineering methods to help you evaluate what the best design concepts are for fire safety in structures. I'm going to start, the first presentation is on the concepts of fire safety design. And this is, okay, if I have a building or if I have a structure, what do I do to make it fire safe, or what are the concepts that I can use to make it fire safety as far as approaches, thought processes, what are the different things I'm looking at. I will be giving you an overview of the concepts, discussion of them, discussion of what are different goals for fire protection or fire safety and design of structures, what are the different approaches for determining what the best fire safety design is in structures, and then discussing some of the resources that are available when you're evaluating fire safety design concepts. When you look at concepts, or how do I evaluate the fire safety in structure, you are looking at, okay, how do I do this? What do I do? Well, the basic thought process is essentially working around this circle where I first identify, what are my fire hazards? What am I really trying to address? Am I having a warehouse full of flammable liquids that also are radioactive, or do I have a bunch of bricks stored in this facility? Clearly, the hazard associated, or the fire hazard associated with flammable liquids is significantly greater than those with a non-combustible brick or something that doesn't burn. So you have to look at, okay, what is my fire hazard associated with this? From then, I can then evaluate, what are my potential consequences associated with this hazard, or how can I do? Will I burn the building to the ground if it catches on fire? Or potentially, if it catches on fire, will have no impact on the people or the structure. And by evaluating these concepts, or what the potential consequences are, I can then identify, okay, what are the potential methods to address these hazards or consequences? And by identifying what methods or potential issues can I use to address these hazards, then I can evaluate the impact of these methods on the consequences. So if I have bricks in a building, my method to protect the structure may be not to worry about it. Whereas if I have a flammable liquid in the building, I may introduce a foam system or some other kind of fire safety system that will limit the impact. I can then look at, okay, do I install a bunch of different options or protection methods, and I can select, based on all these issues, I can then select what are the protection options that best suit my needs. What do I mean by protection options? And these have been discussed earlier in different presentations. And they can include anything from automatic sprinklers, which you see installed in many buildings. And automatic sprinklers, here's a picture of one right here going off. What they have is they have a kind of detection device installed within them that makes it so that it senses heat. And when it gets really hot up where the sprinkler is, this device melts and the water explodes, and the water will come out and extinguish the fire. Not only does it extinguish or control the fire, it will also set off an alarm for when the water flows through the system. So I notify the people in the building that there's a fire. I notify the fire department that there's a fire, and they can potentially come and address it. So these sprinklers perform not only a method to control the fire, but also to detect and to alert the occupants and fire department. And that ties directly into an alarm or mass communication system, where you then have a method for allowing people to get out of the building or alerting them to a fire so they can move to another section of the building and be alert of what is going on. Now, once you alert people, they have to get out of the building. So you provide exits, or you provide a place for these people to go and wait safely. So the number of exits and where you provide them is directly driven by the kind of occupants. You will provide more exits typically in a convention center than you would in a hospital, where the convention center, you have a lot of people who are capable of moving out of the structure if there's a fire, as opposed to a hospital where you have many people, you don't have a lot of people, and the people aren't capable of evacuating themselves through the exit. So you just might move them to another safe area in the building. So these are all protection options. You also have smoke control, which may be passive, such as building a barrier with a door in it and smoke dampers so that smoke can't move from one side of the damper to one side of the barrier to another. Or you may have active smoke control, which may consist of a heating, ventilation, and air conditioning unit, taking the smoke and evacuating it to outside the building. So you have different methods of smoke control as well as structural features. You may have a building that has and is built of non-combustible construction, and it may be a steel building. Well, if you have a regular steel building with no protection on the steel features, in about 10 to 15 minutes of fire exposure, that steel will probably fail. So you may have collapse of your structure. So depending on what you have in that building and the size of your building, if you're a high-rise building and you don't want your structure collapsing, and it's made of steel, you will actually protect that steel so that you get multiple hours of fire protection so that you can actually have all the contents of that building burn out without the structure collapsing to allow all the people to evacuate or to stay in place up above it. So those are different things. There are also other methods or fire safety design concepts, and those can include anything from limiting the fuel load within the structure to many other clever and unique ways to providing fire safety that will all meet the potential needs of the stakeholders, of the user, or whatever you have governing that building. Now, when you talk about goals or determining what fire safety needs in your building, there are typical many goals associated with fire safety in structures. And the fundamental goals are ones that are almost included in every structure. And those can include life safety, such as getting the people out or evacuating them to an area of safety. You almost always want to make sure that people are safe if there's a fire. The only exceptions are some buildings are almost totally unoccupied, or some buildings have such high property protection issues in them that property protection may become a more major issue. You still worry about life safety, but property protection may become the #1 issue. And what do I mean by property protection? Well, if you have a art gallery where you have priceless paintings, or if you have some other form of property that you have a storage warehouse that is never occupied but contains pharmaceuticals, property protection of that facility is almost paramount to what you're dealing with as far as dealing with the fire safety concepts. Another important thing is the continuity of operations. There are some manufacturing plants that are worth millions of dollars of days to the owners. So they want to make sure that you maintain the continuity of operations. Not only would that be in a manufacturing facility, but for example, certain art galleries like to be known to be open 365 days a year. And it's important to them to know that if they have a fire, they will have continuity or be able to be open the next day. And environmental protection is almost always a major issue, but it really comes to a highlight in cases where you may have radioactive waste stored in a facility. So you want to make sure that you provide fire protection in such a way so that if there's a fire, radioactive waste don't spread through the plume or through other portions, through the fire products or smoke outside of the facility and expose the neighbors around the facility. Other goals of fire protection may be just strictly code compliance. The owner wants to make sure that he's covered so that he complies with code. And I put up there reduced costs. I don't know of any building that's been built where they say money is no object. You always have to design or come up with a fire protection scheme that was in the owner's budget and allows the building to be built. You don't want to come up with a scheme that results in costs for the fire protection that greatly exceed the budget that's allowed for the building. Flexibility of the use of the building is a major issue, as well as limiting damage to the historic fabric. If you have a historic building such as National Gallery of Art or the Statue of Liberty, they don't want you doing things that will damage the historic fabric, such as building a stair outside the mouth of the Statue of Liberty so people can exit. You always have to incorporate those goals in your fire safety concepts. Now, when you look at a structure, different things, it's not only fire safety, there are different items that come into play. And life safety is a fire safety issue, but you have to remember, life safety is getting people out of the building as quickly as you can. In an art gallery or something else where they have high security issues, they don't want people being able to leave the building easily. So they may go, okay, security is also a major issue, or the building architecture, or they may have such a design so they don't want the aesthetic impact of the fire protection affecting the appreciation of the concepts of the building. And there are some Library of Congress buildings that are just absolutely beautiful inside. You don't want the installation of a sprinkler system or some other element making it so that you can't appreciate the aesthetics of the building. So you have to make sure that it's incorporated there, or that the fire safety approach doesn't affect the building operations, that the owner can still utilize the building that way that he feels is appropriate. Now, when you look at, okay, who inputs to what is the appropriate fire protection scheme for the building, there may be several different elements that you're looking at. I, as a fire protection engineer, like to think that I make all the final decisions relative to fire safety. But I know that's not the case. It doesn't happen that way. I provide some of the input, but I also have to look at, okay, is the architect or engineer or the designer of the building not going to appreciate my approach to fire protection? Or will the owner and user say, this doesn't achieve what we're trying to do with the concepts or the use of the building, so by doing that fire protection, I may as well as not use the building and not build it. And there's always an authority having jurisdiction, whether it's a federal agency, a local building official, a local fire marshal. There will always be someone who's looking at it for fire safety, for the public's needs, and for these, for the different people who may be occupying it. All these people or stakeholders end up having to provide input for fire safety design. There are also different methods to look at fire protection or fire safety concepts in buildings. And I'll go into more of these in the future modules, but there's a code or prescriptive approach, which is for a typical office building such as this, which is a square building, you can provide exits and you can pretty much provide a code-compliant approach to the building. So you would look at it and say, okay, this is how many exits I can provide. This is where they need to discharge. This is the sprinkler system. These are the different smoke control systems. This is the way I evacuate people. These are pretty straightforward concepts that you use in a typical building, and they're all code or prescriptive based or laid out like a cookbook. For unique buildings, such as these two, you may have to come up with a unique design concept that will be outside of the building code or outside of what is typically accepted, and those are called performance-based approaches. And when you're looking at the overall level of code compliance, you have to look at several different things, and one of them may be the level of code compliance of the structure. Is it code compliant? How do I do it? Or the ability to meet the goals and objectives in a performance-based approach. Can I meet the fire safety goals and objectives that I developed? You may also look at the appropriateness for the area of the building protected. Now, what do I mean by this? Well, if you have flammable liquids that you're protecting, it may not be appropriate to use water as your protection method. You may choose to use a foam or some other kind of system that won't interact with the flammable liquids and potentially make the fire worse. You also have to look at the reliability. You don't want to depend on one system so that if it fails, your fire safety design for the building doesn't work anymore. You're exposing the occupants if you have a single failure. You have to look at the severity of the fire hazards and the feasibility and cost of your approach. Is it feasible to install that fire safety design? And is the cost reasonable? Do you get an appropriate bang for your buck? And then engineering judgment. I've seen tons of things burn. I've seen tons of ways of protection for structures. Okay, if I see that and yet there's something, the code says it's reasonable, but I've seen that fail many times, I have to use my engineering judgment to say I want to use a different approach. And to give you an example, this is the National Gallery of Art. In the National Gallery of Art building, it's a historic structure that has priceless connections in it, collections. The artwork is amazing, and you don't want to damage that ever by your fire protection systems or by a fire. So you have to come up with approaches that will meet not only my goals and objectives for protection of the people, protection of the collections, protection of the building, but you also have to make sure that they're cost effective so that you can afford to install them. There are a couple of documents that provide guidance on fire protection. These are big documents. This is the Fire Protection Handbook. This is one of 2 volumes to give you an idea of the size of the documents. These will give you great insight onto how to address fire safety. Another one is the Society of Fire Protection Engineers Fire Protection Handbook. This is another document that provides calculations and methods to determine fire safety. Again, this is a Fire Protection Handbook, and this is published by the National Fire Protection Association. So in summary, concepts, there are many options for fire protection. The stakeholders or the people who are involved in the building need to be or provide input for the choice to be effective. There are 2 approaches to fire protection, code or prescriptive and performance, and handbooks exist to help you provide what is a fire safety approach. I'm Eric Rosenbaum, Vice President for Hughes Associates. This module will address the code-based approach to fire safety design. What I'm going to give you is an overview of what the code approach is, what are codes, how our codes are developed, discuss applications of codes, and then give you examples of where codes are applied. First question is, okay, code-based approach to fire safety concepts. What is it? Well, what are codes? Codes are documents, here's an example of one, that establish criteria for construction. They are prescriptive based, or what I mean by prescriptive, they essentially are a cookbook of what you do if you have a building, how do you provide the fire safety design, what do you do for fire safety in buildings or fire safety concepts in buildings. They are based on a broad classification of buildings. So if you have a office building, this is the way you protect it. If you have a conference center, this is the way you protect it. It is very straightforward. It requires a lot of experience to use them because there are a lot of intricacies associated with them, but they are provide you with guidance on what is a level of safety you provide in buildings. At this point, I'm going to address strictly prescriptive codes. Just for information, now they are developing performance-based codes, and that will be a module that is discussed at a later time. How are codes developed? Well, there are 2 principal people who develop codes in the United States, and my presentation or discussion will focus mainly on the United States, but there are codes used throughout the world, and we'll discuss some of those later on. The 2 main developers of codes in the United States are the National Fire Protection Association and the International Code Council. What they do to develop the different codes is they get a group of people together, and they say, okay, this is an existing, a building that is going to be built to the building code, or this is a building code. What do you think needs to be provided as far as a level of life safety that needs to be provided in the structure? And they don't just get one group of people together that are homogenous. They try to get people with varied interests so that you don't end up with a life safety code that addresses one person's viewpoint. So what are the varied interests? You might have an enforcer or a person who's a building code official or a fire marshal in the jurisdiction, and they will provide their input on what they think is a level of life safety. Another person might be a special expert, such as myself, who's a consultant, and I use the word expert, that's the way that the codes term it. I don't mind to be pompous, it's just they call them a special expert. They provide their input after designing. I've designed hundreds of buildings, so I can tell you what I've seen put in buildings. I've also burned in the back of my office hundreds of things. What a great job, needless to say. So I can see how things burn and see what are different methods of protection for these different things. Manufacturers also get in there. Now, manufacturers have an interest in getting their products promoted within the code, but it's against the rules to say you must use a specific product. You can only say you can use this protection method as an option, or a user. For example, hospitals are represented, or different American Healthcare Association is represented to make sure that they have their viewpoint provided in their code. The key is when you are writing these codes, anyone can input. They have it so that you can write in and you can propose an amendment to the existing codes or propose changes to the codes. Anyone can put input, but acceptance of these proposed changes is by a vote of the varied interests. And what they do is they develop a committee that votes on the proposed changes. These committees are balanced, so there aren't too many manufacturers, there aren't too many enforcers, there aren't too many special experts, so that they can make sure that what gets into the code is reasonable and cost-effective and provides a level of safety that everyone feels is appropriate. The participation in the vote may be limited. For example, in the ICC, it's limited to enforcers, but in NFPA, any of the varied interests can input, but anyone can input. The vote itself may just be limited to the enforcers, depending on which code you are using. Now, what are types of codes? They have codes that are life safety codes, or directly driven by life safety, such as NFPA 101 is a life safety code where the primary interest is life safety. You have building codes, and I'll give you an example of that on the next slide. You have system design codes. If I want to design a sprinkler system or a fire alarm system or a pump, I would use anything from NFPA 13 for sprinkler systems, NFPA 72 for fire alarm, NFPA 20 for pumps. They all provide you system design guidance, or system design. It's not guidance, it's actually specific criteria for the protection of those systems. And they provide prescriptive criteria for specific applications. Now, some of the most common codes are NFPA 101. Here's a picture of the life safety code. It gives you an idea of what is used in the structure. NFPA 101 is a life safety code that says you need to provide this number of exits. NFPA 13 is a sprinkler system code that says design the sprinklers. If you're in a building that's a high-rise building right now, you will have a sprinkler system in it. Another building code which will govern construction type and make sure that property protection features are addressed is a building code, and this is the IBC, International Building Code. The International Building Code includes things like firefighter safety and building or property protection in them, whereas the Life Safety Code would not necessarily include those features in it. It's mainly worried about the life safety of the occupants itself. Now, when you're looking at these different codes, they provide you with unique guidance. And for example, goals of these may to provide an environment for occupants that is reasonably safe for fire. And when it's not all occupants, because if you're the one who starts the fire, if you're, for example, in a hospital bed and you're what you call intimate with the fire, you start your sheets on fire by dropping a cigarette while you're sleeping, it's very hard to protect or make sure that the survivability of someone who's intimate with the fire is maintained, but occupants non-intimate with the fire should be maintained. And it's to increase the survivability of the occupant who's intimate with the fire. And for example, this is a picture of the first interstate building fire that occurred a long time ago. The building didn't have a sprinkler system at the time on the floors where the fire occurred. So you had actually people die, a person die, and many people get injured by the fire spreading from floor to floor, and many floors were burnt out by that fire. Now, your code guidance will be applicable based on the jurisdiction of where you're located. So if you take the United States, each state adopts a building code, and it may be that, for example, This is a picture of Maryland. Each county in Maryland may adopt a different building code, so you need to make sure that you use the right code to determine what is the appropriate criteria that would apply to that building. Now, this is just the United States. You have 50 codes potentially, where you have one that may adopt the International Building Code. And then what they do is they adopt jurisdictional amendments potentially. So the code may be the International Building Code in Maryland as well as in New York, but the amount of amendments that they adopt associated with those codes would vary so that the code will not look the same whether you apply it in New York or Maryland. It will be different, and you need to make sure you get the jurisdictional amendments. So you could have a lot of building codes associated with where you're dealing, and then that's just in the United States. If you go internationally, there's the SEN codes, or there are a whole bunch of different documents that may be applied. For example, in the Middle East, they may adopt the International Building Code, but again, they will have their local amendments, or they may have their own totally independent code that would apply depending on the jurisdiction. So you need to make sure that you know which code is applicable in which jurisdiction. What is the code approach? Well, it's pretty straightforward. You determine the use of the building. Remember, this is a cookbook, so it's relatively straightforward what you do. You determine the use of the building. Is it a conference center, which is assembly use, or is it a exhibition building, which is a different kind of assembly use, or a restaurant, which is assembly use, or is it an office building, which is business, or is it a storage building, which is storage, or industrial, which will be factory? You may have any number of uses. You determine that use. You then determine number of people in the building, excuse me. You determine the hazard associated with the contents in there, and then you apply the criteria in a very cookbook fashion. If I'm assembly occupancy, that's a restaurant occupancy, this is the way I provide my exits, this is the way I provide my construction type. These are all the different factors that go into it. Well, what are the different factors that go into it? Well, I'm going to start with the occupancy classifications. And what you see, for example, you'll have a different occupancy classification if you have a big classroom building or a small storage or a small interstitial space or an office building. Each of those have a different occupancy classification and will have different criteria that applies to them because they have a different hazard of contents and they have a different number of people. So I determine the occupancy classification, and then from there, I would then determine what are the different features that are provided. Well, construction type is one of the issues. Do I put in non-combustible or construction that won't burn, and do I have to protect it so that it doesn't fail as a result of the fire that I anticipate in the building? So this is a picture of the American Indian Museum. It has an assembly occupancy as multi-level structure. Based on the height and area and the use of that building, I determine what the construction type is, and I know, okay, there's going to be a lot of people, there's a potential for a fair amount of fuel load. I need to make sure that building is of protected, non-combustible construction. Or as you can see, it's all concrete construction or all non-protected, non-combustible construction. Therefore, from the height and the area and the occupancy, it tells me what is the minimum construction type of the structure. I then go look at the means of egress, or how I get out of the building. What is the number of exits I have to provide? What is the capacity of the exits I have to provide? Where do I arrange them so I don't trap people down long corridors? And once they get into the exits, how do I discharge them? Do they go directly outside the building, or do they go through the lobby out of the building, or through a grade passageway outside the building? You also look at the fire protection features. This is an atrium, so do I provide smoke control in here? Do I seal the openings in the penetrations in the firewalls, or do I protect the structure and make it so that it doesn't fail when it's exposed? You have different fire protection equipment, and whether that's a sprinkler system or a smoke detection system or smoke control. These are vents that go up to a lay light area or that allow the smoke to vent from an art gallery down below. so the smoke doesn't expose the artwork. It actually vents up through out of the gallery so that you don't have a problem with the exposure to smoke. It'll also tell you what fire protection systems to install. Do I install a sprinkler system or a fire pump or a standpipe system? And it gives the requirements based on the use or other special conditions. It also looks at, okay, if I have a high-rise building or a tent building such as this is Pier 6 or the Denver airport, how do I protect these structures or unique structures? Or if I have an aircraft hangar or a haunted house, you have haunted houses create a maze purposely. So you have to provide a greater level of safety to assure that people can get out of those structures. Interior finishes are also something that are driven by or controlled. The Station nightclub fire in Rhode Island, they had a lot of foam on the ceiling in a heavily occupied building. You need to make sure that you don't have that problem, so they control the interior finishes so the fire doesn't spread along them. You also have automatic sprinkler, smoke detection, all kinds of criteria that comes into play to make sure that you provide fire safety. That includes methods to prevent smoke from transferring from floor to floor in high-rise buildings. I want to make sure I've given you some of the codes. There are not only the Life Safety Code and the International Building Code, but there can be codes that apply internationally. There might be Department of Defense, General Service Administration, or Veterans Administration codes that are unique to those facilities that would also apply in those structures. So an approach, the code approach summary, codes provide a guidance based on the use of the building. They're applicable to almost all buildings everywhere. They don't specify by specific building. It's a generic approach. And codes and standards look at life safety and property protection, and they exist to regulate and guide. I'm Eric Rosenbaum, Vice President with Hughes Associates Incorporated, which is a fire protection consulting firm. I'm going to be discussing the performance-based approach to fire safety design. I've already gone over the code-based or prescriptive-based approach. The code base establishes in a generic way how you design fire safety for buildings. The performance-based approach looks at how you can address fire safety design in structures based on specific attributes of a single building. What I'm going to do is introduce the concept, discuss different elements of performance-based approach to fire safety design. That includes the goals, assessments, and designs. I'll give you example applications and then how we choose the appropriate designs. What is the concept, or what is performance-based design? And you'll notice I use PBD to indicate performance-based design. It is the evaluation of hazard of risks or risks based on defined goals. And it is very scenario specific. You do a performance-based design based on a specific building, based on specific fires, and based on specific occupant loads. So if you use performance-based design on one building, it doesn't necessarily say that on the building next to it you can use it. It's very specific to what you're trying to address and how you're trying to address them. Throughout this presentation, I'll be talking about hazard and risk. Hazard is looking at the consequences of a fire. So if I burn this flammable liquid, the consequences are it'll potentially burn down. And if I provide this fire protection feature, this is the effect it'll make it so the building doesn't burn down. So it strictly looks at the consequences. Whereas risk looks at the consequences times the probability. So it looks at both items, not only if there's a fire, what happens, but what is the probability of that fire occurring, and what is the probability of that fire safety design or fire safety method working and actually addressing the scenario that we're dealing with. When you look at performance-based design, it's a structured approach to look at, okay, if I have this building or if I have these structures, I will then identify what the goals or objectives are for defining that structure, or what do I want to do? I want to make sure the people are safe. I want to make sure that I can include this aesthetic feature, include this atrium in the structure that I'm dealing with. So based on specific goals and objectives, I'm going to determine what is the fire safety approach. These are in where I'm looking at the different design fire scenarios that can happen. What is the fire safety approach that will meet those goals and objectives so that I can select a final design for the structure so that I can design it to meet the appropriate fire safety or meet the correct performance criteria. And when I say performance criteria, whether that's making sure the people are safe or making sure that the artwork doesn't get damaged in the museum, or that the manufacturing operations maintain in effect, or that my loss doesn't exceed $5 million or doesn't exceed whatever I want my maximum possible or probable loss to be. When I look at what is performance-based design, while I've already discussed what is the code-based evaluation, this is what the code says I can do, but that may not be enough. I may want to know what, based on the actual fire hazard or risk associated with the structure, what is the best approach? So the code may say, you're safe if you provide enough exits from this art museum, but my collection isn't safe enough to me by that. I have The Last Supper sitting inside, the painting The Last Supper sitting inside the building. I want to make sure that it doesn't get burned or hurt by fire in any way. So I may go way beyond the code approach, or I may have an atrium in the building or some kind of architectural feature that isn't typically utilized in the code or hasn't been recognized by the code. So I'll have to come up with a unique fire safety design that looks at hazard and risk to address or come up with what my final fire safety design is of the building. And what is it's based on performance. Now, when I'm looking at how is it different from the code, well, it's based on a hazard or risk assessment, and it evaluates a specific building or structure. When you look at the building codes or the life safety code, it bases it on a generic use or occupancy of the structure. So if I have a retail shopping area, I may always protect them to the same method. Or if I have a sterile support space for a building, you may always protect it to the same method. But if that sterile support area is located above an art gallery or above a collection that you're trying not to damage, or a manufacturing process you're trying not to damage, you may use a different level of protection than if you were just basing it on code, depending on if you meet your goals or objectives. And why do you use performance-based design? Well, the prescriptive code may not be feasible. You may have features, or it may be based on the system performance or to address specific project needs. You may be able to be trying to address specific needs or uses in the building. For example, in the American Indian Museum, you may be using your atrium as one of the ways that you're evacuating the building. So you may want to provide a greater level of safety. Or if you have a unique design, you may have a building that you cannot comply with code. It's just not anticipated by how you do the construction of the building or the design of the building. So you may want to include some special features that allow you to build a unique structure like that, or the architect and user and owner to obtain the aesthetic qualities that they're looking for, unique structure that they're looking for. Now, there may be different goals that you're looking for. Life safety would be protect the occupants not intimate with the fire for the time needed to evacuate. You want to make sure that your building structure is maintained so that you protect it so that it doesn't fall down, so that you are sure you can reuse the building. You may want to minimize the appearance or the impact of the fire safety features on the architectural features, or you want to make sure that your building is maintained so that you can continue to use it, or you don't lose critical operations, or you may want to protect your collections or whatever's in the building, whether it's a pharmaceutical operation or your valuable collections or artwork. you may want to maintain those. And performance-based design goes directly to addressing these performance goals. Okay, if I have these goals, then I have to define or develop some example of performance criteria that they need to be met to. So if one of my life safety goals is to make sure that people can get out of the building and that they obtain a quick exit from the structure and are able to evacuate before the fire affects them, you may come up with different performance criteria that I want to be able to maintain my visibility to greater than 10 meters or 30 feet so that I can see and I'm able to evacuate the building. There will also be exposure to temperatures or exposure to gases. Most people die from gases, so you would think, okay, you need to make sure that my carbon monoxide levels don't get too high and I don't expose the occupants to that. Why is visibility an issue? Because if people can't evacuate, they are much more likely to be exposed to these high levels of contaminants. You also want to make sure that the building or structure is maintained. You do an evaluation, and I'll talk about evaluation methods in a different section. And then you make sure that your egress time plus the safety factor is less than the time to hazardous conditions. So as long as I can get the people out with a safety factor before the carbon monoxide concentrations become high enough to incapacitate or kill someone, or before the visibility gets high enough so that people stop evacuating, then you can consider, all right, I've met my life safety goal of providing a high level of life safety within the structure. Now, when you do this, you end up having to do or evaluate what are my potential fires or what can potentially happen in a building. And when you're looking at this, you're looking at, okay, how can I quantize the exposure of the people to the potential fire scenario? So what you do is you may look at a typical office building and go, okay, I know from fires that I've seen and that data that I have that a fire will burn in this structure, and it will consist of a desk and a side cabinet and all the things that are in a desk, and it will develop being a heat release rate or amount of energy produced by the fire over time. And this is an example of a curve that has an 8,000 kilowatt maximum energy output with a fast growth rate and burns for 15 minutes. Well, that may be this one scenario. If I have a flammable liquid fire, it's going to grow much faster to a higher temperature probably, and then go down. The energy may be the same, but it will happen much quicker and be released much quicker. So you will have to develop fire scenarios that you were evaluating for each of these items. You then will go through and evaluate the risk. And again, you can look at risk as a hazard times the probability. The consequences will increase. There's things such as low consequences. An example of that, if I burn a piece of paper in this building, a single piece of paper, that will be a low consequence. Up to a high consequences would be me throwing a Molotov cocktail in this building. That would be a high consequence. So you're going to fit somewhere in that spectrum, and you can evaluate that using the engineering methods I'll be talking about. Then you have to look at the probability associated with these, and the probability will be from low to high probability. And a low probability event would be a plane crashing into a typical building. Now, that probability may increase, for example, in the Freedom Tower. Well, that was an actual thing that you're evaluating. To a high probability event, like a trash can fire in a room that I'm standing in right now, that would be a high probability event, or the probability increases. You would anticipate in the course of a building that building's life, that you will have a trash can fire and will need to address it. So what this does is sets up for different probabilities and different consequences. You then evaluate what your potential issues, where items or blocks identified in the white are okay. You're willing to accept that risk. In yellow, you have a moderate risk, so you're not less likely to accept them. And in red, you have a high risk. So in most buildings, you wouldn't accept a high risk. So you would not accept a high probability, extreme consequence event, or you would accept a low probability, extremely unlikely event. And you could go through this process based on the evaluation techniques we have. And then in developing what your selected design would be, you would look at it in two ways, and you would look at the options that meet your goals that you've established, and you would compare those with the cost, aesthetics, and feasibilities of those design approaches. And you may want to look at options that meet most of the goals. For example, if your goal was to make sure that you only have low probability, well, we'll have low and moderate probability events or low and moderate consequence events acceptable, and look at them relative to cost, aesthetics, and feasibilities, and then select your final design. So in summary, you have a performance-based design. It's different than your prescriptive approach. It uses fire risk and hazard assessment evaluation. There are numerous factors that influence the ultimate design, including cost, feasibility, and you want to make sure that you address those, including the ability of the design to meet your goals and objectives. I'm Eric Rosenbaum, Vice President for Hughes Associates Incorporated, a fire protection engineering firm. And this module, I'll be talking about engineering methods for determining fire safety designs. In previous modules, I talked about what are different fire safety designs, what are code-based methods, and what are performance-based methods. What I'll be discussing today, okay, how, if I use a performance-based method, or what are different methods that I have for determining fire safety in structures. What I'll be discussing are what are engineering methods, what are the types, and then I'll be giving you an example of different methods. Engineering methods are tools used to evaluate and incorporate aspects of fire safety design. You know, how do I, looking at a building, know what will make it fire safe? Well, we talked about the code approach in one module, and in the code approach, that provides you one specific method. I talked about performance-based design, and that's looking at, based on goals and objectives, what are the engineering, or how I can determine what is safe in a building. And those goals and objectives can only be evaluated through engineering methods. And there are engineering methods that will provide all kinds of data to you. What kinds of things will they do? Well, they can be used to determine system capabilities. What is my egress system capabilities? How do I get these people out? How good is the stair design or whatever I'm using to get the people out, to get them out? It can give me analysis data. For example, it can tell me how long a steel beam protected by a certain amount of fireproofing will last. Or it can tell me how hazardous a fire will occur from a certain sofa, from a certain office arrangement. It can also help me to evaluate the hazards associated with flammable liquid fires or different kinds of fires you might have in a building. Engineering methods also help you to determine your designs. This will tell me this amount of fireproofing gets me this fire resistance rating on the steel, so that's all that I would anticipate. I would anticipate it would withstand any fire that could occur within the building. It will also validate designs and make sure that the designs I'm using are appropriate for the structure. The engineering method will tell you, okay, this smoke control system works, or this smoke control system will probably work, or these different elements of the fire safety design will actually work for what your goals and objectives are. And they can also help you review the risk associated in a building. There are different types of engineering methods, and they range from simple calculations to very complex and detailed models. Those simple calculations, and they range from hand calculations, fire test models, and the models can include any kind of model from computational fluid dynamics or what is said CFD here, to an egress model, to acoustic model, to a fire resistance model. There are all kinds of models and all kinds of calculations that will allow you to evaluate in engineering terms what is being used. The hand calculations give you an example. They take out a calculator, they're simple calculations, and they will define what are the approximate conditions, whether it's the conditions associated with a fire that occurs in a building or how a smoke control system works, to a hazard associated with it, to whether the sprinkler system will work in a building. And a lot of these hand calcs could be defined or contained in the Society of Fire Protection Engineers Fire Protection Engineering Handbook. This isn't a small book, and it provides a lot of detailed calculations for how you want to address fire safety in building or how you can evaluate fire safety in a building. And to give you an example, for a smoke control system, you may want to evaluate whether the smoke control system will prevent smoke from moving one floor level, from a fire floor to a floor higher up in the building. Well, here's a simple calculation that is used to evaluate whether the smoke control system will prevent the migration of smoke. The other thing that you can use are fire tests. Now, if this isn't the best profession in the world where you actually get to burn things to assist what you're doing, I don't know what is. But you can use smaller full-scale tests to help you in your evaluation. And not only do they provide input to your design so they can tell you what kind of fire can happen so that you can evaluate, all right, this is what I'm trying to protect. It'll also validate, these are the designs that I want to use. For example, we had a museum came to us and asked, how can we evaluate what the protection method is that's best for our building so that we don't have artwork on the walls that is affected by a fire? And what we did is we came up with what we thought was the best approach, but the museum had ideas on other potential options. And we brought them in, we actually burned things in the back of our office, and we're able to show them, okay, this is why we think this protection is best, because you can see it has less impact on your artwork and makes them easier to recondition. Now, when you get to fire tests, you may have a building where you're trying to provide fire protection. They're not going to let you light fires in that building most of the time, A, because A, it may not be built yet, or B, they don't want you burning fires. They don't want the impact of the smoke into them. So another engineering method is modeling. You will go in and you will actually recreate the building or the structure of the hazard in different models that will be developed. And you may look at fire scenarios, smoke control, evacuation, egress, and these models can be developed by government institutions, universities, private entities will also input or develop models, and they will tell you, okay, these are the hazards that I see in this building based on this scenario, and will help you evaluate them. One of the most common fire model that is used these days is a computational fluid dynamic model, or CFD model. And the most common one used was developed by NIST, and it's called Fire Dynamics Simulator. And what it does is provide a simulation of heat and smoke transport throughout a building. And what it does is divide a building into millions and millions of grids or cubes so that you can evaluate what the potential hazard is from a fire in one part to a fire in another part. So if you take this building right here and you said, okay, I'm going to put a fire down here in the base of the atrium, and I want to see, okay, the fire can go up through the atrium or can spread across the atrium and up. What are the potential impacts? This fire dynamic simulator would actually give you an idea, based on this fire that you have specified, what the potential hazard is throughout the building. Well, this model gives you an idea right here of, okay, if you just had a fire, what would happen? You can then take that model of a different building, this is a different building, and say, on this model, I have no exhaust. What is the potential impact? And in this model, I'm going to provide exhaust. So I'll show you what the potential impact of that is. Okay, so what you'll see in this scenario is you'll see a fire that starts and you can see the smoke spreading across the top. In the no exhaust scenario, the smoke then spreads totally throughout the building. Whereas in the exhaust scenario, you can see, because you have smoke exhaust from the top of the building, the smoke is maintained above the office building, which is on the right side of the structure, so that the occupants in the office building are not affected by the smoke in that portion of the structure. So you just saw from that simulation how you can use this engineering method to provide an evaluation of how smoke control works. You can then look at the egress and how people get out of the structure and make sure they get out of the structure before the time of a hazard or before they're exposed to that smoke. Another item is looking at, okay, how long does it take the people to get out? And they have engineering methods or models that can be used. Now, you can use a simple hand calculation that looks at people as hydraulics flowing through a pipe, or you can use a model such as Exodus, which will provide you a simulation of how the people evacuate and an idea of how long it takes. And this evaluation will show you people exiting using 3 stairs out of a structure. This model depicts the people leaving the structure. It shows them spreading out among the 3 stairs, actually making a decision which stair to go up, and then evacuating. You can see on the left-hand side are the people going up the stairs. On the right-hand side, it shows the people coming up and leaving the building. As you can see, with the 3 stairs, there is no queuing. There is no one waiting at the bottom, so the evacuation works very well. Now, the next video shows the same people leaving the same structure, but we're only using 2 stairs in this case. And what this does is allow you to evaluate, and the owner and the user to evaluate, okay, based on the occupant loads and making sure people can get out, it gives you an idea that the difference between 2 or 3 stairs doesn't really make a difference. So you're actually able to evaluate, okay, what does the impact and the cost and what are this associated with the different uses of the structure? Okay, so what you've seen is different engineering methods. I want to emphasize, I showed pretty pictures that resulted from computer models that show you people egressing or the hazard associated. You can also do that through hand calcs. It's not going to be as detailed, and it's not going to be pretty picture, but it will probably result in less time of calculations, and hand calcs will potentially be easier to utilize in the structure. Okay, so what I've done is depicted some of the engineering methods that will help you evaluate fire safety concepts. The types include models, hand calculations, and fire tests. The uses including demonstrate whether a design will work, validating approach, or gathering input data. So through my 4 modules, I've essentially discussed how do fire protection engineers design what level of fire safety should be provided in buildings. That can be based on the code, or it can be based on achieving goals and objectives that were established by the users or the different stakeholders in the building. The roles, regulations, and codes provide is to set what are the basis for the determination of an acceptable level of safety in the building. And I also described what engineering methods are available as decision aids in determining what fire protection systems to include. That included hand calculations, models, and fire tests.